आपकी आवाज नहीं आ रही जगदीश सर।
हेलो, गुड मॉर्निंग।
गुड मॉर्निंग सर।
Good
Hello.
morning, sir. Good
मॉर्निंग।
morning, sir.
Good morning. Good morning.
Good afternoon.
Good morning, sir.
मॉर्निंग।
Good morning to each and everyone.
Good morning.
Good morning, everyone. Good morning
Thank
to
you
all
for
of
your
you.
patience. Thank you for your patience, and we shall now proceed because our main dignitaries have joined.
What?
I once again welcome you all to Physics Powering Industry 4.0 Global Summit, organized by JSS University Noida. Welcome to all of you once again. Saraswati Namastubhyam Varde Kamarupini Vidyarambham Krishayami Siddhir Bhavatu Me Sada. With the blessings of Goddess Saraswati, the embodiment of knowledge, wisdom, and learning, we seek divine guidance as we begin this journey of science, innovation, and discovery. A very good morning to one and all. I am Dr. Nupur Gupta from Department of Physics, JSS University Noida, and it is both my honor and privilege to serve as your host for today's prestigious event. I extend a warm welcome to our distinguished dignitaries, respected guests, eminent speakers, industry experts, faculty members, and all the participants joining us from across the country and beyond. With the divine blessings of His Holiness Jagat Guru Sri Shivratri Deshikendra Mahaswamiji, the guiding force of JSS Mahavidyapitha, it is my privilege to welcome you to Physics Powering Industry 4.0 Global Summit 2026, organized by Physics Department, JSS University, Noida. Today, we have the privilege of bringing together some of the finest minds from academia, research laboratories, and industry to explore how physics is driving technologies of tomorrow. Though through these insightful discussions on artificial intelligence, quantum technologies, photonics, advanced materials, smart manufacturing, and renewable energy, today's summit promises to spark new ideas, foster meaningful collaborations, and inspire innovations that will shape the future. As is our cherished tradition, we shall now invoke the blessings of the Almighty through the sacred Gayatri Mantra. Though we gather today on the virtual platform, the timeless prayer unites us in our shared pursuit of knowledge, wisdom, and enlightenment, the very ideals that lie at the heart of education, research, and scientific discovery. Gayatri Mantra.
ॐ भूर्भुवः स्वः तत्सवितुर्वरेण्यं भर्गो देवस्य धीमहि धियो यो नः प्रचोदयात् भूर्भुवः स्वः तत्सवितुर्वरेण्यस्य भर्गो देवस्य धियो नः
I think we have extra blessings of Goddess Saraswati at this particular moment. With these divine blessings and wishes for a fruitful and inspiring day ahead, we now formally commence the inaugural session of Physics Powering Industry 4.0 Global Summit 2026 to formally welcome our distinguished guests and set the stage for an inspiring day of learning and collaboration. It is my privilege to invite Dr. Richa Verma, Head of Department of Physics, JSS University, Noida, to deliver the welcome address. Ma'am, may I kindly request you to address the gathering?
With the divine blessings of His Holiness, Jagat Guru Shri Shivratri Deshikendra Mahaswamiji, I extend a very warm and cordial welcome to all of you to the Physics Powering Industry 4.0 Global Summit 2026, organized by the Department of Physics, JSS University, Noida. It is my privilege to extend a heartfelt welcome to esteemed Vice Chancellor Professor H.R. Mahadeva Swami Sir, Dean Academics Dr. B. Manoj Kumar Sir, Academic Coordinator Professor R.S. Jagdish Sir, all deans, heads of departments, officers of the university, faculty members, and my dear students. We are deeply honored by the gracious presence of all our distinguished guests and speakers. I would especially like to welcome Professor Ram Manohar Yadav, Department of Physics, University of Allahabad, Uttar Pradesh, as our chief guest and keynote speaker. Dr. Bindya Arora, Department of Physics, Guru Nanak Dev University, Amritsar, Punjab. Professor Manmohan Singh Sisodia, Gautam Budh University, Greater Noida. Dr. Alok Singh, Department of Renewable Energy Engineering, Navsari Agricultural University, Gujarat. Professor Atul Khanna, Department of Physics, Guru Nanak Dev University, Amritsar, Punjab. Dr. Deepak Kumar, Managing Director, Webmentix Technologies Private Limited, Noida. And Dr. Pavan Tripathi, Researcher at a National Laboratory, Illinois, USA. The theme of this summit, From Fundamental Physics to Smart Factories, reflects our shared vision of bridging the gap between academia and industry and preparing the next generation of scientists, engineers, and innovators for the opportunities and challenges of the future. Once again, I extend my sincere gratitude to all our distinguished guests, speakers, faculty members, and students for joining us today. Thank you, and I wish everyone a fruitful and enriching summit. Let us remember that to build a smarter and a more sustainable world and future, we have to keep learning. Thank you.
Thank you very much, ma'am, for your warm and gracious words of welcome. Your inspiring address has beautifully reflected the vision behind the summit and has set a wonderful tone for the enriching deliberations that lie ahead. To provide us with an overview of the objectives and structure of today's summit, I now invite Dr. Manisha Chaudhary, Department of Physics, JSS University, Noida, to address the gathering. Ma'am, may I kindly request you to present the summit overview.
Thank you, Dr. Nupu. Good morning, everyone. It's my great pleasure and honor to present an overview of the International One-Day Summit, Physics Powering Industry 4.0 Global Summit 2026. The summit brings together academicians, researchers, scientists, and industry professionals to explore the role of physics and emerging technologies in the smart manufacturing, automation, and sustainable development. The summit comprises a keynote address, 3 invited talks, a case study, and a panel discussion, covering a wide range of the emerging areas at the interface of science, technology, and industry. The technical session begins with the keynote address by Professor Ram Manohar Yadav, University of Allahabad, Uttar Pradesh, on nanoscience from fundamental to real-world application and challenges, where he will highlight the importance of the fundamental physics in enabling intelligent and automated industrial systems. The first invited talk will be delivered by the Bindya Arora, Dr. Bindya Arora, Guru Nanak Dev University, Punjab, on building atomic cyber infrastructure for quantum computers. Her talk will provide insight into the growing significance of quantum technologies and their potential application in future industries. Following the tea break, Professor Manmohan Singh Sisodia, Gautam Buddha University, Greater Noida, will deliver the invited talk on photonics and advanced physics in smart manufacturing, focusing on how photonics and advanced optical technologies and contributing to precision manufacturing and industrial advancement. The summit will also feature a case study by Dr. Alok Singh, Navsari Agriculture University, Gujarat, on transforming the agriculture and renewable energy sector through Industry 4.0 technologies. The session will highlight the role of AI, automation, and smart technologies in advancing sustainable development. After the lunch break, Professor Atul Khanna, Guru Nanak Dev University, Punjab, will deliver the invited talk on material physics for next generation industrial system. This session will highlight the role of advanced materials and their characterization in driving innovation for modern industries. A major highlight of the summit will be the panel discussion on bridging the academia industry gap in physics lab and AI-driven innovation. The panel will feature Professor Atul Khanna from Punjab, from Professor Manmohan Singh Sisodia, Greater Noida, Dr. Deepak Kumar, Greater Noida Web Maintenance Technologies, Dr. Pavan Tripathi, researcher from US. The session will be moderated by the Dr. Pratima and will explore strategies for strengthening academia-industry collaboration, fostering innovation, and preparing the talent for the future technology changes. Overall, the summit provides an enriching opportunity for knowledge and share, industry, interdisciplinary collaboration, and meaningful interaction among participants. Now, over to Rupal.
Thank you, ma'am, for presenting such a comprehensive overview. We now look forward to an exciting day filled with insightful discussions, meaningful interactions, and inspiring ideas. Every successful initiative begins with a vision, but it flourishes through dedicated leadership, encouragement, and collaborative effort. Today's summit is the result of such guidance and commitment. May I respectfully invite Professor Dr. R.S. Jagdish, Dean Student Welfare, Academic Coordinator, and Summit Chair to deliver the opening remarks. Sir, we request you to kindly address the gathering.
Thank you. Good morning to everyone. With the divine blessings of His Holiness Maha Swamiji, it gives me immense pleasure to welcome you all to the inaugural session of Physics Powering Industry 4.0, a Global Summit 2026. I extend my respectful greetings to our visionary Vice Chancellor, Dr. H.R. Mahadeswamy, whose dynamic leadership is driving the SS University towards excellence in education, research, innovation, and global collaboration. I also warmly welcome our Dean Academic, Dr. B. Manoj Kumar, Finance Officer, Controller of Examination, all heads of the department, distinguished resource persons, faculty members, students, industry experts, and participants joining us from across India and around the world. Industry 4.0 is transforming manufacturing and technology through artificial intelligence, robotics, smart sensors, quantum technologies, advanced materials, automation, and the Internet of Things. At the heart of these innovations lies physics, the fundamental science that enables precision, efficiency, sustainability, and technological breakthrough. This summit provides an excellent platform to exchange ideas, foster interdisciplinary collaborations, and explore emerging technologies that will shape the industries of tomorrow. I sincerely appreciate Department of Physics for its meticulous planning and dedicated efforts in organizing this global summit. My heartfelt thanks also go to the convener, coordinator, organizing committee, student volunteers, and all the distinguished speakers for their valuable contributions and unwavering support. I am confident that today's deliberation will inspire new research, strengthen academia-industry partnership, and contribute meaningfully to the vision of Vikasit Bharat and Atmanirbhar Bharat through scientific innovation and technological excellence. I wish all the participants a fruitful, enriching, and a memorable summit. Thank you, and I declare this inaugural session open.
Thank you, sir. Thank you for your inspiring words and visionary thoughts. Your message has truly reinforced the importance of strengthening the partnership between academia and industry for the advancement of science and technology. As we continue today's program, it is fitting to hear from an academic leader who has consistently promoted quality education, innovation, and skill development. His encouragement has helped create an environment where students and faculty are inspired to learn, innovate, and engage with industry. It is now my privilege to invite Dr. D. Manoj Kumar, Principal, JSS Academy of Technical Education, and Dean Academics, JSS University, Noida, to address the gathering. Sir, kindly share your thoughts with all of us.
Thank you. Am I audible?
Yes, sir, you're audible.
Yeah, thank you. Thank
Good
you.
morning, sir.
Good morning, very good morning. Honorable Vice Chancellor, respected Professor Ram Manohar, today's chief guest, and all other distinguished speakers, Dean Student Welfare, HODs, faculty member, and my dear students, very good morning to all of you. With the divine blessings of His Holiness Jagadguru Sri Shivaratri Deshikendra Mahaswami Ji, it is my privilege to chair today's event on Physics Powering Industry 4.0, a Global Summit 2026. On this occasion, I extend my heartfelt congratulations to the Department of Physics for organizing this summit on the theme From Fundamental Physics to Smart Factories, which is nothing but science to engineering. The chosen focus areas for this summit includes quantum technologies, photonics, AI in smart manufacturing, sustainability, and renewable energy. They have covered everything, and this reflects the evolving role of physics in shaping Industry 4.0 and a sustainable future. On behalf of our university, I thank the eminent speakers who will be sharing their valuable expertise and insights in this summit. I appreciate the dedicated efforts of the department in bringing together such an outstanding platform for knowledge exchange. I look forward to many more such events in the coming days, and the initiatives should be industry-oriented and which will empower our students, strengthen innovation, and bridge the gap between what we teach in the classroom and what is practiced in industries. I once again thank the head of the department and all the faculty members for organizing this summit. I wish this summit a success. Thank you.
Thank you very much, sir. Your thoughtful address has beautifully highlighted the importance of interdisciplinary learning, innovation, and industry-oriented education. Your words will undoubtedly inspire our students and researchers to think beyond conventional boundaries. The success of any institution is shaped by visionary leadership that inspires excellence, nurtures innovation, and creates opportunities for future generations. We are truly privileged to be guided by such inspiring leaders at JSS University. It is now my proud privilege to invite our Honorable Vice Chancellor, Sir, Dr. H.R. Mahadev Swami, whose visionary leadership continues to inspire excellence in education, research, innovation, and societal development. Sir, we are deeply honored by your gracious presence. May I respectfully request you to deliver the presidential address.
Yeah, so thank you. Good morning to everyone. Seeking the blessings of His Holiness Jagadguru Sri Shivaratri Deshikendra Mahaswamiji, respected chief guest of today's program, Dr. Ram Manohar Yadav, distinguished speakers, eminent academicians and industry leaders, researchers, faculty members, dear students and participants joining this program from different parts of India and abroad. Very warm good morning to all of you. It gives me immense pleasure to welcome each one of you to this Physics Powering 4.0, Industry 4.0 Global Summit 2026, organized by the Department of Physics, JSS University, Noida. Maybe this is the 15 such summits are organized at the JSS University in this summer break, and all the topics are related to the advanced and emerging technologies powering AI. So this is the one thing. So each department has conducted such kind of summit, bringing the different eminent scientists, eminent people to the platform. Let me just ask a question. Allow me to begin with a simple question. When we hear the words Industry 4.0, what comes to our mind? Maybe, of course, Industry 5.0 is already evolving. Let's keep that side. So when we hear the word Industry 4.0, what comes to our mind? If you ask engineering or the business people, number one is the artificial intelligence, robotics, automation, smart manufacturing, maybe digital twins, quantum computing, maybe list goes on. So these are indeed the technologies defining the future. Maybe there are many more, of course, let's leave that. They are defining the future. But there's another question we should ask ourselves. What is the science behind all these technologies? What is the science behind all these technologies? The answer is physics. So physics is not just merely a subject taught in classrooms. It is the language through which nature explains itself. It is the science that enables us to understand matter, energy, light, electricity, materials, quantum phenomena, and laws that make every technological breakthrough possible. Right? Simply put this, without physics, there's no semiconductor. Without semiconductors, there's no artificial intelligence. Without photonics, there's no high-speed communication. Without material science, there's no electric vehicles. Without quantum physics, there's no quantum computing. So Industry 4.0 may be powered by digital technologies, but the heartbeat is physics. So today, industries are transforming by digital technologies, but heartbeat is physics. So the industries are transforming at an unprecedented pace. Factories are becoming intelligent. Machines are communicating with one another. Sensors are generating massive amounts of data. Renewable energy systems are becoming smarter. Healthcare is becoming more precise. Advanced materials are making products lighter, longer, stronger, and more sustainable. So this is what is happening. Behind every one of these transformation lies decades of fundamental research in physics. So that's why this summit is so timely. So this is how we have planned Physics Powering Industry 4.0. So it reminds us that while innovation often captures headlines, but it is scientific discovery that creates foundation for lasting innovation. So at JSS University, Noida, we strongly believe that universities should not merely produce graduates. They should produce innovators, researchers, entrepreneurs, and the problem solvers. So our vision is to build an ecosystem where education, research, innovation, entrepreneurship, and industry engagement work together seamlessly. Through interdisciplinary learning and strong collaboration with academia, research laboratories, startup and industries, we aim to prepare our students not only for industries, today's jobs, but also for careers that will emerge over the next decades. So the Department of Physics has taken a commendable initiative in organizing this summit by bringing together experts from universities, research organizations, and industry to discuss emerging areas such as quantum technology, photonics, advanced materials, artificial intelligence, smart manufacturing, and sustainable energy. So these are not isolated disciplines. They are interconnected. The interconnected technology that will shape the industries of tomorrow. So dear participants, knowledge grows when it is shared. Innovation flourishes when different disciplines come together. Today's summit is not just about listening to expert talks. It is about asking questions. It is about building collaborations. It is about connecting young research scholar with experienced scientist, a faculty member with an industry expert, a student with a future mentor. Sometimes one meaningful conversation can inspire a research project, a startup, a patent, or even a lifelong career. I encourage every participant to actively engage in today's discussion and make the most opportunity. As we move towards an era defined by intelligent system, quantum technologies, sustainable manufacturing, and green energy, and one thing becomes increasingly clear. The future will not belong to those who simply use technology. It will belong to those who understand the science that creates the technology. So friends, so maybe having said this, there is a lot many things. These are not isolated disciplines. These are all connected disciplines. So that is the science of physics. So, and therefore, investing in physics, education and research is not merely an academic priority. I believe it is a national and global necessity. So this is the physics. So before I conclude, I congratulate the Department of Physics and organizing committee, faculty members, and every individual whose dedication has made this international summit possible. So also thank our distinguished speakers and participants for being part of this important academic initiative. I am confident that today's deliberations will generate new ideas, inspire meaningful collaborations, and contribute in advancing knowledge for a smarter, more sustainable, and technologically empowered future. With these words, I declare Physics Powering Industry 4.0, a global summit 2026 is inaugurated, and with the summit, wish the summit a great success. Let us remember, physics discovers, engineering designs, industry transforms, together they build the future. Thank you. Namaskar. Jai Hind.
Thank you, sir.
Thank you very much, sir. Thank you very much, sir. Your words have reminded us that meaningful innovation is driven not only by scientific excellence, but also by the purpose and responsibility, and we should be motivated enough to work on it. We are deeply grateful for your constant encouragement and the unwavering support, which has been instrumental in transforming the vision of this summit into a reality. Your leadership continues to inspire us to strive for excellence in education, research, and innovation. Once again, thank you for your motivating words and for graciously blessing today's event with your presence. Before we begin, may I request everyone to kindly switch on your cameras. It would be wonderful to see you all, and we would love to capture a group photograph, even though this event is virtual. It will be one moment to capture with all the participants before we start with the formal proceedings. Your presence on the camera will make the moment even more memorable. Okay. Thank you so much. Thank you for this, to confirming to my request. Now, without any further ado, with an inspiring beginning to today's summit, we now move into the academic segment of today's program, where ideas, innovation, and scientific excellence will take the center stage. It is now my pleasure to hand over the proceedings to Dr. Rohit Srivastava, who will coordinate the keynote address. Dr. Rohit, the virtual stage is all yours.
Thank you, Dr. Nupur ma'am. Good morning, everyone. I am Dr. Rohit Kumar Srivastava, Department of Physics, JSS University. On the behalf of the Department of Physics, it's my great pleasure and privilege to welcome our distinguished speaker, Professor Dr. Ram Manohar Yadav. Professor Yadav is a professor in the Department of Physics at the University of Allahabad, Prayagraj. He completed his PhD in Physics Nanoscience from the Banaras Hindu University in 2008. He is internationally acclaimed researcher in the field of nanoscience, nanomaterials, and renewable energy application. In 2013, Sir served as a visiting researcher at the University of Santiago, Chile, under a project funded by the government of Chile. In the same year, he was awarded the prestigious Raman Fellowship by the University Grant Commission, India, under the Indo-US 21st Century Knowledge Initiative. This fellowship enabled him to pursue postdoctoral research at Rice University, US, where he is also served as an adjunct professor in the Department of Material Science and Nanoengineering. In 2019, he received the highly prestigious Fulbright Nehru Academic and Professional Excellence Fellowship. As a Fulbright visiting faculty, he joined the George R. Brown School of Engineering at Rice University. Sir has authored more than 65 research papers in leading international journals, including Nature Communication, ACS Nano, Carbon, Journal of Alloys and Compound, Nanoscale Advances, and many more. His current research focuses on carbon nanostructure, graphene, carbon nanotube, carbon quantum dot, graphite carbon hydrate, and their application in renewable energy, technology, and advanced functional materials. Today, sir will deliver a talk titled From Fundamental Physics to Smart Factories. With great pleasure, I now invite Professor Ram Manohar Yadav, sir, to address the audience. Sir, we sincerely appreciate your presence and look forward to your valuable insight. Sir, the virtual stage is yours.
The esteemed dignitary from the JSS University in Noida, all the speakers, participants, and students. Good morning to you all. Today, first of all, I would like to thank JSS University in Noida and the organizer to invite me for this keynote address. Today is the word of innovation, and we are in the AI era, but we have to think from where this AI came. So the stepping stones of all these industry, all these innovations are actually science. And we all are the students of science. Today, my task is to give you some fundamentals about the nanoscience and nanotechnology that is beneficial for students, and then some applications and what challenges we are facing right now to make a sustainable technology, because the main problem of any industry to sustain, if we are not talking about the challenges, it is not possible to make a sustainable technology. So with these words, I am just going to start my presentation. So today I am going to talk about the fundamental of nanoscience and nanotechnology. Many people know about nanoscience, but why nanoscience is so important? What is the benefit of these nanoscience? Because before nanoscience, we have already known about the atomic physics, nuclear physics, and the mechanics governed by the classical physics. So what is the importance of these nanoscience that all over the world, people are talking about? Most of the funding agencies funded almost more than 50% only to nanoscience and nanotechnology. So every technology okay. So before going to nanoscience, I just want to tell you that how fundamental physics transform the society. For example, the discovery of electromagnetism by Faraday or the discovery of electromagnetic theory by Maxwell leads to the electric motor, automation, even the industrial Internet of Things. So these basic discoveries are actually the stepping stones of the current industry. And what we have studied or what we have innovate right now in the laboratory, maybe in the future that is the stepping that will be the stepping stones of modern or future technology. So the second example is when Edison discovered this bulb, and then right now we are in the LED era. So that is the discovery from Edison, then Planck discovery of quantum theory, then semiconductor physics. So all these fundamental physics discoveries are the backbone of the current industry. Like when wave nature of electron discovered, then electron microscopy came into the picture. And before electron microscopy, no one can think about the microstructural and structural characterization of these nanomaterials, which we have right now working a lot. So this electron microscopy discovery actually begins the era of this nanoscience and nanotechnology. Just like this, the Raman effect. When Raman discovered this Raman effect, it is only the inelastic scattering of light. But right now, it is one of the most powerful characterization tool in science and engineering, even manufacturing. So in physics, electromagnetism gives you wireless communication, quantum mechanics, processor chips, semiconductor memory devices, optics, camera, nanoscience, many things, then material physics, solid state battery, etc., etc. Today we are talking about the industry 4.0. So what about the industry 1.0, 2.0, 3.0, and 4.0? And then right now, some people are talking about this industry 5.0. So 4.0 is actually the nanoscience and AI to make smart factories. So that's why I have chosen the topic of nanoscience and nanotechnology. I am also working in this area. So I am going to talk about this nanoscience and nanotechnology. What is the real application and what challenges we are facing worldwide. So the importance of this nanoscience and nanotechnology is there are many Nobel Prizes awarded in this field. It started from the discovery of electron microscopy, scanning tunneling microscopy, and electron force microscopy. And the recent one is that the Nobel Prize of Chemistry in 2023 for the discovery of quantum dots. I will discuss about what quantum dot is. So many people are right now talking about nanoscience and nanotechnology. What is nanoscience and nanotechnology? What it is, at what dimension we are working, what is the basis, what is the fundamental physics behind this nanoscience and nanotechnology, how it is too much interesting. So the only thing is the study at manipulation of materials at nanoscales, the study and manipulation of science and nanoscale, where all the science are unified in one. So it is not new. Actually, the nanoscience is not new. People know from very beginning about this, but they don't know it is nanoscience and nanotechnology. What is the reason behind this this change in properties? But they have already created and used this. It is not created by man. It is already existed in nature. These are some few examples. So the best example is by nanoengineering. I mean, by the nature nanoengineering. This is the example on the screen. You see it, that the natural demonstration of nanostructuring. The same calcium carbonate is in our chalk, and it is on this construction. What happened when we go from bulk to nanoscience? So new properties emerges, sometimes gravity losses. So what is the history of this nanoscience and nanotechnology? Ireland people make stained glass in year 444. The Italian people use nanoparticles in pottery industry and color in pottery, and the Arabian people use carbon nanotube for strengthening steel sword. The modern nanoscience begin with, I can say from the lecture of Feynman that there are plenty of room at the bottom. The first atom seen by beginning and or after the discovery of STM, and then there is a boom in nanoscience and nanotechnology. It is naturally occurring from very beginning in forest fires, sea spray, mineral composite, etc., etc. Some human origin like cooking smokes, diesel exhausts, and some engineered like metal, quantum dot, buckyball, nanotube, which we have made in laboratories. So nanoscience and nanotechnology, the unification of all the branches of science, not only physics. So how small is nano? I started, this is, these slides, few slides for students. So if you take the ratio of earth to football, that is the same to ratio of football to a nanoparticle called fullerene. That is a nanostructure of carbon. So that way we may imagine how small is nano. The real life, for real life experiences, you may see the human fingernail grow 1 nanometer every second, a beard grow 5 nanometer every second. So that way you may, imagine how small the nano is. If you have a 1 teaspoonful of paint and you want to paint a field having one nanometer thick layer of paint, that 1 teaspoonful of paint is sufficient. So actually, when you say 1 nanometer, you all know that if that is equal to 10⁻⁹ meter. So a sugar molecule, DNA molecule, viruses, and these all are in the range of nanometers. So the then thing is how to define these nanomaterials, or how to define the boundaries of nanoscience. So generally speaking, people said that it is if any dimension of the material is in between 1 to 100 nanometer, you may say it's a nanomaterial. But that is not always true. Sometime in semiconductors, you say the nano size effect come into picture at around 200 nanometer. And even in metals, it comes around below 50 nanometer. So it depends on property to properties, and it depends on material to material. So how to define then nanomaterial, how to define then the dimension of this nanoscience? So you can say when this property of the materials, not only depend on the chemical nature, because in the bulk material, properties always depend on the chemical nature. What is the, how many electrons in the outer cell, what is the, how the structure of this material. But when the properties not only depend on the chemical nature, but also on the shape and size of the material, then you can say it's a regime of nanomaterial. So why these properties changes at this scale? So this is the I think the excitement of this nanoscience and nanotechnology. So two things are basically important. One is surface to volume ratio, and the second is quantum confinement. So in the next slides, I am going to tell you how, I want to teach you how you can visualize how this surface to volume ratio is going to change, how quantum confinement effect going to change this, and responsible for the properties of these nanoscience and these nanomaterials. So the first example is the electrical conductivity of any material. So it depends on the flow of electron. But whenever the distance is comparable or less than the mean free path of the electron, then the definition of electricity, the basic physics is not going to work there, and new physics and chemistry come into picture. So this is the beauty of this nanoscience and nanotechnology, because gold is golden, but at nano sizes, gold is not golden. Even copper is going to transparent, aluminum is going to explosive. So these properties come from when the length scale is comparable to some characteristic lengths, and at that dimension, the classical physics principles break down. So there are few examples of these characteristic lengths, like lattice constant, atomic radius, exciton Bohr radius, electron mean free path, magnetic domain wall, and optical wavelength, etc., etc. So when material size approaches this characteristic length, then only nanoscience dimensions begins. So then today I am going to talk in detail about the surface area and the quantum confinement. So here we see that the smaller particle having greater surface to volume ratio than the bigger particle. You can see here that 2 centimeter cube have a surface area of 24 centimeter square and a volume of 8 centimeter cube. But the bigger one has 10 centimeter cube, has a 600 centimeter square of surface area and a volume of 1000. So the ratio decreases as the size increases. So here we can say that whenever you cut down the sizes of any material, the surface area, surface to volume ratio increases. The other thing is how surface area scales. You may take single particle having radius 1 centimeter of a spherical particle. So the volume of both the cases are same, but the surface area changes. So here you see that when you make 8 particles from a single 1 particle, the volume are same, but the surface area increases. It becomes just double. What to see when you go in the nano size. So for 1 centimeter cube has a surface area of 6 centimeter square. If you make many cubes having dimension 1 millimeter, then the total surface area is around 60 centimeter square. And if again miniaturize and make a cube having a dimension of 1 nanometer, then there is a extreme around 6 crore centimeters. So that way you can say that all the atoms of the material, almost all the atoms of the material are on the surface. They are in a position to react from so reactivity at maximum. So that's the actually responsible for all the properties of these nanomaterials. The second thing is quantum confinement. So if you are talking about the quantum confinement means whenever you miniaturize one dimension, then it is called one-dimensional confinement, and you get quantum well or a sheet of paper. Like if you say that you have a sheet of paper having dimension in nanometer, then you say that it's a 2-dimensional material. Right now, people are saying it is a 2D material. So in 2D material, the confinements are only in 1 dimension. And in one-dimensional material, the confinement are in 2 dimensions. And in 0-dimensional material, like nanoparticle, quantum dots, etc., the confinement in all 3 dimensions. That's why quantum dots are more exciting for innovative properties. So, based on the dimension, you may classify these nanomaterials in different categories. Like 0-dimensional nanomaterial means the quantum confinement in all 3 dimensions. The examples are quantum dots, fullerene, nanoparticles, etc. If quantum confinement in 2 dimensions, then it is called 1-dimensional nanomaterial. Examples are metal nanorods, nanowires, carbon nanotubes, etc. And if the miniaturization is only in 1 dimension, then you say it's a 2D material, like graphene, simple graphene sheet, and other 2D materials. There are one more classification that is called 3D nanomaterial, not bulk. Here the example is bulk, but there is one classification that is 3-dimensional nanomaterial. That's why you can say it's a nano-structured material. When you are saying it's a nano-structured material, the material itself is not in the size of nano, but the grain size in the nano regime. So that's why we get the properties of nanomaterials. So what happened when we miniaturize the properties from 3D bulk to 2D, 1D, and 0D? So you can say, if you are talking about the band gap, you can say, when you are approaching towards atoms, 0-dimensional is like the density of states curve. You see here, the density of state curves are going to be discrete. So the beauty of these nanomaterials are, we get the properties of atoms and molecules at this scale. The one example is the band gap. Whenever you miniaturize the size, the band gap increases. And the band gap is here, there is 2 types of band gaps is there. Always there are 2 types of band gap is there. One is optical band gap, and the second one is electrical band gap. For few materials, both are equal, but actually not always. So the binding energy of electron-hole pair is the difference between the optical band gap and electronic band gap. So for optical properties, we have to, the material which have equal optical and electronic band gap are beneficial, but for electrical and other applications, the counter one is the more beneficial. There are the optical properties of semiconductor and metal, the physics behind it is different. In metal nanoparticle, the surface plasmon resonance is the responsible for that. And for in semiconductors, nanoparticles, the quantum confinement or band gap, it is basically for based on this quantum confinement. These are some example of the optical properties of metal nanoparticles. Like whenever you are talking about the gold, many people already know about the color of gold. So when you go at nano scale, the same gold is not golden. It may be orange, it may be purple, it may be yellow. So it depends on the shape, not only shape and size of the material. So in semiconductor also, the same thing happened at larger distances. Then how these nanoparticles have, how to prepare these nanomaterials. So there are 2 ways to prepare these nanomaterials. One is top-down approach and the other one is the bottom-down approach. Bottom-up approach, sorry. So in bottom-up approach, we take the gaseous state, like, we have to start from the atom and manipulate things atom by atom to make cluster and all structures. And it top-down, you take the big one and then crush it and make the smaller particles. For the homogeneous and for equal good quality of nanomaterials, always the bottom up approach is good. This one is the example of top-down, the Teeter ball mill. I am not going in detail. These are the example of some bottom-up approach. Why only after the discovery of electron microscope there is a boom in the research of nanoscience and nanotechnology? Because before that we didn't know about the microstructure of these particles. So after the discovery of the microscope, we are in a position to so I'm not going in detail on these slides because of time limitations. So these are some microscopes. So after the discovery of STM, AFM, scanning electron microscope and transmission electron microscope, there is a big boom in the research of nanoscience and nanotechnology. And right now we are in a position to visualize atoms in the structure. So these are some example of metal nanostructures. I am working on carbon nanomaterials, so that's why I am going to give you some example of these carbon nanomaterials. Like the well-known allotrope of carbon are diamond and graphite. So from graphite, it is there are many type of other carbon nanomaterials have already evolved, like graphene oxide, carbon nanodot, or carbon quantum dot. Again, I am not going here in detail. This is a structure having 60 carbon atoms, known as buckyball. Graphene is you can say it's the father of 2D material. So if you take single sheet of graphite, it is graphene. And if you fold it, you get a different type of structure that is called carbon nanotubes. I mean, it's like that, simple like that. If you take a simple sheet of paper and fold it like this, fold it like this, fold it like this, or fold it like this, the different angles. So you get different type of nanotubes. So what is the beauty of these different type of nanotubes? So it depending on their diameter and chirality. So chirality defined about from the angle. What is the angle between this chiral vector and A1 vector? So depending on their diameter and chirality, the same nanotubes are either metallic or semiconductor. So that way, if you want to make a junction of metal semiconductor junction, you only have to make a nanotube of different diameters. So that way, so some are semiconducting, some are metallic. Here is an animation which can show you how these nanotubes can be formed. Zigzag is always semiconducting, armchair is always metallic, and the chiral is sometimes metallic, sometimes semiconductor. There are different type of nanotubes. Here is a video how these nanotubes grow in the lab. Then the carbon quantum dot, the zero-dimensional carbon nanoparticle having the dimension about 10 nanometer only. If greater than 10, it is not actually is a quantum dot, but if at the dimension of 10 nanometer or below 10 nanometer, you can say it's a quantum dot. So it is of two types, either sp2 hybridization, sp3 hybridization, either amorphous. So it is sometimes called graphene quantum dot, but sometimes called carbon quantum dot. If only sp2 hybridization is there and there is a crystalline structure inside the core, then you say it's a graphene quantum dot. Otherwise, it is a carbon quantum dot. So these are of different kind. And right now, the market, the average growth rate of these carbon quantum dot industry before 2026, 21 to 26, it is around 16%. But right now it is expected that from 2030, it is growing at around 29%. So there are many work already in the market, quantum LED and many other things. It has already been worked in many fields. We have used carbon quantum dots in our work as a catalyst to convert this carbon dioxide into commodity chemicals like ethanol, ethylene, etc., methane. So that way, I mean, we can use this carbon quantum dot for many applications. Here is the process. The best one is the hydrothermal process for the synthesis of these carbon quantum dots. You can make the properties modified by doping and functionality. You may tune band gap, photoluminescence properties, enhance stability by functionalization and doping with other element like carbon. If you dope nitrogen, phosphorus, or other element, the different properties has come into the picture. These nanoscience and nanotechnology already have been used in diagnostic, cluster treatment, and targeted drug delivery. It is used in print technology. It is used in sports industry, cosmetics, like zinc oxide nanoparticles have been used as a for sunscreen and sunblocks. And then silver nanoparticles have been used for the antibacterial socks and all other antibacterial creams and in other applications. So nanotechnology and nanoscience has already been used in fabric industry, in space, in sunscreen. So there are two type of things are there, sunscreen and sunblock. One is absorb and other one is reflect the light, UV light. So flexible electronics are the other applications of this nanoscience and nanotechnology. Then in batteries, in flexible electronics, in faster processing, in computing, all where in solar cells, even in environmental pollution and climate change. I have already told you that we have used this carbon quantum dot for the conversion of carbon dioxide into commodity chemicals, and that work has been published in Nature. So that is a very good paper of us. So it has already used in pollution degradation. People are talking to use this carbon. People have been already used to talking about this in medicines and other things. It is also have been used in clean water ultrafiltration membranes. And then the other things which I want to talk today is the alarming situation of the other side of the coin, that is the challenges with nanoscience and nanotechnology. The researcher found that in a bottled water, right now we are fond of this bottled water, plastic bottled water, either from any brand. It contains too much of plastics, and 90% of them are nanoplastics. So that is the big concern. The other concern is our brain is full of microplastic and nanoplastics. The recent study published in Nature in 2025 that by this bottled water, by blood infusion, we get these plastic inside our body. And the alarming situation is in liver, total plastic is 140, around 142 microgram per gram. Total plastic is in kidney is 538, and in brain, it's too much alarming, 3,345 microgram per gram. So that's why, even if the plastic production were suddenly stopped, it is too late. So I want to say that wherever you want to cut the use of plastic, you have to. The other thing is people are talking about the nano robot. which are used in many medicines and many other things for pollution degradation and other things. But thing is, if there is a misprogramming in their self-replicating, it can eat all the organic matter in the nature, and that is bad for our earth. So only you can prevent the grey goo. So the challenges of working at nanoscale, we all are working at nanoscience, but there is very few clean room facilities for work. People are not serious about the concern and the danger of this nanoscience and nanotechnology. So the policymakers, government, and all peoples have to think on that how to use this for the benefit of society, not for the harm for the society. There are some societal and ethical concern, like health and environmental risk. Many risks are unknown. Nanoparticle disposal is the big problem. Surveillance breach our privacy and security. Then the ethical use of these nanorobot in medicines. These are the concern with these nanoscience and nanotechnology. I am not going in detail. I am just give you the overview of these things. People are normally talking about the good thing, but no one is talking about the concern of these challenges with nanoscience and nanotechnology. Anyway, there is a bad thing, but there is a thing. There are many jobs in nanoscience and nanotechnology, but at the same time, the bad thing is in military applications, unintended consequences. So to address these consequences, it is crucial for scientists, policymakers, and the public to engage in open dialogue, establish ethical guidelines. That is most important. If no ethical guideline, then it is going to harm the society, not the benefit of the society. So now I will conclude that C.V. Raman did not set out to build a smart factory, but his invention is building the current smart factories. So smart factories are not just product of engineering, but they are the decade of advances in physics and all these things. So today's fundamental research will shape tomorrow's industry, healthcare, energy system, and sustainability. So science discovers, engineers innovate, industry transform. So that's all. Thank you.
Thank you so much, sir, for such a fascinating and thought-provoking talk. I am sure everyone found the session both insightful and inspiring. Now open the floor for a brief question and answer session. If anyone has a question, please feel free to ask. Sir, one question is from Dr. Richa Verma ma'am. Can microplastics really cross the blood-brain barrier?
Not the microplastic, but the nanoplastic.
Okay.
Yeah, sometimes people uses the bag of blood infusion bag that contains too much of plastic. There is one study said that as like the bottled water, the nanoplastic and microplastics comes when you infuse blood for any patient inside, and it goes in the bloodstream, and that way it goes to all the organs of the human.
Any question, audience? Sir, no question. Sir, I have one question. Why
Okay.
are nanometer size material important in plasmonics and photonics rather than micrometer size material?
So you are talking about the optical properties of the nanomaterials.
Right.
So when you are talking about the optical properties, as I have already showed you, that in the case of gold, whenever you change the shape and size of the material, the color change. Color change means the optical properties changed. So that way, you can make from a single material a different colored material, and different colored material, if you are saying, means it has different properties. Sometimes photoluminescent properties are also governed by this band gap. in case of semiconducting nanoparticles. So that has been already used in targeted drug delivery and diagnostics.
Thank you, sir.
And the physics behind it is the quantum confinement.
Okay. Thank you, sir. On behalf of the Department of Physics, I extend our heartfelt gratitude to Professor Dr. Ram Manohar Yadav for his enlightening and inspiring keynote address on From Fundamental Physics to Smart Factories. We sincerely appreciate the time you have taken from your busy schedule to share your valuable knowledge and experience with us. Your interaction with the audience and thoughtful response to the question made this session even more engaging. Once again, sir, thank you for your wonderful keynote address. We look forward to welcoming you again in the future and collaboration. Thank you, sir. Thank you so much.
Thank you.
Now,
Thank you, organizer, and especially Dr. Alok. I am happy to see Dr. Alok here. So,
yes,
Thank
sir.
you, sir. Yeah.
and the head of the department, Dr. Richa.
Thank you for your time,
Thank you,
sir.
sir. Thank you for sharing your valuable time, sir.
Now I would like to invite Nidhi ma'am for next session. Over to you, ma'am.
Thank you, sir. Good morning, everyone. It gives me immense pleasure to welcome our distinguished speaker, Dr. Vidya Arora, ma'am. She's working as Associate Professor in Department of Physics at Guru Nanak Dev University, Amritsar. She is an internationally renowned physicist and researcher in the field of atomic physics, quantum science, and quantum computing. She's earned a PhD in physics from the University of Delaware, USA, where her research is focused on modeling atomic systems for atomic clocks and quantum information. Dr. Arora also has worked as a PSI Fellow at the Perimeter Institute for Theoretical Physics at Waterloo, Canada, one of the world's leading centers. Being the coordinator for Center for Quantum and Material Science at Guru Nanak Dev University, she coordinates collaborative research in quantum technologies and advanced materials. Dr. Arora is also a recipient of the Young Women Scientist Award. She has selection among India's top 3 women scientists by National Academy of Sciences and secured multiple research grants from SERV, DST, and CSIR. So now, without any further delay, I invite Dr. Vidya Arora, ma'am, to deliver her expert talk. Ma'am, please take over. Over to you.
Thank you, Dr. Nidhi. And first of all, I would like to congratulate the senior leadership, including Vice Chancellor of JSS University, Dr. Mahadeva Swami, and also the head of the department, Richa Verma, for extending this invitation to talk. And I really congratulate you all, the organizing committee including, for organizing such an event, because this is the need of the hour. I think physicist, I'm a hardcore theoretical physicist working on fundamental foundational physics, but I think at the same time, our job is also to support industry. So this summit is the need of the hour, where I'm going to talk about another dual technology. So our previous speaker, Dr. Ram Manohar Yadav, he talked about the nano technology, which is a dual technology with the pros and cons, advantages, disadvantages. I'm also going to talk about another dual technology, which is the quantum technology. And with the upcoming national quantum mission announced by government, I think it's required that we support the industry as a theoretician, as an experimentalist, as an academician working in universities. So I really congratulate, and that's very thoughtful to organize such a summit. And thanks a lot to Dr. Nupur Gupta for extending this invitation. I'm really glad I can talk about my research work. And as I communicated with Dr. Gupta, she told me the audience is blend of students, researchers, and industry people. So I have tried to keep my talk that it can suit each of the audience. Hopefully they'll get something from my presentation today, a blend of basics about quantum, my research work for researchers working in this area, and then how we can collaborate with industry, or what my group is doing to support the industry working in quantum technologies. So let me share my screen, and if I can share. Okay. Application. You just need to. Yeah. So can anyone confirm if my first slide is visible?
Yes,
Yes,
sir.
sir.
All right. And I'll start with the title, which is Building Atomic Cyber Infrastructure for Quantum Computers. So as I said, I'm a theoretical physicist who's working in theoretical atomic physics calculations and also quantum foundations. And so my talk today is a science-driven cyber infrastructure, which my group is trying to develop to support upcoming quantum technologies. But before that, for the young researchers, young student in the audience, I would like to give the storyline how we came up with these quantum technologies, which we call as the Quantum Revolution 2. And before that, let me give you detail of what was Quantum Revolution 1, which we usually teach to our students in class. So it all started in late 1800s when scientists thought that we have almost figured out everything about physics and there were only a few gaps left to fill. So we had kind of figured out everything, but in the end of 19th century, new discoveries were being made, new problems emerged like the ultraviolet catastrophe, where the results could not be explained using classical physics. And unsatisfied by the results which classical explanations were giving for these strange findings or behavior of particles, physicists at that time, they developed a new system of mechanics, which was quantized, which was uncertain, and it was probabilistic. So which was popularly known as quantum mechanics. At that time, some of the physicists like Einstein was not happy with the probabilistic nature of quantum mechanics, but since then there has been debate. Anyway, so quantum mechanics emerged at that time and it addressed a very important question about the nature of light and nature of quantum particles. So in 18th century, light was thought to be just particle, but in 19th century, with some experiments like diffraction, interference, and so on, it was proven that it behaves like wave. But towards the 20th century, quantum mechanics, it gave an explanation that our photons, which are the constituent particle of light, they behave both as, they are particles, and they also have probabilistic behavior, which is like a behavior of a wave, and they can interfere like classical waves. So at that time, people thought that this is something new, which could be emergence of a new technology, new regime. And maybe I can go back and then talk about the different technologies which were being developed by these ideas which were emerging at that time. And Bell Lab in 1947, they built the first transistor using these quantum-like properties of electrons. And around the same time, people who are working in optical physics, they developed lasers, which is also relies on the quantum phenomena. So these inventions, which were based on the quantum nature of the particles, but they were supporting classical technology. So laser is a classical technology. All these inventions were termed as the Quantum Revolution 1, because these technologies, scientists were using quantum theory to build them, to explain them, but these were just practical tools for classical worlds. They were not fully exploiting the strange features of quantum mechanics like entanglement or superposition. And first quantum revolution didn't make full use of quantum mechanics, but that changed in 1860s when Dr. John Bell, he proposed a very unique, powerful idea which shook the foundations of quantum mechanics. It shook how we thought about quantum mechanics. Like, it turned out to be more weirder than we had known. He showed that entangled particles, they exhibit correlations which cannot be explained locally. So there was no local mechanism which could explain quantum entanglement. And local mechanism was something which we used to, like every interaction which is happening between particle could be explained locally. Non-locality would mean that I'm doing some experiment here and it's affecting another experiment in US or Canada. So these phenomena were not known, but when he showed that entangled particles, they were exhibit some kind of correlations which cannot be explained locally. There has to be some non-local phenomena. And in simple terms, it means that if there are two entangled particles and you measure one particle, the other particle instantaneously responds to that measurement. And it doesn't matter what is the distance between these two particles. And it was not because they were carrying some local hidden instructions from the very start, but it was because that the connection between them was fundamentally non-local in nature. So this non-locality, in quantum mechanics, it opened a number of ideas to this new field. And that's where I would term quantum revolution 2 started. Not entirely experimentally, but a lot of theoretical physicists, theoretical progress was being made, where quantum particles were being proposed to build quantum technologies. But the problem experimentally was that we didn't know how to manipulate or control these quantum particles. So with quantum particles, the problem is that they are very fragile, and even a small interaction of these particles with environment, they tend to lose their quantum nature. So we didn't know how to control these particles, how to protect them from the environment interaction, how to protect them from decohering. And in 1990, around 1990s, 1995, laser cooling and trapping of experiment won Nobel Prize, and we started to even very efficiently started to control, manipulate these atoms. And that's, I think, the mark of something called quantum revolution, where we could not only use quantum theory to build classical technologies, but we were using quantum particles, we were using their strangeness to build these technologies. So in other words, first quantum revolution gave us things like classical technologies like lasers, MRI machines, transistors. They worked on quantum rules, but they involved large number of particles. We were not working just with single quantum particle. But the second quantum revolution was different. Here we were learning to control individual quantum particles at very small scale, and we are trying to maintain the delicate quantum nature they have, like quantum entanglement and superposition. So quantum revolution is a paradigm shift where we are able to build technologies which use full potential of quantum physics. And you might have heard about all these quantum technologies like quantum computers, quantum key distribution, quantum materials, quantum annealing, and so on. So broadly, these quantum technologies are grouped into three main categories. Some people put it in four categories, like they split quantum simulations, but I keep simulation as a part of computing, but that's a personal choice. So the three main categories were quantum sensors, where these sensors could detect even tiny changes in fields or motions. And they are used in medical imaging, navigation, and also doing fundamental physics. Like these sensors could predict or are proposed to give signatures of dark matter. So there's a model where a dark matter is assumed to be a field, and since these sensors are very sensitive, they could interact with any kind of field. They could also lead to the discovery of dark matter in future. The next is the quantum communication, which uses quantum systems to send information very securely. So unlike the traditional communication which we use, which can be intercepted by anyone without you knowing that somebody is hearing your conversation, quantum cryptography makes eavesdropping detectable. So the idea is that if you send a message and somebody is trying to read it, then the message self-destructs itself. So you know that somebody is trying to eavesdrop. And the third is the quantum computers, which are like fundamentally different from classical worlds. And I'm going to talk about quantum computers more in my talk today. So briefly, I think almost everyone who has heard at least one talk on quantum computers already knows that classical computing is different from quantum computing. And classical computing, it relies on something called bits, zeros and ones, which means circuit on or off, like the switch is on or off. And each bit is always in a definite state. Either it is 0 or 1. So either the current is flowing or the current is not flowing. However, quantum computers, on the other hand, instead of working on bits, they work on something called quantum bits, which can exist in superposition. And these quantum bits, they function as two-level system. And two-level system in terms of physics means that a system where I can know everything about the system by asking one question. one yes or no question. So for example, this is a two-level system where I have a ball and a box with a partition between. And I just need to ask one question in order to know which side of the box is the ball in. I could either ask if the ball is in left. If the answer is yes, then ball would be in this basis or in this state. And if the answer to that question is no, then I would know that the state of the system is the second one. And these possibilities in which the ball can exist. So here there are two possibilities that ball can exist in. One is it could exist in the left side of the ball, and the other is it could exist on the right-hand side of the ball. So these possibilities are called the bases of the system, which mathematically we represent as a ket vector 0 and 1. Also, in order to ease out our calculations, we usually write everything in our quantum mechanics or quantum computation in terms of matrices. So for example, these bases, which are the answer to the yes or no questions, the number of possibilities a system can exist in, it can be represented as column matrices. So the 0 basis, which means the ball is in the left side, could be represented as a column matrix with 1 and 0 element. And similarly, the other basis, the 1 basis, could be represented as a column matrix with a matrix element 1 and 0. Now, there's obviously a starking difference between these quantum bits and classical bits. Quantum bits can exist in superposition. So one single ball could exist in superposition of being in the left side and the right side. And it doesn't mean that it is spread out or it is simultaneously present in both boxes. Superposition cannot be visualized classically. If I try to make you picturize superposition, it's not possible to do that. At least I can't do that. Superposition just means that it has a fixed probability of being found in the left side and the left side when I do measurement on the system. So unless I look at the system or do the measurement, it is in superposition. When I do the measurement or observe the system, I'll find that it is in box left with some probability a square or box right with some probability modulus b square. And here I would like to just make one small comment because that's important for my further slides, that one qubit can store information in two amplitudes here. So these A factors, these probabilities are called as the amplitudes of the state. So these amplitudes A and B, you can store the
I think there is some network glitch, and Dr. Vidya will be joining us shortly. I request all the participants to have patience and wait with us. So she'll be joining back. Thank you.
Okay. I'm not sure if I was able to convey what these qubits and two-level systems are.
Okay.
Yeah.
We can start. You're audible and the slides are visible.
Okay. So, Nupur, where should I start from? The qubits or the quantum basis or the phases? I don't know.
The phases.
The phases. Okay. So, with the
Okay.
yeah, just give me a second. I'm trying to. Okay. Yeah. Yeah. So, I don't know why my slides are not moving. Now they're moving.
Yeah, they're moving.
Now they're moving. So with the quantum basis, I said that these amplitudes, they give probabilities, and with quantum mechanics, these amplitudes are complex, unlike classical, where classical probabilities are just real numbers from 0 to 1. But here they could be complex as well. And this complex nature gives an extra advantage to quantum mechanics or quantum physics, which is exploited to make quantum technologies, is that they have phases. So, for example, here phases I'm describing as arrows, although again, there is no classical analogy for these quantum phases, but you can think of them like phases in waves and so on, which is an incorrect analogy, but just for the visualization. And it turns out these phases are very important when we work with the quantum algorithms, or when we are trying to build technologies or trying to explain phenomena like quantum interferences or not. If it weren't the quantum phases, then interference would have never been there. Okay, so just like classical computers, you have qubits here as the alternate of bits. And just like classical computers can do operations on these bits, like they have X gate or NOR gate or OR gate, where you do operations on these bits. Similarly, for quantum computers, you can also do operations on these qubits. For example, identity operation would mean doing nothing. If your particle is in the left, you just leave it in the left. If the particle is on the right, you just leave it in the right. You could change the phases, or you could do something like X gate does in the NOT gate does in the classical computer. You could change, like switch. If the particle is in the left, you change it, you bring it to the right, and so on. So all these operations or gates in quantum mechanics are represented as these 2x2 unitary matrices. And these are some very famous key quantum gates represented in matrix form. And one of the very important gates which is used in quantum computation is the Hadamard gate. Okay. Now, building upon this idea that you can represent qubit as superposition of the basis. Basis is the number of possibilities. You can also extend this model, like expand this to multi-qubit system. So one qubit means two possibilities. If I have two qubit system, then that would mean four possibilities. So instead of just one box and a ball, I have two boxes and two balls. And the bases, allowed bases or allowed states in which the ball can exist if I do measurement on the system would mean that the both balls are on the left side, both balls are on the right side, or one on the left, one on the right, and so on. And a two qubit system would be again represented as superposition of all these possibilities or all these bases. And again, these amplitudes here A, B, C, D are complex amplitudes, and the modulus square of these complex amplitude give the probability of finding the system in one of these bases when I do measurement. The information which I can store in this two qubit system is in four amplitudes, unlike the classical case. For classical bit, 2 bit of information means I can only 2 bit mean I can store only 2 pieces of information. But here I can store information in 4 amplitudes. And this gives the power of the quantum computers. The amount of information that a quantum computer can store raises exponentially. And it turns out that if I have 500 qubits, theoretically, it would mean amplitudes more than the estimated number of atoms in universe. So theoretically, I could store the information of the entire universe in just 500 qubits. The other advantage or power of quantum computation is the quantum parallelism, which means that, like in classical computers, most of the classical computers, the computer scientists in the audience would agree that classically we perform action in series. So it's like one-to-one action when we are doing computation. However, since for quantum computers, the state can exist in superposition of multiple choices or multiple bases, I can perform just one operation on the entire state and build something called the quantum parallelism. So it's a powerful feature of quantum mechanics where I can operate using just single operation. I don't have to use 4 different operations to operate on this state. Having said that, it doesn't mean that when I'm doing a measurement, then I would observe all the 4 outputs. I'll just observe one output. Okay. Anyways, so these are all the theoretical basics of quantum computers. Now, experimentally, there are a number of physical systems where we can realize or we can build quantum computers. Some key approaches are like liquid NMR, trapped ions, cavity QED, solid state schemes. And in India itself, the researchers in this domain are actively working on building computer. Like, for example, here is the QPI AI Indus in Bangalore. This is the Amravati in Andhra Pradesh quantum computer, which is the technology, indigenous technology India is trying to build. And by the way, this is how a quantum computer using atoms look like. So it's a big tabletop. It's not like a very small handy thing. It's a big tabletop experiment or a computer where you use lasers to manipulate atoms. So my research work is related to supporting quantum computation using trapped atoms. And it turns out that in order to build any quantum computer with any of the systems, you need to satisfy 5 criteria, which are famously known as De Vincenzo's famous computational 5 criteria. And it turns out that atoms, like neutral atoms, they perfectly satisfy these 5 criteria. For example, they are scalable. If we trap them in optical traps, we can easily initialize all the atoms. Like it's very easy to make all the atoms in ground state. And since they are neutral, they have weak coupling with the environment. So the decoherence time is very long. It doesn't decohere very easily with the environment. And then you can also build qubits with them. Like single qubit gates are well understood in atomic system using spectroscopy. The only challenge here is to find controlled interaction between 2 qubits to build a 2 qubit system. So let me explain that a little bit. And also important point which I didn't mention in the previous slide is that when we are trying to build these quantum computers using atoms, it's very necessary that we control and trap these atoms in order to reduce the decoherence. Like we don't want them to interact with the environment. If we cool them, they won't interact much with the environment. And also their motional shifts will be reduced. So they will be confined, they won't move more. It will be easier for us to manipulate selectively each atom and so on. And this is where atomic physics plays a very important role in cooling and trapping atoms. Okay, so coming back to the 2 qubit or the universal qubit. Now, the question is, in order to build any computer, you need 1 qubit gate, you need 2 qubit gates. The question is, do we need more than 2 qubit gates? And that question is same applicable for classical computation as well. But it turns out that since, as I mentioned before, these gates in quantum computation can be written as unitary matrices, and any n cross n unitary matrix can be decomposed as a sum of 1 or 2 cross 2 matrices. So all you need to build any universal quantum gate is just one qubit gate and a 1 2-qubit gate. And as I said, for atoms, building 1-qubit gate is well understood using atomic spectroscopy, which is done by single qubit rotation, like transferring electron from ground to excited, excited to ground, and so on. For 2-qubit gates, we need to build something called CNOT gate. CNOT gate is a controlled NOT gate, where you have 2 qubits here written as X and Y. One is the control, which controls if the target Y has to be flipped or not. Okay, so if the control is in 0, then the target is not flipped. It stays in the state which it is in. If it is in 0, it stays in 0. If it is in 1, it stays in 1. But if the control is in 1, then the target qubit is flipped. So if it was in 0, it is changed to 1, and if it is 1, it's changed to 0. In order to build this CNOT gate, it's very important that we are able to find an interaction between these 2 qubits. In our case, these 2 qubits are the atoms. And as I said, these neutral atoms, they don't interact. They are neutrals. They don't have Coulombic interaction between them. Whatever interaction is between them is a very small van der Waals interaction, which is not enough to build this CNOT gates. But if we excite these neutral atoms to a very highly excited state, let's say to a principal quantum number state 50D or 50P or 70S and so on, then these neutral atoms, they exhibit very unique properties which can be exploited to make these CNOT gates. And these highly excited atoms are called Rydberg atoms. So in order to build this CNOT gates using atoms, we have something called Rydberg states. And people know how to build these Rydberg gates using Rydberg gate scheme. The advantages of using Rydberg atoms is that, again, since they have been excited to a very high principal quantum number, their size is very big, and they have a very large dipole moment. And these dipole moments, so a Rydberg atom has a dipole moment, another atom has a dipole moment, and we know from elementary physics that 2 dipoles, they have strong interaction between. We can expect these strong interaction to create entanglement and build CNOT gates. So this is the Rydberg gate scheme where we exploit, where we use laser technology to build something called a CNOT gate here. Okay, I don't want to go into the details of how this works, but I'll be more than happy to explain how the Rydberg gate scheme works and how the CNOT gate is built from here. The basic principle is very simple. Like if, let's say, you have 2 atoms, 1 and 2, these are the 2 qubits. The 2 qubit states are 0 and 1. So either it could be in 0 state or it could be in 1 state. And Rydberg state is a very high excited state. For example, here it is 40P. What you can do is you can exploit a phenomena called Rydberg blockade, where if one of the atoms is excited to a Rydberg state, let's say atom 1 is excited to Rydberg state R, then it is going to inhibit the atom 2 to excite to Rydberg state R. So this is inhibited, it's not allowed. And this I would say this phenomena where one atom which is in Rydberg state doesn't allow any other atom in its vicinity to be excited to Rydberg state is called Rydberg blockade. Okay, so what is the role of atomic physics in all these building these technologies? And I'll particularly talk about my group where we do high precision atomic calculations. We need these atomic properties first to cool and trap atoms, because we can't build these technologies for now if they are not very cold. And also we need to understand these Rydberg interactions, because they are required to make a CNOT gate. Without a CNOT gate, we won't be able to build a quantum computer. And we also need to know atomic properties like lifetimes, AC polarizabilities, or autoionization rates to calculate how much the system is decohering with the environment, to calculate gates, errors, and etc. And also predict, okay, maybe instead of rubidium, if we use cesium atom, then we would be able to build a better quantum computer. So my general observation, where the idea started of building a was that we need lots and lots of data to support these quantum technologies. And usually experimentalists were contacting our theoretical group to provide us so and so atomic data to build some kind of quantum technology. So there's huge demand of data. And we need some kind of platform where the experimentalist or industry or startup, they don't need the theoretical expertise to produce that data. And even if they don't know some theoretician who's producing this data, they are able to find that data to support their experiment. So that was the general observation. And the present status is that we have number of codes available online, theoretical codes, which calculate these atomic properties. For example, for Rydberg atoms, the most popularly used one is the alkali Rydberg calculator. It's called ARC. For atomic calculations, there are number of softwares or codes available, which rely on different methods, some relativistic, some non-relativistic, and so on. The problem with these existing codes or even database, for example, NIST has a database of atomic properties. The problem was that these codes are very complex to use. They are inefficient, difficult to use, and they don't support the current growth which we are seeing in quantum technologies. Like with the advent of quantum technologies, we are needing lots and lots of data, which these old codes cannot support. They're very poorly documented. For example, if I talk about GRASP, GRASP is an atomic physics code to do calculations. There are multiple versions of GRASP. So over the years, people collaborate, they build next version. The old version gets outdated. Now you have to reinstall it, recompile it. So it's a lot of mess. Not only for experimentalists who don't have any theoretical expertise, even for theoreticians like me, it's very complicated to use these codes. So what we thought of was that we already have a lot of data. We are an atomic physics group. Can we build a platform which can support experimentalists, startups, and industry so that they can find this data with ease with just click of buttons? And at Atomic Physicists, what we do actually. So this part is to support, to show what kind of research I'm involved in with the atomic physics calculations. And atomic physicists, the goal is to solve Schrodinger equation or Dirac equation, depending on whether you need relativistic or non-relativistic results. And then using that equation, you find precise wave function. Using wave function, you calculate properties. And these properties are used to probe new physics, like as I mentioned in my first slide, search of dark matters or physics beyond standard model and so on. And in addition to that, we can also support a lot of applications. For example, these properties are used in atomic clocks, for quantum computation, for cooling trapping of atoms and so on. And it turns out that calculating these atomic properties exactly is not always possible. For exactly, I think we are able to do it for hydrogen atom, which is the smallest atom. We can do those calculations analytically, and maybe for helium or lithium at the most. So as the number of electrons increases, solving these equations exactly is not always possible. What we try to do as theoretician is we try to achieve results close to exact, if not exact. And the problem with solving these equations exactly is this term here. This is the Coulombic interaction or correlation between electrons. It's a two-body problem. So it involves R1 and R2, which means that it's very difficult to integrate or handle this in Coulombic interaction. What we do is, instead of calculating these many-body Hamiltonian electron by electron, we use a different approach, which we call as the Hartree-Fock approach. Or we could use different methods, like the teachers in the audience, they are familiar that when we teach quantum mechanics, we teach perturbation theory, we teach variational method in order to include fancy terms. So what we do is we treat this as the main Hamiltonian or unperturbed Hamiltonian and treat this non-handleable part as the perturbative potential, and then use perturbation theory to calculate, to do the calculations. And it turns out that if we calculate these perturbations up to 13 order, we get very close to experimental results. But using perturbation theory is not always possible, especially for heavier atoms, because the number of electrons is a lot in heavier atoms. And it gets very complicated to use perturbation theory. What we use instead is called a Hartree-Fock theory, which is a mean field theory. So in mean field theory, what we assume is that electron is moving independently of each other. So there is no electron-electron correlation, but each electron is moving in the average field of the nucleus. It's a very successful theory, which is not very precise, but gives us good result, gives a good ansatz for higher calculations. So what we do is, it's a self-consistent theory. We start with assuming that the potential is zero, solve the Hamiltonian, find energy wave function, and then calculate Hartree-Fock potential, and then iterate it back, keep on iterating until we get the desired precision. Any standard iteration, computational iteration theory works like this. So what we do is, in this Hartree-Fock, the version which we use is called the Dirac-Hartree-Fock theory, because we want to do relativistic calculations. And in this Dirac-Hartree-Fock theory, the complete wave function is represented as the Slater determinant of independent orbitals, standard quantum mechanics. And each of these independent orbitals for one electron is a Dirac orbital with a large and a small p component. So it turns out that when we use Dirac-Hartree-Fock theory, a lot of correlations they get missing, because it's just an approximate method. It won't give you like very accurate result. So beyond Dirac-Hartree-Fock, in order to include the missing correlations or missing interactions in our picture, we use something called post-Hartree-Fock method, like configuration interaction couple cluster. In our group, we use couple cluster method, and couple cluster method is nothing but it's kind of an excitation method where we start with the Dirac-Hartree-Fock wave function and then say that this wave function is the lowest order wave function, and we can excite them by these excitation operators. In our group, we use something called linearized couple cluster. And maybe I can skip all the technical part, but the main idea is as follows. We can solve the Dirac equation or the Schrodinger equation to a very high precision to obtain these wave functions. And once we have these wave functions, we can calculate any atomic property, any transition property of the system, because these transition properties are nothing but matrix element of the operator of the desired wave function, or of the desired property. For example, if I want to calculate the dipole matrix elements, this operator here is just the dipole operator and so on. Okay, so we have a large database of atomic properties, and I'm building a very big, like I'm working in collaboration with the team at University of Delaware to build an atomic data portal where we are giving atomic properties like matrix elements, transition rate probabilities for a number of atoms. But this is a static website, and it has, this is a standard portal access that we have had about 4,500 total sessions so far, starting from 2022 when it was launched. And each visit has led to a download. For example, there are 15,000 downloads of the data so far. There are 7,800 total users. So the web portal, which I'm involved in collaboration with the team of University of Delaware, is just static. So you have properties which are on the website. You click on the property, download it, use it. You have CSV as well if you want to use it for computational purpose. What in our group we are building is something called the Rydberg Atomic Physics Package, where we are trying to build a graphical interface software, user interface, where experimentalists, they give just very small input that they want so and so property for so and so element in so and so state, and after running, the output is in a graphical user interface friendly form. So you don't need any computational expertise to do that. And we are building this package on various methods. So we are not just using one specific method. Since we have expertise in atomic physics calculations, we know how to use these different methods. We are using a number of different methods and trying to compare like which method gives what kind of result, and then use the best result in our calculations. So the goal is that we evaluate these atomic properties, and then On the way, since we are theoretician, we can't stop doing fundamental physics. We are also trying to develop new methodologies where we can improve our calculations. And in the end, the major goal is to build a cyber infrastructure where we have a user-friendly and a versatile relativistic program for high-quality atomic data. The innovative part is that the infrastructure is built for and with the community, so it's a collaborative. We plan to have a feedback form where people can give feedback that we need data for this, or maybe change this in your code or something like that. It would be readily usable, accessible to not only atomic physics community, but to startups as well, which do not have any contact in the research community. It will require minimum knowledge of coding. So you just apply a few parameters to describe your result and get the output. This is the workflow. So we have divided into 3 layers. One is the input, the computational engine, and the output. I really want to describe it, but I see it's 11:30 already. So I'll glimpse through what are the methodology or technical details of the portal. But we use different methods, like the finite difference method. Finite difference method is solving the differential equation exactly. And the basis function method, where you try to solve it numerically. And we have provision right now. It's in, like, we are building it, and we have a provision of using finite difference method and also the basis function method. For basis function methods, we are using two different bases, the Gaussian type orbital the portal has a nice provision of checking before producing your result. You can check if the wave function, the equation which you have solved, does it produce a reliable wave function for the properties to be calculated. So you could check what happens if I increase the number of bases, what happens if I increase the radius, and so on. And also has provision of something called removing spurious states, which is more technical and I think not suitable for the present audience. So we can use different balance conditions to remove these spurious states from our spectra. And for Rydberg atoms, we have a different methodology of using model potential to do these calculations. So this is the interface, which is not running right now. There's like, I cannot show it real time how it works, but it's very user friendly. You just give few parameters, only these 3 parameters here, and just click on run. It gives you output. The output is at the Hartree-Fock level. You download that output and then put that output in the, if you want to do like post Hartree-Fock calculations like couple cluster and so on, you can also produce very high precise calculations in it. So in the end, I would just like to advertise the Center for Quantum and Material Science at GNDU, and I think I'll be happy with any industry who wants to contact us, because one of the main agendas of the center is to train our students for these upcoming quantum technologies. With that, I would like to end and acknowledge all my collaborators and all my students who are working in that's supporting the work. Thanks a lot.
Thank you, ma'am, for your presentation. Now the floor is open for questions. Participants, if you have any questions or would like to seek any insights on any topic, you can ask the speaker. Ma'am, some questions are there in the chat box. One participant is asking the question.
Yeah, I'll go.
Ma'am, one participant is asking the question that these days it is being heard that very soon quantum computing will take over AI. How far is it true?
So this is mostly hype right now, and this is one of the areas where our center is also working. It's called responsible quantum technology. So it's as I said in my first slide, quantum technology is a dual technology. We need to be very mindful and thoughtful while we are using it and while we are propagating it. It's very much easier for us to get grants by making big claims that quantum is going to overcome it's a threat to cryptography, it's a threat to our secure communication, quantum is going to soon take over AI and so on. But these are right now not true statements because we are still building them. The technology has picked up a lot of pace, no doubt. We were expecting that we are going to build these technologies in 10 years, but the pace has picked up and we are seeing developments in few years only. But right now, I don't think it's going to take AI. What I can comment is that AI and quantum computation or computing joined together will be revolutionary.
Okay, now one more question is there in the chat box. Why do quantum physicists investigate whether quantum mechanics can be written only using real numbers? Can iota be removed, or it is just hidden under mathematical structure? So
It's hidden under the mathematical structure, but yeah. So even in our group, we were trying to find a way. So remember, for other audience, the question is, why do we need those complex amplitudes, which I mentioned in my slide? Why do we need? Can we do quantum mechanics without introducing those complex amplitudes, which have iota in them? So yes, there has been a recent paper, I think this month, where physicists have tried to find a new way of doing quantum physics without introducing imaginary particles, just by real numbers. But it's very complicated. I haven't read the paper in depth, but just from the glimpse, what I understood was for each state, they have a flag on it so it kind of it's hard to explain in very basic language, but it's a very complicated theory, not as easy as using quantum mechanics. And I think iota can be genuinely removed. Right now, if we are trying to remove iota, the theory is becoming very complex, which is not appropriate at the student level. So maybe at the researcher level, but it's not adding something new to the physics. Whatever physics we are doing with iota is simpler. We can do with avoiding iota, which will be very complex. So I don't see any advantage of using a complex theory which doesn't add up to anything, except for our fundamental understanding, which I support a lot. Rydberg atom cooling, what type of cooling mechanism is used in? So I am a hardcore theoretical physicist. I don't touch any experimental instruments except for small lasers, which I use for science outreach. But usually the experimentalists who are working on cooling atoms, they cool using lasers. So ideally, what you do classically, you'll think, okay, if I'm shining laser on something, that object should heat up. For atoms, what happens when you shine laser on them, they cool. And the phenomena is the Doppler shifting and the momentum loss of the system. You can read more about it. So everybody is using lasers to cool these atoms. How real qubits made? Okay. So real qubits are nothing for different proposals. As I mentioned in my slide, that there are different proposals to build these quantum computers in reality. For example, some people use ions, some people use atoms, some people use NMR techniques. For atoms, these qubits are nothing but single atom. So if I can go back to my slide, where I introduced, let me share again and go to that slide. Just give me 1 second. Yeah, okay. Let me share my slide again. So I don't know how familiar you are with atoms, but this is a schematic of a Rydberg atom. The ground state of rubidium atom is 5s half, and the nuclear spin for rubidium is 3 half. So this leads to a hyperfine splitting in the rubidium atom. This 5s level splits into 2 hyperfine levels, F is equal to 1 and 2. And this F is equal to 1 is the ground state of the system, and F is equal to the excited state of the Rydberg atom system. Qubits are realized by this single atom where zero state, remember I mentioned these possibilities, these bases. So 0 bases is given by this ground state, and 1 is given by this F is equal to 2. So all you need to do, for example, if I want to build a 1 qubit gate out of the 5s, let's say I want to build a X gate. X gate is nothing but transferring 0 to 1 and 1 to 0. So all I'll do is I'll shine laser on atom which is in 0 state, and you know that laser can excite the electron from ground to excited, and I can do that excitation. That would be 1 qubit. Very, very simple terms. It's like more complex to what I explained, but in simple terms, these atoms are your qubits.
Thank you so much, ma'am. So on behalf of Department of Physics, I would like to thank Dr. Vidya Arora, ma'am, for her inspiring talk. Your talk was fascinating and emerging field has given us a deep understanding of how atomic scale are shaping the future of quantum computing. We truly appreciate the time, knowledge, and the valuable insights shared with us. So, on behalf of every present here, I extend my sincere appreciation and wish you continued excellence in all the future endeavors. So, once again, thank you so much, ma'am.
Thank you, ma'am.
Uh, Now I hand over the talk session to Dr. Alok Singh. Alok sir.
Thank you, ma'am. Thank you, ma'am. Good morning, everyone. I am Dr. Alok Singh, Assistant Professor, Department of Physics, JSS, University Noida. It is my privilege to introduce Professor Manmohan Singh Sisodia, Dean Student Affairs and Professor in Department of Applied Physics at Gautam Buddha University, Greater Noida. Professor Sisodia sir earned his PhD from IIT Delhi and completed prestigious postdoctoral fellowship at Georgia State, USA, and Tel Aviv University, Israel. With over 20 years of teaching and research experience, he made a significant contribution to photonics, nanoplasmonics, thin film, and computational physics. He has published more than 50 research papers and successfully supervised several PhD research scholars. Today, he will deliver a talk on light-driven manufacturing, the role of photonics in smart factories. Sir, please join me with warmly welcoming Professor Manmohan Singh Sisodia. Sir, please. Sir, slide is visible.
Good morning, everybody.
Good morning, sir.
Good morning, sir. Good morning, sir.
Good morning, sir.
Good morning,
First
sir.
of all, I would like to congratulate the leadership of JSS University for organizing this event. And also, I would like to thank Department of Physics for inviting me, for giving me the opportunity to deliver a talk on light-driven manufacturing, the role of photonics in smart factories. I can see so many known faces, and the work that I'm going to present or talk, some experts are also sitting there, and it is part of their contribution, so they can also intervene in between. Thank you, Dr. Alok Singh. Thank you, Dr. Pratima Rajput, for your contribution during your PhD and later on. So I will speak about the role of photonics in smart factories and little bit about the basics of photonics, what we do presently and what we did, let us say, few years back. इसको कर दीजिए F5. Presentation mode. Okay. So when we talk about the photonics, I'm sure that most of us are aware about the light and then the photons and then the science and technology dealing with the photons, what we call as the photonics. In short, photonics is nothing but the science and technology of generating, controlling, and detecting the light. It enables communication, sensing, manufacturing, and there are so many technologies which are outcome or let us say based on photonics. Most of us are already aware. For example, lasers, LEDs, detectors, optical fibers, cameras, spectroscopy, and so many type of sensors are possible due to the advancement in the photonic technology. इसको ना sorting करना present नहीं ये कभी इसको फिर ऐसे करना Okay. Because your topic is based on the industry, and when we talk about the evolution of the industry, we know it all started with the discovery of steam. So industry 1.0, it was based on steam, then industry 2.0, it was based on the electricity, industry 3.0. All of us are aware that electronics and then standard computers, they were the backbone of industry 3.0. But now industry 4.0, where we think about the fusion of physical and digital worlds. So, like how photonics is going to contribute in this era of industry 4.0. What we can see that when we talk about the electronics, obviously it could reduce the size of the systems and the devices, but the speed remained low for digital processing. And photonics, it played a better role where the speed of processing is enhanced so many times. And also, if we talk about the basic photonics, then the size of devices, it remains quite large. But again, due to the utilization of advancements in photonics, we can call that plasmonics, several better features in photonics have been obtained. For example, light can be confined at nanoscale. Through field enhancement, several optical phenomena, optical effects can be improved, and photonics and electronics, they can be merged together. The important idea is that electronics components, they have been reduced to very small size, obviously due by virtue of very small transistors and very small ICs. But due to the limitation on the wavelength or the size of the optical components due to the diffraction effects, the size of optical components and optical devices, it has always been a bottleneck. But again, the advanced technology, advanced photonics technologies, including plasmonics, that is being used for reducing the size of optical components as well. So it is now becoming feasible to merge photonics and electronics at the same level. Efficient molecular energy transfer, light energy harvesting, so many applications now the photonics is playing. And now, when we talk about the photonics, we look at the electromagnetic spectrum. Being physics students, all of us are aware that it has a long range of wavelength or frequencies or energies. In one side, we have, let us say, X-rays and gamma rays. On the other side, we have, let us say, sound waves. In fact, we have radio waves. And the large region between the radio waves and X-rays and gamma rays, then there is a small range of visible spectra. Close to that spectra, we have UV spectra on one side and infrared and terahertz on another side. And this is perhaps the most important part of the spectra from the photonics point of view. We talk about like UV part, the visible part, and let us say infrared or terahertz part. That is very, very important from photonics point of view, where photonics has contributed a lot, and still it has a great potential of contributing and making basically the making contribution in the development of the world. If we look at the photonics overview, I already talked about the photonics. So The first thing is light. How to produce light, that means light generation. Then light manipulation, light transmission, light detection, and the integration. The important part of photonic spectrum, which I spoke, like UV, visible, near infrared, mid infrared, far infrared, and terahertz. The use of this spectra, it has made so many applications viable and feasible, which includes lasers, optical fibers. Then there are so many optical components and meta surfaces, optical sensors, optical imaging and spectroscopy, and then light modulation tools and quantum photonics. So, photonics is currently playing the role in so many crucial areas, including optical communication. Obviously, it has so many applications in defense, security, by virtue of its high speed and bandwidth, the precision and accuracy which light supported of the photonic systems they will have, the energy efficiency, how photonics can help in developing sensors, or let us say solar cells or the modulators, then enabling future technologies, and it has reliability from the industry point of view due to the minimum of EMI, the electromagnetic interference. In smart factories like real-time monitoring, high-speed optical communication, obviously most of the communication earlier, it was based on electronics, but due to the demand or due to the increased traffic at an exponential rate, the electronics and electronic systems, they cannot cope with the requirement of the communication and the photonics, where the wavelength is almost 4 orders of magnitude greater. That is why the bandwidth of optical communication systems, it is more than 4 orders of magnitude, 4 to 5 orders of magnitude higher. And this frequency, it gives rise to a large bandwidth, which is able to tackle the amount of traffic that is exponentially growing. So photonics is playing a crucial role in optical communication, precision measurement, automation and quality control, and predictive maintenance. If we look at the slides, see, ultimately, the pillars of Industry 4.0, all of us are aware that the trends in industry are evolving. In fact, I would say, again, at a very fast pace. It requires connectivity, it requires capability for data analysis, automation, digital twin, and cyber security. So, the smart factory, obviously, it will have everything connected together, where the conventional devices, conventional systems, they are networked with the new technologies. Whether we talk about the cyber security, we take advantage of artificial intelligence, we take advantage of machine learning, so that the human intervention is minimized, and the speed and the amount of information that can be processed, the or the amount of information, important information that can be generated or that can be transmitted, that can be enhanced substantially in Industry 4.0, because the aim of this revolution, ultimately, it requires minimization of human intervention and being at the core, the digital revolution. Focus on digital revolution for the betterment or for the facilities for the humanity. Optical sensing and metrology, I will talk in detail somewhere else. When we talk about laser-based manufacturing, so laser, a very important tool, which is very much used in the industries for laser cutting, for laser welding, for laser drilling, laser surface treatment. And not only that, laser is in fact at the heart of the optical communication. When we talk about optical communication system, it consists of mainly three parts. It is basically a source, an optical source. Optical source is mainly a laser or an LED. Then we have transmitter, which is normally an optical fiber, and then a receiver, that means an optical detector. So laser working in different wavelength ranges. Lasers of, let us say, varying size, lasers of varying power. They are very much required. For example, for space missions, laser is a crucial instrument or a crucial device. For defense, laser is a crucial device. For welding, for drilling, for nano-level drilling, laser is a crucial device. Not only that, for 3D printing also, the laser is playing an important role. For optical sensors and metrology, fiber optic sensors are there based on interference, then 3D scanning, non-contact dimensional measurement, temperature and strain monitoring, high-speed cameras, so many applications for defect detection, deep learning inspection, robotic guidance, and inline quality assurance. What are the benefits and what are the challenges? Compared to electronic technology or compared to electronics, few things I already discussed, that electronics cannot cope with the amount of information that is being generated and that need to be processed. So photonics is an answer to that. And photonics is successfully implementing the idea of communication throughout the world, communication to all, communication everywhere, at reduced cost, in reduced time. And photonics technologies, they are highly contributing in reducing the waste, in energy efficient devices. I will talk about few of them. And obviously, the in challenges, high initial investment and skilled workforce, these are few challenges which we need to address. When we talk about the optical effects or the photonic effects, the light, it has different facets. Like if you look at this Likert cup, if we see the cup in the reflected light, then the color will be different. And if we see this cup from the transmitted light, the colors will be different. So light, how it is manipulated, how it is transmitted, how it is observed, it plays an important role. And nitty-gritties of light, they can be utilized for making the humanity basically far better than what it is today. Okay. If we talk about the Raman effect, obviously most of us are aware about the Raman effect, but detection of only a few number of molecules has been always a challenge. That means finding out that which molecule is present in the sample. Raman effect is an important tool, but it requires a sufficient number of molecules in the conventional Raman effect. A sufficient number of molecules, that means a sufficient sample size is required. How photonics has further improved it. Photonics has largely improved the Raman signal, that is due to the surface enhanced scattering, which has increased basically the intensity of the Raman signal. And this intensity of the Raman signal can be enhanced up to an extent where a single molecule can be detected. That means a trace of molecules, they can be detected, and this application, it has again so many avenues in defense, in safety, in security, in material science, in communication, and in several other areas, including food quality analysis, cancer treatment, forensic, and drug discovery. So the photonics, the important contribution of photonics is that it has largely improved the performance of conventional systems, conventional devices, and also the conventional systems designed for micron level technologies. Now, with the help of plasmonics and similar technologies, photonics can be operated at nanoscale also. Like photonics can be utilized for harnessing the solar energy by using the concept of plasmonics, where nanoparticles, particularly metallic nanoparticles, they can largely improve the light collection efficiency of systems. All of us are aware that for a solar cell, the primary requirement is that the light that falls on the system, the maximum of this gets absorbed. In fact, not only the light falling on the system or on the surface, but the light that is in the nearby region of the system. If our system can collect light like a funnel from a large area, then more light collection, it will result in higher current production and obviously a better solar cell. The concept of light scattering assisted by plasmonic nanoparticles is playing an extraordinary important role in enhancing the property of photovoltaic system, in enhancing the efficiency, and also in producing the solar cells of nano dimensions. So many motivations for photonics-based photovoltaic systems. Like solar photovoltaic systems, they can reduce the cost maybe by a factor of 2 to 5 as compared to what the cost was almost 10 to 15 years back. Also, 90% of solar cells based on crystalline silicon wafer, but the 40% of the cost of the cell is for the cost of wafer. By reducing the size, by reducing the requirement of the thickness of the semiconductor by utilizing photonic scattering, the cost of the solar cell can be reduced by 40 to 50%. The need of thin film-based solar cells is currently of great interest, but due to less absorbing power of these cells, alternate light trapping mechanisms are required. So, solution to increase light trapping in thin film, as I already said, that first thing is that we reduce the thickness of the film, and secondly, in addition to the film, if we also use plasmonic nanoparticles, then the light absorption capacity of the system, it will increase drastically, and this enhanced absorption, it will obviously reduce the cost significantly, and this is what is required for the industry. Then photonic is playing a very crucial role in the area of sensing. When we talk about the sensing, again, sensing of so many types. The important one is basically molecular sensing. I already talked about sensing or the detection of a single molecule. Professor M.I. Stockman of Georgia State University, United States of America, he gave the idea that nanoparticle-based photonic sensing, it can enhance the sensing up to an extent that you will not require a very large sample size. That means even if there are only few molecules, in fact, the attempts are being made for a single molecule, that even a single molecule can be detected. That is of utmost importance for the industry also, that impurities of very small amount, impurities of very small magnitude, they can also be detected. In the applications of photonics, we can see like medical diagnostics. I will talk about some of the applications in medical diagnostics, imaging, glucose monitoring. In fact, Dr. Alok Kumar, he has already done a lot of work on glucose monitoring, then environmental monitoring, disease detection, chemical sensing. There are so many areas where photonic sensing is greatly contributing, or it is showing a futuristic potential where sensing can be done on the basis of photonics. And one idea, it was given by Dr. Naomi Halas, Professor of Electrical and Computer Engineering at Rice University, United States of America. The idea is that how photonics can be used. Photonics, along with the applications of nanoparticles, can be utilized for improving the cancer treatment. You can see some of the pictures from her papers, that wherever the cancer is detected, we can use photonic system where with the help of nanoparticles, the particles can be in fact injected there at that point where the cancerous cells are there. The experiments have been performed on animals. Very good results, they have been reported, and the trials, human trials, they are in process. I think it will be a great boon to the humanity if photonics-based cancer treatment, it can be materialized in the hospitals in the reality. A very important subject, which is definitely part of the photonics, where surface plasmons, they can be produced where metal dielectric interfaces are there. Without going into much details, the only thing that I would like to share is that surface plasmons, these are quasi-particles, and they are hybrid particle of, let us say, electron and photon. And these are nothing but the quanta of collective oscillations of electrons at the metal dielectric interface. And these surface plasmons and the technologies based on surface plasmons, or let us say we call that plasmonics, it has in fact increased the applications of photonics significantly. Without going into much details, these photonic technologies, as I already talked about few, are being used for solar cell, for enhancing the reaction rate in the chemical reactions, the sensitivity and the detectivity of devices, for example, solar cells, photodetectors, LED and laser, the efficiency of LED and laser can significantly be improved. And the energy transfer rate, Dr. Pratima is there, who has worked a lot on the aspect of energy transfer based on FRET, or the Foster resonance energy transfer. Photonics is able to increase this energy transfer. Photosynthesis is in fact one such real example where the energy transfer between molecules can be significantly enhanced, and devices can be made based on them for the applications, again, in solar cells, in detectors, modulators, and many more. These are some of the calculations we did without going into much details. The only thing I would like to share is that what we do theoretical modeling based on Maxwell equations, where full wave equations are solved for plasmonic system or the photonic system, that how light interact with metallic systems. Metallic systems can be of spherical symmetry, in fact, or can be other types of systems also, nanoflowers, nanopods, so many types of particles. We did some work on different particles having spherical symmetry. You can see simple nanosphere, then core cell nanoparticle, then multi-core cell nanoparticles. And by using our theoretical approach, we were able to show that core cell nanoparticles and double core cell nanoparticles, they can effectively be used for increasing or enhancing the energy transfer, for increasing or enhancing the optical phenomena or optical effects like absorption, like reflection, like transmission, and obviously many more effects based on such particles. The effects which we measured, which we analyzed, or the ideas which we generated from our work, we worked on applying those ideas for sensing, for detection. And Alok applied this work, that how the outcome of this work can be utilized for medical applications. How, without, let us say, using the needles and the syringes, can we use optical system, the photonic systems, to measure the glucose, to measure, let us say, other important parts, other vitals of blood samples, so that without any injection, without piercing any injection, can we have the idea of this medical diagnostic based on this? And we already talked about scattering based light trapping. Pratima, you can tell me when the time is about to finish. I talked about solar photovoltaics, and in fact, this work, which we did at Georgia State University, what I would like to add that simple photodetectors, let us say, in the visible region, or let us say in near infrared region, based on semiconductors like gallium arsenide and aluminum gallium arsenide, what we did, these systems, they were having a particular sensitivity and, let us say, detectivity. But when we applied photonic interaction through plasmonic system as, let us say, Bragg reflector, you can see there is a Bragg reflector, or what you can call, let us say, simply a grating. The detectivity and sensitivity of such systems, it was enhanced significantly. We did theoretical calculations, and later on, experiments were performed by the group, and the significant enhancement in consonance with the theoretical predictions, they were observed at Georgia State University in Atlanta. These are some of the pictures from that group. And so basically what we do, that how nanoparticle systems, how the capabilities, how the applications of nanosystems can be enhanced further with the help of photonic intervention, with the help of plasmonic intervention, and a very basic physics. It states that light matter interaction can be significantly improved by incorporating photonic effects, and that improved enhancement in electric field or electric field intensity, in fact, that is at the core of so many benefits which we are harnessing from the photonic systems, or the community will be harnessing in the future. And these are some mathematical steps, starting from Laplace equation, solving those equations for a single particle. So these are some simple calculations where electric field enhancement in the tune of maybe around 100 can be observed for a simple gold or silver nanoparticle. Obviously, these are very straightforward and simple calculations. Other combinations of nanoparticles where dimers or trimers and other combinations, they will obviously produce electric field enhancement of greater amplitude, and obviously they will have the capability of improving the performance of devices significantly. For JSS University, two of the faculty members, those who did such calculations, those who are expert of such calculations, obviously they have this idea, and they can in fact teach all these ideas in the class also, in their group also. So again, this is continuation of those calculations for core cell nanoparticle. And then dimer, let us say we have combination of two particles, and in fact there is no limit. There can be combination of any number of particles which can be dealt theoretically, and when theoretical calculations become very tough, then there are commercial software also which can be utilized for more efficient or more fast calculations. And it is the hybridization effect that in fact explains all enhancement, whatever combination of nanoparticle systems is used, that can be used to predict that how much enhancement is going to take place. Without going into much details, again, the basics, let me only the explanation to one result is that how scattering efficiency or scattering cross-section, these are scattering efficiencies. What we have shown in our work that scattering of radiation can be significantly improved by incorporating photonic systems or the plasmonic systems. We can see that efficiency, quantum efficiency or scattering efficiency, it is increased significantly. Moreover, we also contributed that how to decrease the line width of the emission or the scattering. Because for sensing purpose, what we require, the scattering efficiency to be more and the line width as small as possible. Both things contributes theoretically to a better sensitivity, to a better detectivity, and in our calculations, we can see that full width at half maximum was decreased significantly by using different approaches, which includes basically incorporating gain, etc. So I think 12, 15 was the limit. So let me cut everything short. What I can tell you that during his PhD, Alok developed, in fact, a software that is very handy, which we started naming as Nanosensor Lab. And Nanosensor Lab, which works on the idea of calculation of scattering based on Mie-scattering theory. The whole system, it has basically the process of solving Mie-scattering equations, where scattering can be calculated and systems can be designed, sensors can be designed. And that software can be utilized for educational purpose, for research purpose, and obviously it can be, in fact, modernized more, and it can be made available to a broader community also. So let me, I think, so many things we did, and idea was that by incorporating photonic concepts, by incorporating optical concepts, how the devices can be improved, how the application can be extended to the medical side, to the industry side, to the food side, and so on. So all these results which were published few years back. So let me not go into the details. The idea was that for medical diagnostic, like Alok did very nice calculations that how blood and let us say the sugar and such things can be, how the detectivity of the sensitivity of such things can be improved significantly, and how our software nanosensor, it can be utilized for designing such systems for medical purpose, for the industry purpose. And so many things, so many ideas, including the phonoresonance, idea of the phonoresonance, plasmonic switching, and these are क्या हुआ जरा क्या हुआ हाँ so these are some of the contributors you can see on the screen, and in fact there are many more who contributed this knowledge. I again thank you, the leadership of JSS University, the leadership of Department of Physics, Dr. Richa Verma ji, Dr. Pratima Rajput, Dr. Alok Kumar Singh, and their team that you invited me and I could share few things with you. And in future, if there will be an opportunity, I think we will have chance to discuss all these things in detail. Thank you so much.
So thank you very much, sir, for enlightening and inspiring talk. And if any questions, please, anybody can ask. So we have some question in chat box from Rajesh Chaurasia, sir. Do we study X-ray for photonics applications? X-ray are highly energetic, and does it help using for some special applications?
As far as our regime is concerned, we focus ourselves. In fact, most of the photonics, as I discussed in the beginning, that at one end there are like terahertz waves, or let us say terahertz system, and on another side we have UV. So from UV to terahertz is at our target, is mostly at the target of photonics community.
One more question. We study X-ray for, can you explain how diffraction limit is overcome in plasmonic photonics application?
Yes. When light-matter interaction takes place, as I told, that at the metal dielectric interface, what happens, a new hybrid particle, which we call, let us say, plasmon or surface plasmon, which is generated with the interaction of oscillating electrons. So this is basically a hybrid particle of photon and electron. And this particle, what happens is that the surface plasmon, the frequency, the wavelength of surface plasmons is significantly reduced with respect to what the wavelength of light was. So it is the effect of light matter interaction, the surface plasmons which are generated. So the surface plasmon wavelength will be very, very small as compared to the wavelength of light. And obviously, the diffraction effects, they are applicable on the wavelength. So since effective wavelength is reduced by virtue of surface plasmons, that is why diffraction effects are managed.
One more question. Among the various solar cells, such as DSSC, perovskite solar cell, silicon solar cell, organic solar cell, which have been found to be benefit the most from nanoparticle enhancement?
Let me not comment on all types of solar cells. What I am trying to tell that efficiency of solar cells, for example, thin film solar cells, and also in fact perovskite solar cells, there have been so many publications that their efficiency has been greatly enhanced by incorporating plasmonic nanoparticles, and I already discussed the case of thin film based solar cells. So photonics or the effects which I have talked, see, these are the effects which works as added effects. So obviously thin film solar cells were already there, but what to do to increase the performance of solar cells? And plasmonic nanoparticles, they provided, let us say, one way of enhancing their efficiency. And it can be utilized in different types of solar cells, be it perovskite, be it thin film, or be it other types also.
One more question from Rajesh Churasia, sir. We have much smaller particle than electron like quarks. Are they also candidate for quantum phenomena just like electrons qubitting?
I have not reached at that level, and see, whatever our study is, I think I should have cleared that before, that our study, it is mostly within the regime of Maxwell equations or the domain of Maxwell equations. We, in our study, we did not incorporate quantum effects. Yes, quantum effects are being incorporated, and there is totally a new area of quantum photonics or quantum plasmonics. So definitely all these things can be done.
Thank you, sir. Any questions from audience? If there are no further questions, sir, one question from my side. Sir, with the rapid integration of AI and photonics in Industry 4.0, what key skills should students and young researchers develop today to contribute effectively to the future of smart manufacturing?
See, I think obviously how optics or let us say photonics is going to contribute in the area of, let us say, communication, like quantum communication. Three important things, obviously, most of us know: quantum communication, quantum materials, and quantum sensing. These three things, obviously, are very important. If we can equip ourselves with all these technologies, obviously, quantum sensing, quantum communication, one can be fluent, one can understand them, obviously, when he or she is clear about the concept of photonics. That means all these ideas are feasible only with the help of photonics, and obviously qubit system and all these things, basically, they are largely based on approach of photonics these days.
Thank you, sir. Thank you so much for your valuable insight into photonics and its transformative role in Industry 4.0 have greatly enriched our understanding and is inspired everyone present. And thank you, sir, for your time. Thank you so much, sir.
Once again, thank you all.
Thank you. Thank you. Now over to Pankaj, sir.
Just
Manmohan sir, thank you sir for your inspiring talk. I feel truly fortunate to have you as my supervisor. Your guidance, encouragement, and unwavering support continue to shape my academic journey. It is always a privilege to learn from you. Thank you very much, sir.
Am I audible?
Yes.
Yes,
Okay.
sir.
Okay, now we invite the next eminent speaker, Dr. Alok Singh. It is my privilege to introduce our distinguished speaker, Dr. Alok Singh. Dr. Alok Singh, PhD degree recipient from IIT Delhi, and has made significant contribution to research through numerous publications and patents in the field of renewable energy and engineering. He is currently serving as Associate Professor and Principal in the Department of Renewable Energy Engineering at the College of Agriculture Engineering, Navsari Agriculture University, Gujarat. Dr. Singh has extensive expertise in renewable energy systems, precision agriculture, smart technologies, and sustainable engineering. His work focusing on integrating advanced technologies to address real-world challenges in agriculture and clean energy. Today, he will deliver an insightful talk on the theme AI plus engineering, physics. Engineering the intelligent factory with a special focus on transforming the agriculture and renewable energy sector through Industry 4.0 technologies. His session will explore how artificial intelligence, IoT, automation, digital twins, robotics, and data-driven decision-making are revolutionizing modern agriculture and renewable energy systems, paving the way of smarter, more sustainable industries. Now I invite Dr. Singh. Over to you, sir.
Good afternoon, sir. Good afternoon to all of you. Good afternoon to organizers, participants, and all the dignitaries today. Today, as told by the sir, that I am going to present give my talk on the interventions of IoT and AI for the agricultural, especially focusing on the based on the agriculture engineering for the agriculture, and which will also be mixed with the renewable energy sources. So, should I present?
Yes.
Is it visible?
Yes, sir.
Okay.
इसको लगा रही हूँ ना, इसमें ब्रेकेज आ रही है, इसमें नहीं सुनाई दे रहा, इसमें
Is presentation visible on the screen?
Yes, sir.
Okay, okay. Yes. So the topic is transforming the agriculture and renewable energy sector through the Industry 4.0. Myself, Dr. Alok Singh, working at the Department of Renewable Energy Engineering at Navsari Agricultural University. So, first of all, what we think, if we talk about the AI and machine learning, what thought comes in our mind? Mostly people think that how AI can be associated with the agriculture. And if we talk about the AI, first thought which comes in our mind is someone may be thinking about the self-driving cars on the road. Some may be thinking about the smartphones, chatbots, etc. But in real, this AI can also be integrated with the agriculture. Few decades ago, agriculture was adopted to be the things for the very rural people, farmers, which stay in the rural areas. But now the things have changed due to this intervention of AI, artificial intelligence, and machine learning, etc. Now, agriculture has not remained the boring thing as it used to be earlier. Now, we can utilize all the modern technologies in agriculture also. So, this is the evolution of the agriculture from agriculture 1.0 to agriculture 5.0, which is to be predicted for the future generation. So, how it was evolved from agriculture 1? Earlier, hundreds of years ago, the farming was done, agriculture operations were done by the manual methods. Manual labor was used, human intervention was there, animal power was used, basic hand tools like khurpi and plow were used. and especially the powering agent to these all the things was muscle and sweat, muscle power of human beings and muscle power of the animals. Then the agricultural things were moved to the next step, and it was mechanization era when the things were mechanized. What was mechanized? What was the benefit of mechanization? Mechanization increased the productivity in the lesser time, but the machines were again dumb. Those machines were not having any type of intelligence. So our time was reduced with the increase in the productivity, but again, it was not smart agriculture. And that era was called the machine age. Next, we moved to the precision agriculture, in which we adopted GPS system, GIS mapping, and basic automations. That is called computer age. So we are at this time, we are at the mix of agriculture 3.0 and agriculture 4.0. So this time we are using GPS for defining the area of our field. We are using the GIS techniques, and we are using the drones for mapping the area. So many things are being used at present, which comes under agriculture 3.0. And we have moved toward the precision agriculture, where the resources are used very precisely for the agricultural operations. Next, which is at the current time, agriculture 4.2, where we are using data-driven farming, in which we use Internet of Things like sensors. We are using cloud computing, AI, and big data analysis. This is the smart era. And what next is expected, that the agricultural operations will be completely automatic, where the robots will be used, and they just need to be controlled. They will do the things using their intelligence itself. There will be self-sustained robots. So this is the expectation in the future in agriculture 5.0. Yes. So the next one is agro-energy nexus. How there is synergy between the agriculture and energy. As we know that we cannot think of the agriculture's food security without the energy security. It means we can say that agriculture and energy both are locked to each other. Agriculture and energy both are locked to each other. If we say that we are achieving the energy security, that means at the same times we are moving towards the food security. So both are interlinked to each other. If we need food security, then we first need energy security. Both are the basic requirements of any civilization. We can live without the machines, we can live without any other thing, but we cannot live without energy, and we cannot live without the food. So these two are the basic requirements of human beings. Roti, kapda aur makan. पहले से इनको बताया गया. So this is one component of the basic requirement. So, and we know that out of total energy demand, 10 to 15% of the global energy consumption is required for the agricultural operations. We all know that agriculture is an energy intensive factory. We can say energy intensive factory. As in factory, the products are produced inside a closed chamber. Similarly, in the agricultural operations, various agricultural products are produced in an open factory, open farm, open agricultural land, which is traditionally being used by the farmers these days and extensively used. So where the energy is required in agricultural operations, there are different agricultural operations in which in different way energy is required for the operations. So the first thing is seed bed preparation, where we prepare the seed for sowing seeds. So it is pre-sowing task. Then after sowing the seeds, there is requirement of water for irrigation. So and first of all, for seed bed preparation, we use tractors, automotive power, and the fossil fuels are being used at present at most of the places. And in this seed bed preparation, we use plow. Earlier, this task was performed with the wooden plow. Now this is replaced with the modern plow, which is called mold, bolt, plow, harrow, etc. And this is driven by the tractor, which is running on the automotive power, diesel engine, etc. Next, our energy requirement for the agricultural operation is water pumping for the irrigation purpose. This also consumes a lot of energy, and this is the process which is run for longer duration over the whole period of the production of the crops. And the next one is greenhouse climate control. Yes, there is one more type of farming which is done under the, we will know all those things in later slides. The greenhouse production is also done, that is called controlled climatic condition. So that control conditions is also generated by using the lot of energy. And the next one is post harvest control. There are some other steps also, pest control, herbicide, fertilizer application, and then post harvest cooling, and then the marketing, transportation, etc. So all these operations right from the beginning till the product to be sold in the market, all these things require input of the energy. So we can say that agriculture is an energy intensive task which is primarily performed by the farmers. So decentralized generation. Now suppose if we this energy intensive operations, if we completely depend on the centralized power produced from the centralized thermal power plants or centralized hydropower plants, then it will again be not be sustainable, because if we are dependent upon the coal based power plants to fulfill the requirement of energy to complete our task, that will not be called as sustainable. So what we need to do, we need to just install the solar photovoltaic plants at the farmer's field, or we can use the biomass, which is the byproduct of the agricultural production, for the generation of biogas. There are many techniques. Here we cannot cover all those things. Gasification process, where you can produce the producer gas, and alcohol, bioalcohol, which is also called biopetrol, that can be used as a petrol. So these all are the fuels which are produced from the renewable sources of energy. So this is called decentralized generation of the energy at the local level, at the farmers level. So if we use these types of energy, we will not have the dependency on the central energy stations. We will generate our local energy at the local form, and that too in the form of renewable, which will minimize the carbon footprint being emitted to the environment. So our goal is to a zero carbon. Closed loop agriculture means no wastage. We don't have to waste. As I told earlier, that the residue, agricultural residue, which will be produced from the agricultural production, that will also be used for the generation of electricity on the farm. We don't need even to transport that agricultural residue from one place to the other place where the energy is required. So this will enhance the ecosystem, and certainly, obviously, the AI integration is required to optimize all these things. Energy integration to enhance the energy security, AI optimization is certainly required. So what are the core pillars of AI and machine learning? It is supervised or unsupervised algorithm analyzing the historical patterns of the predictive modeling. First of all, we need to collect the data, and we already have the data of previous 1 or 2 decades. Those all the data are analyzed based on the different climatic parameters, soil data, atmospheric data, wind data, moisture data, solar radiation data. All these data are analyzed for the longer duration to predict for the future and integrated with the current production pattern. So this is the task of machine learning. The next is computer vision. I'm telling only in the context of agriculture. I'm not deviating to the other fields, so I'm focusing only on the agricultural production. So computer vision. In computer vision, deep learning, CLL, YOLO, allowing machines to analyze imagery from the drones, smartphones, and satellites. This will also play an important role what we will do, we will give our drones high definition cameras. Those cameras will visit the whole farm. Suppose any farmer has large farm of 5-6 hectares, where he cannot move by walking. He cannot cover all the field by walking. So he will use the drones, and drones will be equipped with the HD cameras, and those cameras will capture the thousands of photographs of whole the field, complete field. And these days governments are using these things to predict the yield of any year. They from the satellite images, they capture the crops grown, and based on those crops, they can predict the yield of the crops for any particular season, and further for the whole year. So these drones, which can cover large amount of area in a very short period of time, they can capture thousands of photographs of the crops, and these photographs will tell so many characteristics of the crops, such as what is the intensity of the plants, what is the color of the plants, is there any infection or any disease spreading in the plants. So all these things will be captured by the drones having the high definition cameras. At the same time as the Google Lens works, we can use our smartphones, take the photo, and farmers can use this photo to detect any disease affecting their plants. And satellite is, as I told, the satellite is already being in use to predict the yield of any particular year or any particular season. So this is the computer vision which is being used for the crop yield prediction and any future immediate requirement for the crop which is needed attention. Then natural language processing. One more thing is there, that our farmers may not be knowing English, or they may not be knowing the local language. Some of the farmers don't know even Hindi, and the farmers in the Gujarat, they don't know. Sometimes they even don't know Hindi. So to tell them the technologies in their language is similarly important, just to gather the information for the farmers. So the language is also a barrier that is resolved by the use of AI and machine learning. The farmers can conversate with the AI technologies in their own language, and the AI will convert the solution for their problems in their own language. So they don't need to know any high language programming, though the AI goes through the high level programming, but it hears the farmer in their local language, and it presents the solution to the farmers in their local language. So this is the benefit of the AI, which is helpful for the farmers which are not highly qualified in terms of language. So reinforcement learning, this is autonomous decision making agents controlling microgrid energy dispatch. Yes, the machines are allowed to learn from their own way. Suppose there is a robot. So robot arms are going to pick the tomato from the farmer's field, and and they are going to the field of farmers to pick the tomatoes. Suppose they used extra pressure to pick the tomato from the farm, and the tomato got crushed. So we will mark him, we will penalize the robot, and we will say that you are doing wrong. Again, suppose it put a small amount of pressure on the tomato and tomato dropped. So we will again say that we will penalize him, penalize the robot, and we will say that you have done wrong. So in this way, it will learn. It is called reinforced learning. It will learn that how much exact, and suppose if it exerted the exact amount of pressure which was required to pluck the tomato, then we will award it. Yes, you have done the right. So in this way, the robot will learn that when it was rewarded or when it was penalized. So in this way, it will keep on learning that what is the process of picking a tomato from the field so that it gives the maximum yield. So this type of learning is called the reinforcement learning, which enables the robots work in the better and efficient manner. Similarly, in the field of energy, we can also use the same technology. Yes, cyber physical systems. What are the various steps? What are the various steps to use the AI in the agriculture? So what we do first of all, we need to install the IoT sensors in the soil moisture to measure the soil moisture, to measure the leaf temperature, pyranometer readings, and inverters, etc. So the first step or layer one is the IoT sensor. We can compare it with our body. जैसे हमारे बॉडी में वो 5 सेंसर्स होते हैं, 5 इंद्रियां. We use eyes, tongue, ear, nose, and skin. Similar way, in the farmer's field, the sensors are used for the measurement of soil moisture, because the moisture is an important parameter which defines the productivity of the crop, and the temperature of the leaf, which also tells so many information about the progress of crop growth, pyranometer, which measures the solar radiation, inverters, the electricity production from the decentralized solar power plants. So these act as a indries of our body, जैसे हमारी body में इंद्रियां होती हैं. The layer 2 is transmission. Yes, so we can compare it with the nervous system of our body. We sense anything. Suppose we touch the hot cup of tea, then our nervous system sends the message to our brain. So similarly, the things are sent via the internet protocol, wireless internet, 4G, 5G technologies. So layer 2 is the transmission, the data which is recorded by the sensors, different type of sensors, those are transmitted to the brain of this whole system. And what is the brain? The brain is exactly the AI, where the data is transferred through the nervous system or transmission system, that is internet, to the brain, which is AI. Now this AI can be either the small computer kept itself at the farmer's field, or it can be cloud computing AI models. So either we can use the small computers on the field, or we can use the cloud AI computing for the processing of data by the brain, which is AI. And the next layer is muscles, means actually who will perform the task. Then AI will give the results. AI will analyze the data which are collected by the sensors, sensors, and this will be transferred to perform the task. What tasks can be performed? These are associated with the valves. Valves will automatically open. How much water is to be supplied? Accordingly, the valve will open. How much valve is to be opened for supply of water? Then the variable frequency drives, means motor, for irrigation motors. Suppose there is requirement of certain amount of water in the field for any crop, then the AI will analyze the amount of requirement of the water. How much water is required? That amount of water will be transferred from. Now this water can be this can be extracted from the ground or from any water resource. If it is being extracted from the ground using the solar PV panels, then solar PV panels, motor of the solar PV panels will come into the function, and solar panels will move towards the sun. Radiation will fall. Electricity will be generated. The required amount of water will be transferred from the variable frequency drives, and similarly, in coherence, the valves will be opened, and the exact amount of water that is required by the particular plant, that will be transferred. Suppose there is requirement of 50 ml of water, that 50 ml of water will be transferred from the underground water or reservoir to that plant. So this level of precision can be achieved using the AI. Now, what will this do? This will conserve our resources. Why this all is required? This all is required because of finite earth. Finite earth, because our earth is finite. So resources are finite. We cannot use the infinite amount of resources. So this precision level is required, which can be easily achieved with the help of AI. Yes. What is the agricultural lifestyle? So first, as I told, that first thing is the preparation of land and soil conditioning. One can think this is very easy task, but actually this is not an easy task. Preparation of the land, as I told, that this is done by the MB plow, moldboard plow, run by the tractor. And these tractors nowadays are being operated by the computers. So a certain level of automation is there. Soil conditioning. Soil conditioning means the finding the requirement of crop, and accordingly, what is the soil conditioning? Soil conditioning is first, many of you may not be knowing, the pH level of the soil, moisture level of the soil, and requirement of micronutrients such as NPK. N is nitrogen, P is phosphorus, and K is potassium. So these are the main requirements of the soil. If now we have to prepare our land according to the crop to be grown. So what earlier farmers were doing, farmers were plowing the complete field. They used to apply uniform amount of fertilizer in the whole field. Actually, it is not required. What is the requirement? The requirement is that our whole field does not have the same requirement of the nutrients. Certain part of the field may require nitrogen, certain part of the field may require potassium. At some places there may be high pH, at some places there will be low pH. But what farmers were doing, because they didn't have any technologies to assess the exact amount of requirements of the soil, so they used to apply the uniform fertilizer. So this was what? This was the wastage of the fertilizer. As we know that the production of fertilizer is again an energy intensive task. A lot of energy is embodied in the fertilizer production. So if it is being used wisely, then first of all, we will not be having the extensive fertilizer use. We will save the energy. At the same time, the chemical fertilizers are polluting to the water, underground water. So we will also be saving the pollution of the underground water. So here also the AI helps us. Land preparation, soil conditioning. The next one is crop establishment. Crop establishment includes the sowing and planting. This is also not an easy thing. Sowing of the plant. So if we think about sowing, then there are two things which matter. One is the depth of the seed. Seed is not very cheap. If we go to farmer and ask, seeds have very high cost. So damaging of seeds cost the farmer a lot. So what is the depth of sowing? What is the temperature of the soil? And what is the moisture content of the soil? These all the conditions affect too much. So we just need to confirm whether we are using the appropriate depth, we are maintaining the appropriate depth for sowing. And what was the traditional method? The traditional method was broadcasting. The farmers used to broadcast the seed. So this was the very least effective method of sowing the seeds. So later on, what came? There were seed drills. Seed drills were used, which maintained the regular depth of the seed under the soil, which is about 6 to 7 centimeter, 5 to 7 centimeter under the soil. But again, the seed drills didn't have any intelligence. They just kept on sowing at the same depth. Somewhere they used to skip the seeds. So this was not totally intelligent farming. But by using the AI, we can put the high definition cameras at the opening of the seed drills, which will identify whether the seed is being sown at the regular depth, at the fixed depth, and should not be any missing of seed while the sowing. So if there is missing or there is any clogging in the seed drill while the sowing operation, it will inform the driver, and driver will correct the thing, and it will again start sowing at the regular intervals. So, and at the same time, as I told, there are sensors in the fields. Those sensors determine the exact amount of moisture under the soil, exact amount of dryness of the soil. Temperature of the soil, dryness of the soil means moisture content. If there is excess amount of moisture, there is excess amount of moisture or lower temperature, too low temperature, then the seed will rot. And if the soil is dry and there is high temperature, even then seed will be dried and there will not be any germination, which will ultimately result in the lesser production of the crop. So we can see that how many mechanisms are involved in a small operation: land preparation and sowing and planting. Then next one is crop care. This is the process of longer duration in the phase of crop yield. It includes irrigation, fertigation, plant protection. Irrigation is the most energy intensive task while the production of any crop, growth of any crop. Then fertigation, in between fulfilling the nutrient requirement of the crop. And if there is any disease infecting the plants, that is fulfilled by the plant protection equipments. Now, what was the ancient method? I think we will cover it later on. We will go for with the summary of these things. Then the next one is harvesting and yield assessment. Harvesting is the operation when the crop is completely ripened and we are now ready to harvest the crop and assess the yield. Then we will go to the market, produced are they are harvested, we have cleaned them, we have graded them, and now the products are ready for the market. They are packaged and they are sent to the market. These all are energy intensive tasks. Yes, so here we will discuss all the things. The traditional method, uniform tilling and manual soil sampling and lab result takes week. Yes, there is a problem that farmers, there are KVKs, as we test our blood, suppose we have any disease, and after disease we went to the doctor, and doctor took our blood sample, and taking blood sample for any particular part of our body, he tries to assess the problem in our whole body. And suppose he says that I am sick today and I am going to doctor. Doctor is taking the blood sample from some certain part of my body, and he says that come after 3 weeks and we will tell you that what is the problem to you. So is it there? Does it have any meaning? I think no. There is no meaning of telling the result of today's sickness after the 3 weeks. At the present time, what was happening, even today in rural areas, the farmers collect the soil sample from their field. They collect, in moving their fields, they collect 10 to 12 samples from their field, and they put it in the polythene bag. They send it to the labs, and after 2 to 3 weeks, the result of their soil comes. And they inform that what is the result, what they test, that how much nitrogen is there, what is the pH of soil, is there any salinity in the soil, and what are the nutrients level at this time. So, and till then the weather is already changed, climatic conditions are already changed. So the testing samples which were collected 3 weeks ago, and after 3 weeks the conditions have been changed, and now he has to sow, the conditions are already different. So as the today's sickness and today's sample collected is not effective after 3 weeks, similarly for the soil, these things will not work after the 3 weeks. But with the help of modern techniques, we can prepare the soil preparation based on the zone mapping. This we are doing. And what AI can do, AI can use spectrographic soil sensors which will give the real-time nitrogen, phosphorus, potassium, and pH mapping. These sensors produce the light waves. These light waves go to the soil sample, and they have different ability to absorb the radiation, and hence the different reflectivity of any certain light to the sensor back. So based on the light reflecting back from the soil, it instantly tells that which nutrient at which soil pixel is more or is in lower quantity. So at all the not all the at the maximum points, we can get the instant value of the NPK present in the soil, and this instantaneous measurement of these values can help us in determining that whether at which location which fertilizer is necessary. So in this way, we don't need to spread the uniform amount of fertilizer at every location. Earlier, what farmers doing, they were guessing. They were just before sowing, they just start spreading the fertilizer, which was floating the ground level, which was increasing the intake of the fertilizers. So with this method, we can reduce our intake of fertilizers, and to the particular plant, to the particular location of the field, we can apply the fixed amount of fertilizer. In this way, spatial interpolation using random forecast. Yes, exactly. We can do the interpolation, because even by this technique, we cannot do the testing at each and every pixel of the soil. So what AIs can do, AI can analyze the previous data available with it by machine learning, and they can use the data by interpolating the values collected from the field of the farmer, and they can generate a comprehensive map based on the color, which will tell about how what exact amount of nutrient is deficient in any particular location of the soil, and the farmer can, and it can not farmer intervention was required. Then the drones can apply the that amount of we will feed that map to the drones and AI. Then again it will guide that based on that color availability, this has to spread the fertilizer at that location. So it will be very comprehensive. Yes, in phase 2, sowing and crop establishment. So earlier what farmers were doing, farmers were saying that suppose in the they have to sow the wheat, and the time was fixed that in 3rd week of the November we have to start the sowing. But as we all know that these days there is climate changes prevailing, and due to this climate change, we cannot say that at the end of November or at the 3rd week of the November there is appropriate time for sowing the wheat. So that time of sowing the wheat can be determined exactly by the AI, that this is the at this time, with the help of weather forecasting data available with the meteorological departments. The AI can analyze those data. AI can analyze the conditions of climatic conditions. It can analyze the conditions of our soil, atmospheric temperature, etc. And based on the common conclusion, it can say that on this date, at this time, if you will sow, then there will be the maximum germination of the plant. So this is the benefit of the AI, which helps not by the calendar based sowing. It helps in determining the exact time, exact date of sowing, which will further help in giving the maximum yield of the crop. Next one is crop care, which includes irrigation, nutrients, and protection of the crop. Again, the irrigation was done based on the calendar. Suppose we have sown the crop on this date, then after the so many days, we have to give the irrigation to the plant. Then after certain days, we have to apply the chemical fertilizers. And after a certain time, we have to visualize the crops and their leaves. and based on the visual effects, we have to apply the fertilizers or pesticides on the crops. Now, what was happening? So now what is there? We have applied the IoT-based sensors on our almost all the parts of the field, which determines actual amount of moisture level available in the soil. It determines whether this moisture level is appropriate for that crop or not, and as soon as there is requirement of the crop, roots say that I'm thirsty, then the amount of water that is required, that is sent by the AI to that particular plant, not to the whole field. Actually, we don't need to irrigate the whole field. We don't need to irrigate the soil. We just need to irrigate the root zone of the plant. So this is very much helpful in precision farming. This is called the precision farming, because I have already told that we are limited with the resources, and water is fresh water. Fresh water, that is only 1% of the total water available on the earth. So if we will not use the water wisely, then we will certainly be going to in the trouble in near future for our future generations. And agricultural irrigation is the major operation that uses the fresh water. So in that field, there is immediate requirement of using the water precisely. So by adopting drip irrigation, by adopting sprinkler irrigation, we have already minimized the utilization of water from the underground or from the river. But by smart way of utilizing the drip means the water will be given to the plant root, not to the soil, by the drip irrigation system, that too when it is required, not based on the calendar date. So that will further reduce the application of water. In the same way, chemical, as I already told, that sensors will determine that where there is requirement of chemicals and particular amount of chemical, that will be applied only to that plant's root. So it will further reduce the demand of the chemical fertilizers. And disease and pest reduction. Earlier, what farmers were doing, they used to see the plant's leaves and they observed that there is yellowing of the leaves. They assumed that yellowing is due to the deficiency of the nitrogen. They applied the urea at that place. So this was there. But what was there? But that as long as the plant leaves become yellow, 2 or 3 weeks before that yellowing, which was visible, the plant's cells started dying. So what invisible cameras do based on the AI, those invisible cameras based on the AI, they detect the attack of that pest at the time of actual attack of those pests. So farmers were knowing it when the effect of the disease was actually visible. But till then, the plant was sick, plant was about to die, and that will affect the production of the farmer. But with the help of AI and other smart tools, we can detect it at the early stage. We can small amount of pesticide, herbicide at the time. Actually, in agriculture, this is time intensive and this is energy intensive. का वर्षा जब किसी सुखाने, जब खेती सूख गई तो बारिश का कोई मतलब नहीं. इसी तरीके से at every step, at the time of sowing, at the time of irrigation, at the time of fertigation, अगर हमने कोई काम समय पे नहीं किया तो उसको करने का कोई मतलब नहीं है. आप कितना भी उसमें फर्टिलाइजर डाल दो, कितना भी इरिगेशन दे दो, एक बार प्लांट अगर सूख गया, then there is no need of applying lot of water on it. The thing which is essential is that you apply the things at the right time. You miss the time frame, you miss everything is gone. Actually, agriculture is not like other factories. In other factories, suppose you have produced anything and that final product you are suppose there is any fault in the factory and there is fault in any factory, then what will you do? You will stop the button, you will stop the machine, the belt will be stopped, you will repair the machine, And again, you will run the machine and production will be started and products will be produced. But what is there in agriculture? You cannot stop the thing. Once you made any mistake at any step of the agriculture or any step created due to the natural calamities, then you cannot go back. You made any mistake at the initial level, you didn't water or you flooded it with the water, the crop's roots will be damaged, it will be rotted. Or suppose you applied large amount of fertilizer, the crops will be heated, they will be burned. So at any stage you made any mistake, you cannot go back. You will again have to wait for the next year for the next crop. And that's why, and again, suppose there is any product which is produced at any factory, you can put it many years on the shelf. There is no shelf life like term. But in case of agriculture, there is certain shelf life. If you produced and you harvested the crop, you harvested the tomato from the crop, on the same day, it will start producing the heat and it will start damaging. So you cannot have a lot of time. You don't have the shelf life. So there are so many problems with the agriculture. That's why in agriculture, in any field, either you use or do not use AI, but in case of agriculture, there is very much precision required for making our farmers rich like other industrial businessmen. So what we do, we teach our farmers. हम अपने farmers को क्या करते हैं? We teach them कि भाई you grow, we make them grower, and like other businessmen, we don't make them a businessman. How they get their value, this will come in the next slides. So we have to make our farmers also learn them after growing how to make the business, how you get the maximum return of your product. So this we don't teach to the farmers. We teach only farmers that you grow lot of things, lot of product. After growing them, they just dump the things. Sometimes they outside the mandi, they dump the tomatoes, they dump the onions, and they don't get any price for that. They produced a lot, but it could not give them the appropriate return. So we also have to make them a good businessman, so that they could analyze the market, they could analyze the value of their products, they could learn how everything I cannot cover. They should learn how to add the value to the product, value added products. 1 kg of aloo potato is sold in the market for 10 rupees per kg. But for that 1 kg, you make the chips, wafers, those are sold for hundreds of rupees in the market. So we have to make the farmers that how they increase the value of their products. So in this way, AI can help the farmers in determining the appropriate timing of the irrigation, appropriate amount of the irrigation, uniform chemical spraying at exact timing. Timing is very much important. And as I told, this is the most energy intensive. Crop care is the most energy intensive operation for the crop yield. So everywhere energy is involved. Energy is involved everywhere. Yes. So these are the soil moisture sensors. These are the drones being used. आजकल हम लोग drones use करते हैं for spraying and dusting. These drones are widely used these days for the spraying and dusting. Yes, the next phase is harvesting and post-harvesting logistics. So traditional method was using in earlier decades ago, we were using the manual harvesting, visually grading, and immediate local market dumping. So these were the traditional methods which were adopted 20 years ago, 25 years ago. What are the modern techniques? Now we have mechanized harvesters, which cut the crops, bind them, clean the crops, and optical sorting belts, which sort the things based on the color, and cold chain transportation system. So these are the modern techniques. And what AI can transform in this harvesting, AI will, what was the harvesting traditionally method? The harvesting method was that whole crop was harvested at the same time. Suppose we are talking about the tomato. So if the farmer is going to harvest, farmer will harvest his whole crop. Either the tomato is in red, or it is green, or it is over ripened, all the tomatoes he will harvest at the same time. But what AI can do, AI and robots can identify those plants, those tomatoes which are ready to be plucked. So the only tomatoes will be plucked which cannot sustain on the field for more time. They are ready to be plucked. They will leave the green tomatoes for the next week, and they will not allow to come the situations of over ripening. So in this way, the exact timing, as I told, that every step needs the timing. Exact timing of the ripening of the crops will be determined with the help of AI. Instead of harvesting whole crop at a time, the harvesting will be done in the steps. The crops which is ready, the products which are ready will be harvested at present, and the which can be left for the next week, those will be harvested in the next week. At the same time, the grading will be done, good quality products and the lower quality products, so that it could be sold according to their value. And one more problem, as I told, that we don't teach farmers that how to get the maximum value of their product. So here AI will help. How AI will help the farmers? The AI will tell that, first of all, AI will be used for enabling the products to increase the shelf life of the products. So farmers should be equipped either on farm storage of the to increase and storage of the products, and or government provided storage of the products. Governments also provides the cold storage, so that farmers could hold their products for the shorter duration or longer duration, so that when the market prices are high, they could sell the products in the market at that time. Again, what poor farmers do, they harvest the product, they go to the nearby market where there is no demand of their product. So they either dump it or they just get the minimum price of their product and they come back. So they are growing a lot, but they are not getting the return of that their products. So this is the problem. So what AI will do, AI algorithm will analyze the data of the nearby markets. They will find out where there is demand of their product and when that demand will be occurring and in which market. So by this algorithm, AI will analyze based on the machine learning previous experience. AI will tell the farmer that you should hold your product for 3 days, and after 3 days in that particular market there will be higher demand of your product, and till 3 days you have to kept your product in the cold storage, and then you will get the higher returns. So in this way, AI will also help the farmer to get the maximum return of their products. So this is the magic of the AI intervention in the agriculture. So these all were the things which are done at the open field. Now I will give some insights on the control environment agriculture. So all these things I have discussed till now was based on the agricultural operations on the open field. There is one more type of agriculture where the agricultural production is done inside the enclosed environment, and that enclosed environment is controlled by the several machines, robots, AI, etc. So sometimes we call it greenhouse, but actually greenhouse is not that a polythene structure. We all know that a type of tent, that is not a tent. That is an enclosed structure which is supervised by the various machines and which controls the microclimate of that enclosed environment, which will give the environment to the crop according to their need. So again, what are the requirement of enclosed ambience? The requirement of any plants are light, temperature, humidity, carbon dioxide, and those can be actively manipulated. So here our dependency, our problem was that we don't have any control on the nature. There is sun, sometimes there is rain, sometimes there is carbon dioxide excess or lower, or humidity is not in our control. So climatic parameters in the open field are not in our control, but in the enclosed chamber we have advantage that we have controlled, we can create the control environment with all these parameters. So these controlled environment provide the favorable conditions, and the growth of our produce yield is increased 2 to 3 times more. So what is the driver? The driver is the urbanization. We all are moving to the cities. We don't want to live in the rural areas. We want to live in the urban areas. There is degradation of the land slowly by the lot of application of fertilizers, lot of application of irrigation, extreme climatic events, erratic climatic conditions, and water scarcity. So these things make us think to move towards the controlled environment agriculture. So what are the advantages? By this, since we can create the environment according to ourselves, we can take the off-season crops, and which also saves 90% water productivity compared to the open field systems. Everything is automatic, temperature, climate, everything. So in that condition, yes, someone may think that there is a lot of energy intervention in such type of cropping system. Yes, there is a lot of energy requirement in such type of system, but there is solution. What is there, that if we use that amount of energy obtained from the coal-based thermal power plant, then again we are shifting our goals from one to other. So we will have to move towards the sustainable sources of energy, which are obtained from the solar photovoltaics or agricultural residue. Agricultural residue will be used for generation of biogas. That biogas will be used for running the generator, and generator-based electricity that will power our farms. Similarly, from some of the crops such as sugarcane, corn, they are rich in starch, and those starch crops can be used for production of alcohol, that is the ethanol, bioethanol. So that ethanol can be used as replacement of the regular petrol, and that can be used for further generation of the electricity or any energy use. So these renewable sources of energy integrated with the precise farm of agriculture, we can grow the agriculture in sustainable way. Yes. This is vertical farming. Modern high-tech vertical farms in the greenhouse where the area is less. We cannot grow as in Mumbai, like cities which are very high in density. We cannot give the homes to everybody on the horizontal. We are growing vertically. Similarly, if we have to fulfill the requirement of food, in future we will have to go for the vertical farming, where we use the stacks of 3 to 4 to 10 to 15 stacks, and there we can do the farming. Yes. So what is the greenhouse protective cultivation? It is of 3 types. One is polyhouse, other one is insect-proof net house, and the third one is shade net innovation. Polyhouse, the basic structure is made of galvanized iron, and on that iron we cover it with the help of polythene sheet, UV stabilized polythene sheet, and that polythene sheet creates a closed airtight chamber for production of agricultural products. Other one is insect proof net house. Net house is वो जालीदार जो कपड़ा होता है, वो allows the air to communicate from inside to outside and outside to inside, but it doesn't allow the insects to come from outside to inside. So it protects our crops from insects and allows the aeration from outside to inside. Similarly, shade net innovations. Nowadays, there is the color-based agricultural operations are being performed. What is the color-based? Some of our colleagues are doing research on that color-based. They are using the different colored shade nets. Some are using black, some are using red, some are using blue, white. So the production of agricultural produce based on the shade net color is also affecting. So what is obtained that as in solar light, there are 7 visible colors. Vibgyor, we all know, violet, indigo, blue, green, orange here. So the blue color and red color are most important colors which play their role in the growth of plants. In the early stage, blue color is necessary, and in the later stage, red color is necessary as it is obtained from various researches. So these colored net also play their active role in the growth of the plants. These are the agricultural structures, protective cultivation done under the greenhouse. Plant factories. जैसे हम फैक्ट्रीज की बात करते हैं वैसे हमारी प्लांट फैक्ट्रीज भी, वी कैन कॉल दिस प्रोटेक्टिव एग्रीकल्चरल सिस्टम्स एज प्लांट फैक्ट्रीज and vertical farming architecture. So this is, as I already told, that is a completely sealed building-like structures, and vertical stacking. Crops are grown in 3 to 25 vertical tiers under the artificial lights. It has higher space efficiency. In case of horizontal cultivation, we cannot use we cannot grow a lot of crops, we cannot get a lot of yield, but in case of vertical, 1000% of efficiency is achieved. And HVAC is controlled dehumidification system, maintaining the optimal vapor pressure deficit, etc. That can be easily performed inside the controlled structure farming. Photomorphology, morphogenesis, and artificial LED lighting. Yes, so this is also an important thing we should know. That's why I kept this slide here. Though the radiation which is coming from the sun, the radiation which is required by the plants is called photosynthetically active radiation, because the photosynthesis is the process which is used by the plants to convert the solar energy. Actually, what are the plants? Plants are nothing but those are the conversion of solar energy to the biomass. So I tell my students, I keep on telling my students that sun is the ultimate source of the energy. If someone says that we don't use sun, it doesn't have any meaning. Everybody is using sun. In day-to-day life, we are using sun. The ultimate source of energy is sun. We are eating food. The food is being produced from the sun, because biomass is nothing but it is the conversion of solar energy from sun to the carbohydrate and then further to the sugar. So it is the biomass, and the radiation that is required, that is photosynthetically active radiation, which lies from 400 nanometer to 700 nanometer. As I already told, that blue spectrum and this red spectrum is, out of those 7 colors, blue and red spectrum are most widely used for the growth of the plants.
Hello, sir. What time you have taken left for complete presentation?
I think within 5 minutes I can complete.
Okay, sir. Thank you.
Yeah. So this is the artificial LED lighting which can be used. Yes, as I told, that in the greenhouse, inside the greenhouse, these 3 technologies, these 3 methods can be used for the growing of crops. It is hydroponics, aeroponics, and aquaponics. These all are the soilless cultivation. In hydroponics, we just use the flowing water which contains the nutrients, and the soil roots are dipped in the water. And in case of aeroponics, the roots are hanging in the open air, and the mist enriched with the nutrients are supplied to the plant roots. And aquaponics is the technique in which the fish and plants are grown together at the same water container. So the excreta of the fish is used as the fertilizer for the crops. So mutually there is a give and take process. So these are the techniques being used these days, and these can be adopted in the cities. ICAR, Indian Council of Agricultural Research, which is situated at the Pusa, New Delhi, they have developed these vertical farming technologies, which is based on the hydroponics and aeroponics. People can install this in their balconies, and they can grow thousands of plants at their home. They don't need to go to the market to purchase the highly pesticide infected crops. They can grow their own tomato, cucumber, and coriander, etc. They can grow at their home, and these products are available at the Pusa, New Delhi. Anybody can go and get training there and purchase it at their home, and at least 3 to 4 stacks vertical farming structure they can purchase, and which can produce almost 1000 plants at their home. So these are the technologies. This is some example of that soilless units. Yes. So I have already discussed that renewable energy can be integrated in many ways with the agriculture, and AI intervention can further reduce the use of energy. Yes, solar panels can be operated at the maximum power point with the help of fuzzy logic controllers, artificial neural networks, to give the power at the maximum rate. Yes, there is one more thing nowadays, that is agrivoltaics and energy water fruits energy. Agrivoltaics, this is the agrivoltaic. Here, there is a fight between the energy and the crops. So the solution is that we can install the solar photovoltaic panels at about 10 to 15 feet, and under the solar photovoltaic panels we can grow the crops. They help each other. Actually, sometimes there is load of solar radiation on the plants. That load of the solar radiation or heat on the plants can be reduced with the help of installation of solar panels, which will create the shade on the plants. And the solar panels reduce their efficiency of production of electricity if they get heated. So the plants produce the moisture through the evapotranspiration process, and that moisture will cool the panels from the bottom. So they will help each other. Panels will provide the shade to the plants, and there will be less moisture evaporation from the plants and nearby soils. So there will be less requirement of soil and the saving of the plant water requirement. At the same time, there will be higher production of electricity from the photovoltaic panels, and efficiency of both will be increased. So there is a new technology that is called agrivoltaic system. So there will be less fight between for the land, for the plants and agriculture both. So AI tracking tools help in all these things. These are the government initiatives. Government is providing help to the farmers. They are providing fund for the vertical farming. Digital agricultural mission funds are being made available, and some advisory tools are available in the farmers mobile in the form of app. So these are the things. Major challenges, high capital. Yes, there are some challenges also. Some of the sensors are available at the lower cost, but many sensors still cost too much to the farmers. There is need of digital literacy trainings to the farmers, and internet connectivity at the rural areas, power availability that can be fulfilled by the decentralized power system. So these are the visions for the agriculture 5.0. We can integrate it with the robots, and we can achieve the agriculture 5.0 mission. And we should know that the AI and machine learning and robots will not replace the human beings. हम लोग डरते हैं कि ये ह्यूमन बींग्स को रिप्लेस कर देंगे, लेकिन ऐसा नहीं होने वाला है. ह्यूमन विल ऑलवेज बी देयर, देयर रिक्वायरमेंट विल ऑलवेज बी देयर. दे विल जस्ट इनहेंस द एफिशिएंसी ऑफ द थिंग्स and will help in giving the higher production and enable the increasing economy and GDP of our country. Thank you.
Thank you so much, sir. Very nice talk, and cover all the things in a very lucid manner. So
I tried to
once
cover.
again, thank you very much, sir.
Thank you.
Sir, we have some queries, not a question,
Yeah.
because
Yeah,
you
yeah.
have elaborate all the things in this lecture. Sir, what is the awareness program for the farmers by the
Yes,
government of India? Because without awareness of the farmer, everything is, I think, useless, because our motto fulfill, how can we transfer our ideas to the farmers in the reality? How AI change in the reality?
Yes, yes. Actually, I'm working in the tribal area here at Gujarat. So in this tribal area, there are farmers which don't know anything. Even they don't know the basic things about the agriculture. So we conduct the training programs. All the agriculture universities have lab to land programs, and they have agencies called Krishi Vigyan Kendras, KVKs. These KVKs are continuously involved in transferring the technology which is developed inside the lab, these all the AI technologies, to the farmers. They go to the farmers field, they conduct the trainings for the farmers at their at the university level, at office level, even the in the Rabi season, Kharif season. We as a farm scientist go to the farmers field, and there the trainings are organized, and we teach them that what they can do to get the maximum yield and to integrate the energy with the farming system.
Okay, thank you, sir. We have a couple of questions in our chat box, but it is not possible to cover all. A few very important questions is that, sir, in the context of the agri-solar research, what is your perspectives on integrating solar panels with agriculture fields to enable the simultaneous production of crops and solar energy?
Yes, as I told that agrivoltaics is an emerging technology these days, as we don't have too much fertile land, and at the same time we need the energy. So adoption of agrivoltaic will certainly help in producing the energy at the same time performing the agricultural tasks. This is a well known technology this time. Most of the things have been evolved.
Okay, sir. Another question is that can AI be used to increase agriculture produced by using AI in genetic engineering? Is it being using already exist? Any positive results seen in this area?
Actually, I don't belong to genetic. I am agriculture engineering, so I cannot say more about that genetics. But I think there will be things I don't know, so I don't want to say anything about the genetics related things.
I think there is no question from the participants. So thank you very much, sir, for
Thank you, sir.
sharing
Thank
your
you for
valuable experience and valuable ideas and enlighten us. So thank you very much, sir. Thank you. Thank you,
thanks
sir.
for providing me the opportunity. Thanks to all of you for bearing
Thank
me
you, sir.
such a long time. Thank you.
Now, one important announcement to all dignitaries and participants and students, and we will rejoin at 2 p.m. sharp. Now it is the time for lunch break. So thank you very much. Thank you, sir.
Hello everyone. I just want to make a short announcement that in some time you will also be shared a feedback form in the chat box. So that feedback form, we request you all to fill that feedback form, so that your attendance and your certificates can be made using that feedback form details. Thank you. See you sharp at 2 p.m. Thank you everyone. शुरू करें?
Hello. Hello, Dr. Risha Verma and Dr. Gupta.
Good afternoon, sir.
Good afternoon.
You are audible, sir. I think someone's phone is lying nearby.
मैम आप लोग नियर बाई दो लोग बैठे हुए, कोई ऑन करके, कोई एक अपना या तो म्यूट करे, कुछ दो लोग नियर है इसलिए इस तरह से आवाज आ रही है।
नहीं, अब नहीं हो रही।
Hello.
Okay.
Can you
So
hear me
a very
clearly?
warm, yes, sir. Yes, sir.
Yes, sir.
Okay, so I welcome all of you back after lunch for this very exciting session of physics sparring industry, and I have the honor of welcoming Dr. Atul Khanna, sir, who is presently serving as Professor of Physics at Guru Nanak Dev University, Amritsar. Now, sir began his research career at Technical Physics and Prototype Engineering Division of Bhabha Atomic Research Center, Mumbai, where he worked on thin films, gas sensors. He did his MSc in physics from IIT Delhi and his PhD in applied physics from Guru Nanak Dev University. Later, sir carried his postdoctoral research at University of Arkansas, USA. His research spans oxide glasses, thin films, gas sensors, superionic solids for batteries. He is recipient of the Young Scientist Award in Physics from Indian Science Congress Association, Kolkata. He has guided 22 major research projects, and presently one is ongoing. And he has the honor of publishing around 110 research papers, and he has guided around 17 PhD scholars. So with this massive introduction, I warmly welcome you, sir, to take over the session. Thank you.
Thank you, Dr. Risha Verma and Dr. Nupur Gupta for this kind invitation. I'm very happy to be here and to attend this summit. So shall I share my presentation?
Yes, sir. Yes, sir.
Yes, sir.
Can you see it? Is it
Yes,
visible?
sir. Yes. Yes, sir.
Yes. It's currently on 70th slide.
Let me. Is it full screen now?
Yes, sir. Full screen.
Okay. So this is the title of my presentation. So once again, I thank the organizers, in particular Dr. Nupur Gupta, for this invitation. And this presentation is on materials synthesis, processing, and characterization techniques. We need a variety of materials if we want to have a Viksit Bharat by the year 2047. We need large-scale manufacturing of variety of magnetic, ceramic, battery, solar cell material, silicon material, and their fabrication in different devices. We have to process those materials after synthesizing, and then we have to characterize them, see their structure, atomic structure, magnetic properties, electrical properties, optical properties, and so on. And materials synthesis, processing, characterization, we need competencies in all these branches. Of course, one person may not be able to do everything. So you need a teamwork. So Richard Feynman, one of the great scientists from the last century, he was also an outstanding teacher. So he made this statement: all matter is made up of atoms containing electrons, protons, and neutrons. And according to Richard Feynman, this is the deepest truth of the nature. Someone asked him, what is the deepest truth of nature? If you can describe it in just one line or few words, and if you know that knowledge, you can derive a lot of other useful information and knowledge. According to Feynman, the understanding or the knowledge that all matter is made up of electrons, protons, and neutrons, that is the atomic structure of matter, is the deepest truth of nature. So can you hear me clearly? Am I audible?
Yes, sir. Yes, sir. Audible.
Yes, sir.
Okay. So at the microscopic level, that means when you are dealing with electrons, atoms, protons, nuclei, you need quantum mechanics. And quantum mechanics was discovered in the last century, basically between the years 1900 and 1930, in the first 30 years of the 20th century. And people like Planck, Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Pauli, Ehrenfest, Pearls, and many others, they contributed to the development of quantum mechanics. And now we know, or we are fond of making this statement, that there is no phenomena relating to light, matter, and radiation which cannot be explained by quantum mechanics. So quantum mechanics is unusually successful to explain atomic phenomena to very high degree of precision and accuracy. And how quantum mechanics was discovered? It was discovered by some routine observations of spectroscopists. So spectroscopists, they studied the emission spectra of elements like hydrogen, helium, argon, and they found these atoms, when they are in the excited state, you can put them in the excited state by creating an electrical discharge or by using a flame test that you do in chemistry, and you observe only certain characteristic lines from each atom, as if each atom has a unique atomic structure, unique arrangement of electrons inside them, and there is some kind of transitions between inside these atoms which emit spectral lines of definite frequency or wavelength. So this simple observation by spectroscopists of the 19th century, it provided a clue that different atoms have something different inside them. So then came the double slit experiment discovered by Young's double slit experiment discovered in the 18th century, and that showed that light has a wave nature. Earlier in the time of Newton, they said light has a particle nature, and later on experiments were done by Davison and Germer, and also by G.P. Thomson, who showed that the so-called matter, the electrons, neutrons, they have a wave nature also. So now we say that matter and radiation have neither a wave nature or a particle nature. It is neither. How you interact with matter or radiation, that will tell you whether it behaves like a wave or a particle. So reality is not objective. Reality is subjective. How the observer interacts with the matter, that will reveal information about matter. And we know electrons, they have a wave nature also. Earlier, we were thinking they have only a particle nature. The electrons discovery is attributed to J.J. Thomson, but his son, G.P. Thomson, he showed that the electrons have a wave nature also, and they show interference effects. And electrons of kinetic energy of say 50 to 100 electron volts, they have a deep Broglie wavelength of few angstrom. And this wavelength of few angstrom matches
Excuse me, sir, maybe you are muted.
Atul sir, we can't hear you. You're on mute.
Sir, you are on mute. Kindly unmute yourself. Yes.
Yeah, can you hear me now?
Yes, sir.
And the slides are visible?
No, sir, not now.
Not
We need to
now.
reshare.
Maybe I have to again.
Yes, we'll have to reshare again. Yes. It's not full screen. Yeah.
Okay.
Yes. Yes.
So some of the other strange ideas of quantum mechanics is tunneling, where a microscopic entity like electron, it has a kinetic energy less than a potential energy barrier height, but still it can come into a region which is classically forbidden. And this arises particle is something localized. So over small intervals of time within the limits of uncertainty principle, the electron, which has a kinetic energy less than the potential energy barrier height, it enters classically forbidden region. This is the phenomenon of tunneling, which is used to make devices like tunnel diode or a single electron transistors. And tunnel diodes are in turn used to make high frequency oscillators. So what are the applications of physics? We have understood material properties significantly during the last 100 years. And you need quantum mechanics if you want to study, if you want to understand their magnetic, ferroelectric properties, or even properties like synthesis techniques. So the synthesis of materials is very important. And the material science aim to study the aggregate or collection of atoms. If you study the aggregates of atoms, molecules with one or more dimensions of the size of few nanometers, then we are dealing or we are concerned with nanomaterials. So one of the material which has revolutionized our modern day present world is silicon. And silicon is a semiconductor. That means it is a material whose conductivity is between that of an insulator like a diamond and a conductor like a copper or a silver material. Silicon is a material which is very essential for our electronics industry. All our electronic devices, your discrete devices like diodes, MOSFETs, MOSFETs, sorry, not MOSFETs, they are made out of silicon. And we need single crystal of silicon. Silicon wafer is required for the fabrication of electronic devices like diodes, transistors, BJTs, MOSFETs, triac, diac, and so on. So a single crystal silicon is very essential we in India are still not able to produce high quality electronic grade silicon. So silicon wafer is imported. We don't make it in India. We make some polycrystalline silicon wafers. But if you want to fabricate electronic devices, whether discrete electronic devices or integrated circuits, you need single crystal silicon. So we are having in nature, we are having some materials which are single crystals, like for example, diamond, ruby, or sapphire. These are single crystals in which ordered arrangement of atoms that extends throughout the dimensions of the material. And there are also man-made crystals like silicon, germanium, gallium arsenide, and many other hundreds of single crystals like sodium chloride. They are technologically very important materials, and we can use this material to engineer quantum structures like quantum well lasers or heterostructures. So making of such man-made crystal is called crystal growth. So crystal growth of single crystals of silicon, germanium, gallium arsenide, gallium nitride, aluminium gallium arsenide, or other single crystals like bismuth germanate, sodium chloride. It is a very important area of technology, of materials technology. So how we make silicon single crystals? Silicon is very abundant in nature. Silicon exists in nature in the form of silicon dioxide. Your sand, the shining particles that you see in sand, they are silicon dioxide, quartz. And we can reduce silicon dioxide by reaction with carbon or coke at elevated temperatures like 1800 degrees Celsius. Silicon dioxide is reduced with carbon and it forms silicon, carbon monoxide goes out. So in electronics industry, you need very high purity silicon, silicon of the purity of 7 nines or 8 nines. That is known as electronic grade silicon. So once you have prepared silicon, you refine it by chemical vapor deposition techniques where silicon is reacted with hydrochloric gas, HCl gas, and it forms trichlorosilane, SiHCl3. And this trichlorosilane, it is allowed to undergo decomposition and it forms silicon. So this way you can get very high purity silicon. So one of the very important properties of semiconductors is that if you add a very small amount of dopants like phosphorus or antimony or boron or aluminum, then the conductivity is modified drastically. By several thousands of times, the conductivity enhances by adding very small amounts of dopants. So this is the phenomenon of doping. So silicon wafer production is done in several steps. You start with the initial raw material, that is silica, silicon dioxide, which exists in sand. Silicon dioxide is very abundant in the earth, and you produce silicon, which is metallurgical grade silicon, MGS. This metallurgical grade silicon may be having a purity of 97 or 98%. And then it is reacted with HCl and it forms chlorosilanes like SiHCl3, trichlorosilane. And we get pure deposited silicon. This pure deposited silicon is then melted in crystal pullers. And we do crystal growth by using crystal pullers and by using Jarlowski technique. And we get these big ingots of electronic grade silicon, which may have diameter of several inches, maybe 12 inches in diameter and several feet in length. And then you can cut and get wafers of high purity electronic grade silicon. And during the process of crystal growth, you can add impurities, deliberately add impurities like phosphorus or antimony, and you can get doped P-type or N-type silicon. So this material is extremely important. If any country or any nation wants to have a mastery of the fabrication of semiconductor devices and integrated circuits, it must have these high purity electronic grade silicon wafers. So this is a schematic of a typical crystal growth puller. We have a furnace and we have a crucible. The crucible uses silicon dioxide or quartz, and inside this we are having high purity electronic grade silicon, which is having a melting point of about 1420 degrees Celsius. So you will melt the material around 1600 degrees Celsius so that it is sufficiently fluid. And we are having a seed crystal. The seed crystal is in a low temperature region. The melt is in the high temperature region. So the seed crystal touches the melt and gradually it is pulled upwards through a region of higher temperature to a region of low temperature. And this way crystal growth takes place. So very slowly you cool the melt. And when you cool the melt very slowly, you give sufficient time to the atoms to arrange in regular periodic lattice, so they form a single crystal. So crystal pullers are huge machines and very expensive machines, and there is a lot of expertise in growing high quality, defect-free single crystals. Because defects, if they are there in your single crystal sample, they will increase the resistivity, they will cause the scattering of carriers. So this is the photograph of a typical single crystal ingot of silicon. Silicon is a semiconductor, band gap is 1.1 electron volt. Pure silicon is highly resistive. Its resistance may be several mega ohms. But if you add very small amounts of dopants of the order of 10 to the power 13 to 10 to the power 15 atoms of dopants per centimeter cubes, conductivity can increase few thousand times. So that is the remarkable property of semiconductors. Very small amount of dopants, they drastically enhance the conductivity. And you can make a p-type conductor in which the carriers are positively charged. You can have a n-type conductor in which carriers are negatively charged. And we need both n-type materials and p-type silicon to make PN junctions, PNP transistors, n-channel MOSFETs, p-channel MOSFETs, and so on. So this is the photograph of a typical silicon wafer, which may have a diameter of, say, about 30 centimeters, 1 foot. And it is given mirror-like finish, and you have to handle it in a clean room because silicon can oxidize very rapidly and it can form, it always forms, in fact, an ultra-thin layer of silicon dioxide on its surface. So we are still not making these silicon ingots and silicon wafers. These are being imported. But we have started work in the IC fabrication, and many new IC fabrication plants are also coming in India. Some plants have become operational in the state of Gujarat. Recently, Japanese Prime Minister, she visited India, and Indian and the Japanese governments, they signed agreement in which Japanese companies will establish IC fabrication plants in the state of Assam and Gujarat. So this is a cut view of an integrated circuit. I am sure you must have all seen these devices, the so-called chip, having black plastic coverage, and these are the pins. This is the dual inline packaging of an integrated circuit. And if you remove this plastic top covering, you will see this beautiful circuit. These are the interconnections, and you can zoom it, and you can see, if you want to see even sub-microscopic parts of this integrated circuit, you will need an electron microscope, a scanning electron microscope. You know, an optical microscope can give you maximum magnification of 1000 to 2000, whereas a FESM can easily give you a magnification of 500,000 or 600,000. So the integrated circuits are those in which the entire circuit of an amplifier or an oscillator or a comparator is fabricated on a single wafer of silicon. We make all the diodes, PNP transistors, MOSFETs, whatever you need, resistors on that surface of silicon. So instead of having discrete components, you are having miniaturized components in which the size of a transistor may be just few microns or even less. So the distances which the electrical signals travel are very small. So the speed is higher. So integrated circuits are faster. And you know, speed is one of the criteria of any modern day computer or other microprocessor or other devices. So integrated circuits are extremely essential. They are everywhere in all your electronic devices like televisions, laptops, mobile phones. You name any electrical or electronic device, even your automobiles, they are having large number of sensors. So you need chips, integrated circuits to have those systems in your vehicles. These are the photographs of the discrete components like resistors or transistors. You can also fabricate circuits made out of discrete components. And they are slower because the circuit will be bigger. But the advantage of a discrete circuit is that if some component gets damaged, and if you can identify the part which is not working, you can perhaps repair it. But the repair of an integrated circuit is not possible. So what are the processes involved in fabricating ICs? As I mentioned in the beginning, the first process is silicon wafer. You need silicon wafer, electronic grade silicon wafer. And then you will have to deposit some other materials. So you need techniques like MOCVD, MBE to do epitaxial growth. Oxidation. You know, the most important or most common part in any IC is MOSFET, metal oxide semiconductor field effect transistor, in which we are having a source, drain, and a gate. And there is a channel between the source and the drain, and there is an oxide layer which isolates the channel from the gate. And when you do this isolation, you increase the input impedance. When you increase the input impedance, your device becomes low power device. It consumes lesser power. Its input impedance is higher. So that is a better device for amplifier applications. So oxidation is an essential step. And silicon has a remarkable property that it can be oxidized. It can be oxidized to silicon dioxide just by exposure to air, oxygen, or steam. So we can do wet oxidation, that is done or we can do dry oxidation with oxygen. And then we do lithography. This is the most important step, one of the most important steps in the IC fabrication, where we copy a pattern from one surface to another. So your silicon wafer may be 30 centimeters in diameter, and out of that silicon wafer, hundreds of silicon chips can be fabricated. And all those silicon chips are fabricated simultaneously. So we copy one pattern on several parts of the silicon wafer. And this technique of copying the pattern, that is a circuit, from one surface to another, is known as lithography. If you use light, visible light, then it is known as photolithography. If you use UV light, that is also light, but that is known as UV lithography. We can do lithography also with electrons and also with the X-rays. Another process is diffusion. You want to create N-channel silicon or P-channel silicon. So we have to dope the silicon with boron. So if you want to do boron doping, you will use a gas like diborane, B2H6. If you want to do doping with phosphorus, you can use phosphine. So diffusion is one very important step. And because diffusion happens only at high temperature, so the process of diffusion is done by heating a silicon wafer in a gaseous atmosphere of diborane or phosphine or arsine at elevated temperatures of about 800 degrees Celsius or 900 degrees Celsius. And you can create one particular diffusion profile. You can create a Gaussian diffusion profile. You can create a error function type diffusion profile, depending upon the surface conditions which exist on the wafer. ion implantation. This is the technique again used to do doping. So we have a accelerator which accelerates, say, phosphorus ions or antimony ions or aluminium ions, and you can inject those ions in your wafer. So here you have a much better control over dopant profile. Then isolation, you want to isolate one component on an integrated circuit from another component. So we create a layer of silicon dioxide between them, because silicon dioxide is an insulator. And metallization, you have to make contacts, you have to interconnect the devices on the integrated circuit. So that is done using materials like aluminum or metal silicides like tungsten silicide or cobalt silicide or platinum silicide. And then, of course, there is a final step of packaging and testing. So any single silicon wafer may yield few hundred integrated circuits. And the yield is, of course, never 100%. It is maybe 99%. That is the mastery that we have attained today, that the yield of a single silicon wafer may be 99%. That means 99% of the ICs fabricated are in good condition, they are in working condition. So as I mentioned, photolithography, how is photolithography done? The aim of photolithography is to copy a pattern from one surface to another surface. So the surface is, of course, silicon, and that silicon surface is coated with photoresist. And we are having a mask. This is the mask. And mask has certain transparent regions and certain opaque regions. So photons, HNU, they fall on the mask and they expose the photoresist covered silicon. And photoresist are of two types. One is a positive photoresist, other is a negative photoresist. In the positive photoresist, wherever light will fall, that area will become soft. In a negative photoresist, wherever light will be falling or exposing, that area will become hard. So after you have exposed the photoresist with the light or visible light or UV light or X-rays or electron beam, you put it in a developer solution. So if it is a positive photoresist, the exposed region will be washed away and the unexposed region will be left. So this is how you will create a pattern on the silicon wafer. So on the right side, I show this diagram where we are having this mask, and this is what is known as the projection lithography, where we project the pattern design on the silicon wafer using arrangement of certain lenses. You must have heard of this company, ASML. It's a Dutch company, and they are the world leaders in making deep ultraviolet photolithography system. Can you hear me clearly?
Yes, sir, you're audible.
Okay. I was just checking. Sometimes the internet connection gets lost.
No, very clear, sir.
Okay. So this is the photograph of a typical deep ultraviolet photolithography system. ASML, they are the world leaders in manufacturing this unit. You know, most of the chip manufacturing is being done in Taiwan. And now, of course, India is also setting up chip manufacturing plants. And any company which wants to make VLSI chips, very large scale integration chips, it must have this machine. And recently our Prime Minister, Shri Narendra Modi ji, he visited Holland, Netherlands, and he signed an agreement to get some of these machines in India for our IC fabrication plants. So I come now to nanomaterials. You have heard of these materials a lot of times. Nanomaterials are commonly defined as materials in which the crystallite size or the size of the particles is less than 100 nanometers. You know, electrons, they have a wave nature also. They have a dual nature. And when you see wave nature of electrons, then you see quantum effects, the quantum size effects. The effect of size of a material, on the optical band gap, on the magnetic properties, and also on the mechanical properties. So when the size of a material is less than 100 nanometer, then we say a material is a nanomaterial. So 1 nanometer is very small. 1 billion nanometer is equal to 1 meter. So 1 nanometer is 1 billionth of a meter, 10 raised to the power minus 9 meters. And what is nanotechnology? It is basically mechanisms that have been built by nanoscale components, by using to place every atom or a molecule at a desired place. We will put atoms or molecules at a place where we want them to be put. So that ability to manipulate the atoms at the atomic level or at the nanometer level, that is nanotechnology. And this idea was first given by Richard Feynman in 1959 when he gave a lecture by the title, "There is plenty of room at the bottom." He meant that there is a lot of scope for manipulation at the atomic level. And by creating novel structures, by manipulating the position of atoms at a length scale of few nanometer or few angstrom, you can create novel structures. And there are two approaches basically to make nanomaterials or nanostructures. One is top-down approach. You take a bulk material and break it, keep on breaking it and until you reach nanometer scale. Or the bottom-up approach. For example, when you grow thin films, you grow a thin film layer by layer, atom by atom. In atomic layer deposition, you grow it atom by atom. So very small rates of depositions are there in ALD technique. Similarly, in molecular beam epitaxy or MOCVD, metal organic chemical vapor deposition technique, you grow epitaxial films, atom by atom. So the film is single crystal and it has structure which is same as that of the substrate. So that is the bottom-up approach, thin film deposition. So top-down approach is analogous to making a stone statue. You start with a stone block and using hammer and chisel, you break it and you make a design. So this causes wastage of materials. The fibers or the wires, the copper wires or the fibers which we use in our textile industry, they are used by this, they are fabricated by top-down approach. Bottom-up approach is like building a house brick by brick. So you establish bonding between the atoms, covalent bonding or metallic bonding. And this is how we prepare thin films, bottom-up approach. This is the photograph of carbon nanotube, originally discovered as product of fluorines. And they are one-dimensional materials. Their length may be few microns, but their diameter is few tenths of nanometer. So there is confinement of electrons in 2 dimensions, and electrons are free in 1 dimension. And whenever you confine the electrons, you quantize their energy states. And whenever you quantize their energy states, you will see quantum mechanical effects. Only certain discrete energies will be possible. So carbon nanotubes, they are made out of carbon. You can imagine having a sheet of graphite and you fold it and join it. So what you get is a carbon nanotube. It may be single vault, it may be multi-vault, and you can prepare carbon nanotubes, CNT, by chemical vapor deposition techniques. Here, for example, they are using a laser ablation method. They are having a laser like carbon dioxide laser, CO2 laser, and there is a graphite target. Graphite is carbon, and laser impinges the graphite target, heated to a temperature of 1200 degrees Celsius. And inside this, we are having argon atmosphere so that carbon doesn't oxidizes. And when laser is incident on the target, it causes ablation. That means whatever is there in the target will come out. And you will see carbon nanoparticles fluorines and carbon nanotubes condensing on the inside of this CVD chemical vapor deposition chamber. So this is one of the processes by which CNTs, now they are being made in bulk by industries. How to prepare gold nanoparticles? Gold is a metal. In the bulk form, it is a very good conductor. And we can synthesize gold nanoparticles by simple colloidal particles. You can take aqueous solution of chloroauric acid, HAuCl4, and very dilute solution of chloroauric acid, HAuCl4, in which there are hydrogen ions and AuCl4 negative ions, and add a small amount of PVA, polyvinyl alcohol. So this PVA will act as a reducing agent, and you will get colloidal solution of gold nanoparticles and other compounds. So PVA acts like a reducing agent and also as a capping agent. It will surround your gold nanoparticles and it will not allow the size to grow beyond a certain limit. So I can control the length and the width of these gold nanoparticles, and you can get these colloidal solutions, which are shown here in these test tubes of different colors. And if you take their UV visible absorption spectra, you will see this absorption peak around 530 or 520 nanometer. So by controlling the shape, the aspect ratio, L by W ratio, you can control the optical absorption spectra of the gold nanoparticle colloidal solution. I can prepare quantum dots of semiconductors like cadmium sulfide by chemical methods. And here you see quantum dots of cadmium sulfide suspended in some solvent, colloidal solution, and their color is different. This is, the upper one is blue color and the bottom one is reddish in color. This is because these colloidal solutions of cadmium sulfide, they are having cadmium sulfide particles of different sizes. If the size is more, the band gap of cadmium sulfide will be less. If the size of the quantum dot is smaller, the band gap is higher. So you can see the variation in color of each solution, illustrating the particle size dependence of the optical absorption for each sample. In a solution having smaller particles, that appears to be reddish in color, because if the particle size is smaller, the band gap is larger. So it will not absorb red light, but it will absorb blue light. So the solution will appear reddish in color. Whereas the topmost solution in this bottle is bluish in color in the transmission light, because these nanoparticles are bigger in size, so their band gap is larger. So UV light is able to pass through it, but red light is absorbed. So you can see, you can tailor their optical absorption properties just by controlling the size of the nanoparticles. So some of the machines or equipment which are being used for characterization of materials, once you synthesize your material by bottoms up or by top down approach or by other methods, by Swarovski method, those are of course bulk materials. We have to characterize those materials. We have to study their surface morphology. So we can use electron beams. You can accelerate the electron beams, and these electron beams, they fall on your sample, which should be conducting sample, and they cause secondary electron emission. You can generate an image of the surface using this secondary electron emission, and you can easily have a resolution of 1 to 10 nanometers in a modern day state-of-art field emission scanning electron microscope. This is the photograph of a FESEM with the EDEX attachment, and it's a Zeiss system. So you are having an electron source. The electrons may be generated using tungsten filament or lanthanum hexaboride filament, or it can also be cold field emission type of a gun. You focus these electrons by using lenses, and the lenses are magnetic lenses, and these are the apertures. So this high energy electron beam having an energy of say about 1 to 30 keV, it will raster scan the sample, and it will emit secondary electrons from the surface and also X-rays. These X-rays you can use to study elemental composition of the samples, and the secondary electron emission or the backscattered electron emission, it can generate image of the sample surface. So if you want to study the surface morphology, whether the sample is rough or whether it is smooth, you can use field emission scanning electron microscope. And the present day state-of-art FESMs, they cost around 2 crores. And in India also, now a company has come up where they are indigenizing the manufacturing of these analytical machines. Because when you want to characterize your material after synthesis and processing, you must have analytical tools like transmission electron microscope or an atomic force microscope or a field emission scanning electron microscope or an X-ray diffraction system. These machines are imported, costing several crores of rupees. So now companies are there in India which are offering AFM as well as an scanning tunneling electron microscope at a cost which is 1/10 or 1/20th of the cost of the imported systems. So there are large number of detectors like secondary electron detectors, backscattered electron detectors, EDS for composition analysis. And then there also may be attachments like cathodoluminescence. When the electrons, they impinge on the sample, they can cause the emission of light. That is the phenomenon of cathodoluminescence. So you have to prepare the sample before analysis in a FESM. Your sample must be conducting. So this is a typical mount, sample mount that you may use in your FESM. These are the stubs on which you place the sample. And if the sample is not conducting, you have to provide a conducting path of carbon paste or silver paste or gold paste from the top to the bottom, so that there is no accumulation of the primary electron beam. This is a photograph of a typical transmission electron microscope. In a transmission electron microscope, the electron beam is accelerated to much higher kinetic energies of the order of 200 keV or 400 keV or even more, 400 kilo electron volts. And this high energy electron beam, it passes through the sample. So this is a microscope which works in the transmission mode. Just as you are having optical microscopes which work in the reflection mode as well as in the transmission mode. So in a TEM, we use the wave nature of light, wave nature of electrons. So again, we are having an electron gun, and these electron guns, they accelerate electrons up to say 400 keV or 200 keV or even 1 million electron volts. And you know, electron has a wave nature. Their wavelength is very small. The wavelength of a electron of kinetic energy of 50 electron volts is about 1 or 2 angstrom. So if you are having electron beam of kinetic energy, say 400 keV, its wavelength will be a fraction of a angstrom. And smaller the wavelength, more is the ability to see small things. So the resolution will be higher. So TEM can see very small features. You can get subatomic resolution with a transmission electron microscope. You can easily identify the crystal planes using a transmission electron microscope. These are some of the TEM pictures of biological samples like blood cells and mitochondria, Golgi bodies which are there in your cells. And again, for TEM, you have to prepare the sample. The sample must be very thin. If you want to study a thin film, you will have to do ion milling to thin it to a thickness of say few thousand angstrom or few hundred angstrom. and place it on a carbon coated grid so that the electron beam can pass through it. And you can study the atomic structure. You can see the crystal planes with the transmission electron microscope. Another instrument which we material scientists, they extensively use is the atomic force microscope. So is my time up or can I continue for some time?
Yes, sir. So for 5 minutes, 5 to 7 minutes.
Okay, okay.
Thank
So
you.
this is another instrument, atomic force microscope, where we measure a force, van der Waals force between the tip and the sample surface. And this force moves the tip up and down. So you can study the topography of a material using atomic force microscope. This is the basic arrangement. This is a tip made out of silicon. This is a cantilever. So tip experiences a force between the atoms of the tip and the atoms on the surface. And there are different modes. The contact mode where the tip and the sample are in contact, or in a non-contact mode, or a tapping mode where you are touching the sample periodically or intermittently. Scanning tunneling microscope can be used to study conducting samples, where we measure tunneling current between the conducting sample surface and a tip made of a platinum. So an AFM can be used to study all type of materials, insulators as well, but an STM, it can study only conducting samples. So people in IBM, they made this quantum coral for the first time in 1995 in IBM labs, where they used a low temperature scanning tunneling microscope to place atoms of cobalt on a single crystal surface of copper. So they made this quantum coral of the diameter of, say, about 50 angstrom. And copper has free electrons.
Sir, I think there is some problem with your network.
There.
Yeah.
So shall I stop, Nupur?
Yes, sir, you can summarize your current work in 1 or 2 slides.
Okay.
So that we can open the session for
Yeah.
questions.
So there are other important techniques like XRD, used to study atomic structure, and Raman spectroscopy, where we study inelastic scattering of light and we get information about short range structure of materials, and it is extensively used by gemstones and pharmaceutical industry. If you want to distinguish an artificial diamond from a natural diamond, Raman spectroscopy is the only technique. We can use neutrons, and we are having reactors in India at BARC. Neutrons are also elementary particles, and they have a magnetic dipole moment also. So they are extensively used to study both atomic structure and magnetic structure. We are having synchrotron radiation sources at Indore and also elsewhere in the world. And you can do XRD in a matter of few minutes. XRD machine will take about 2 hours or 3 hours to record a diffraction pattern, but you can do XRD in a synchrotron very rapidly and with very high intensity. So if you want to progress in space program, in defense program, you need materials, variety of materials, hard materials, high temperature materials, magnetic materials. Silicon, of course, is needed to make ICs. And so careers in material synthesis and processing is everywhere, in healthcare, in space program, in civil aviation, in railways, IC fabrication, manufacturing, textiles manufacturing. Textiles are also dealing with materials like nylon or polyester or polyviscose. And there is a big area of renewable energy sources like wind power and solar power. And we need batteries to store energy because the renewable energy sources are not always available. Wind and sunlight is not always available. So we need batteries. We need cathodes, we need anodes, we need electrolytes. So in 2019, a Nobel Prize was given in chemistry to Whittingham, Goodenough, and Yoshino for the development of lithium-ion batteries. So the present-day lithium-ion batteries, they use electrolyte, which is a liquid. We would like to have an electrolyte, which is a solid. So there is a big search. A lot of active research is going on in solid-state electrolytes. One area is rare earth magnets. In any electric motor, you need a magnet. So we use magnets which are very small in size and which are very powerful. So these are the rare earth magnets. This is one of the thrust area of Government of India. 5,000 crore rupees have been earmarked for the manufacturing of rare earth magnets in India. And recently in Bangalore, a startup announced by the name of Vimac, where they reported the fabrication of an electric motor without using rare earth magnets. So basic science provides impetus to technology and societal growth. The fruits of basic science that we did last century, one of the most important fruits is the microelectronics industry. So microelectronics industry was not possible without understanding solid-state physics deeply. And it generates technological spin-offs. Material synthesis, processing, and devices technologies, they are key to realizing the dream of having Viksit Bharat by the year 2047. And the present-day problems in India, such as overpopulation, sanitation, pollution, job creation for youth, they can be tackled by materials innovation and boost to manufacturing industry. So any sort of manufacturing industry, it deals with materials synthesis or processing. So materials innovation mission, it will play a very important part in realizing our dream of all Indians to have a developed India, Viksit Bharat, by the year 2047. So we have to set our goals and really work hard, work as a team. In India, we try to work individually. We are not ready to share our gains or profits. So we should learn to work in team and in synchronization, and we can surely achieve our targets. So thank you very much. Thank you.
So thank you so much, sir, for this inspiring talk. You really took me down memory lane. And I'm sure all present here must have very easily correlated themselves with your lecture, with you starting with de Broglie, then coming over to crystal growth, wafer production, integrated circuits, fabricating monolithic ICs, photolithography, nanomaterials, also mentioning gold here, and then there's synthesis, STEM, and obviously, sir, one question which we are getting in our WhatsApp group, and I would like to end with that is, what role do you think AI will be playing in this field? Because we can see the creeping of AI in almost all fields everywhere. So can you just, in short, with your experience?
Yeah, AI, as I think, or as I understand, is we have a lot of database for all type of materials. We have their compositions, we have their data on their magnetic properties, electrical conductivity, hardness, optical properties. So AI can predict compositions which might have some very novel properties. So it can shorten your work. I mean, it can provide a shortcut instead of trying all the materials one by one or sequentially. So it can pinpoint that which material composition will have which desirable property. If you are, for example, trying to prepare a very hard glass, as we do it in our laboratory, we have prepared large variety of borosilicate glasses and introduced different type of metal ions in them. So we have a data of about, say, 100 or 200 glass compositions. But if you see a literature, they have a database of thousands of compositions. So AI can help you to develop correlations, structure property correlations. So this is, I mean, what I feel AI can help a material scientist. It can predict the compositions which can have desirable properties.
And sir, I think in this field and your this interesting and inspiring lecture, I think quantum computing can also play a very major role here with this work.
Of course.
You agree to that?
Yeah, quantum materials is now one of the thrust areas of Indian government.
Yes, you mentioned in your lecture also, which I was hearing.
Yeah.
Yes, you have mentioned
there is
about
a national quantum mission. National quantum mission aims to have basically 3 parts, in which one part is, of course, quantum computation, and
Yes.
one part is cryptography. That means communication, safe communication of the useful information. And the other part is quantum devices, to make very small and sensitive devices which can detect very small magnetic field, very small temperature, very small, say, pressure. So this is again a result of our understanding or achievements in quantum science. But how far we have, achieved quantum computation, I'm not an expert in that. But definitely, this is be playing a big role. It will provide impetus to other sciences, to other technologies also.
Okay, sir. So thank you so much. And lastly, when you mentioned about Viksit Bharat, so will the government finance us with gold, where they are saying not to buy gold? And you have mentioned gold nanoparticles.
Yeah, gold, I can finance gold, no problem. I can give you some amount of it.
Thank you so much, sir. Thanks a lot. Thank you so much, sir. I would personally like to thank you for being here and like with one invite. I know you have to take out time from your schedule, and I'm really grateful that you said yes to when I requested you to be the part of this Physics Industry 4.0 Global Summit. Thank you, sir.
Nupur, there are 1 or 2 questions in the chat box also. If
Yeah, please go ahead.
So first question is, given the high cost of STEM, are there any affordable characterization techniques that can provide comparable information about size, morphology, and distribution of nanoparticles?
No, I didn't understand clearly. Can you repeat?
Yes, we know that STEM is very costly, like scanning electron microscopy is very
Yes,
costly. So are there any affordable techniques to provide the similar information of size, morphology, and distribution of nanoparticles apart from STEM?
Yeah, actually, if you want to study the size distribution of the particles, other techniques are light scattering, dynamic light scattering, but the resolution is less. Here, the resolution is less in dynamic light scattering, and it is possible only for colloidal solutions. So FESEM you can actually use nowadays. There is a large number of centers which have been established by IITs, and the cost is not so high. They typically charge about few hundred rupees, maybe 700 rupees or 800 rupees per sample. So it is not such a prohibitive cost. And if you want to study morphology, composition, surface morphology, then SEM is the only technique. Surface morphology can also be studied using atomic force microscopy. Using AFM also you can study atomic force, the surface morphology. But if you use FESEM, You can do morphology studies and composition studies simultaneously. So there are large number of centers, consortiums like UGC, DAE, CSR. So they don't charge anything. You have to write some proposal and you can go to their UGC, DAE, CSR Indore Center. They are having AFM, FESM, TEM, UP, XPS, everything they are having, Raman scattering, and there are no charges. You have to write a proposal and you can use it free of charge. I think Nupur has also used the CAT facilities, the Indus 2 in 2018. So there were no charges. In fact, they paid you travel allowance also. So you have to write a good proposal, and there are international facilities also. We have used the facility by the name of CERIC, Central European Research Infrastructure Consortium. There they are offering NMR, neutron diffraction, this synchrotron X-ray diffraction, battery materials characterization free of charge, and they give you air ticket also.
Right.
So you can plan a good proposal. We have used CERIC funding, and I went with my student daughter in 2023, and it was all paid. So we had a good time. So you have to write a good proposal. So people will offer you collaboration free of charge. No need to pay any charges.
Sir, one more question is there. I'll take this as the last question. Like you talked about semiconductor manufacturing plants. And
Yes.
so what do you think will be the biggest challenge in making India self-reliant in chip manufacturing?
Yet once we start fabricating
Yes,
integrated circuits, so because ICs are being used in everywhere, in defense technologies like missiles, in weapons, in your microwave oven, in your laptop, mobile phones, missiles, everywhere. So in automobiles also. So we need not make silicon wafers. We can import silicon wafers. But once we start the various processes like lithography, oxidation, diffusion, which are all the steps involved in the fabrication of IC, then we will be self-reliant. We are now becoming one of the major producers of ICs in India. And in the next 5-10 years, due to the thrust given by the central government, we will be in a very good position.
Okay.
We have to train also the manpower who can do these processes.
Okay. Thank you, sir. Thank you for attending to the questions of our participants. Please stay connected because now we are proceeding with our final session segment, that is our panel discussion, right?
Okay.
So now this is the most anticipated segment, I think, of today's summit. We have been preparing for it a lot. The panel discussion. So the theme of the session is Bridging Academia Industry Gap in a Physics-led and AI-driven Innovation. As the world rapidly embraces AI, advanced manufacturing, quantum technologies, and smart industrial systems, collaboration between academia and industry have never been more important. This discussion will explore how physics-driven research, technological innovation, and academic excellence can work together to address the real-world challenges, accelerate technology transfer, and prepare the next generation of scientists and engineers for an innovation-driven future. It is my privilege to introduce our distinguished panelists. We are delighted to once again welcome Professor Atul Khanna, Department of Physics, Guru Nanak Dev University, Amritsar, whose engaging talk earlier today emphasized how material physics is shaping the future of industrial innovation and technological progress. Joining him is Professor Manmohan Singh Sisodiya, Head, Department of Physics, Gautam Buddha University, Greater Noida, who earlier delivered an engaging talk on how photonics is driving innovation in smart manufacturing and next-generational industrial technologies. Now, it is my pleasure to introduce our other esteemed panelists. Our next distinguished panelist is Dr. Deepak Kumar, Managing Director of Vimentix Technologies Private Limited, a technology entrepreneur and industry leader. Dr. Kumar has an extensive expertise in artificial intelligence, software engineering, digital transformations, and Industry 4.0 technologies. Through his leadership, he has been instrumental in developing AI-driven solutions that bridge academic research with industrial applications, making him a strong advocate for innovation, entrepreneurship, responsible technology, and deployment. Our next distinguished panelist is Dr. Pawan Kumar Tripathi, a researcher in computational science and artificial intelligence group at the US National Laboratory. His research lies at the intersection of AI, high performance computing, material science, and advanced manufacturing, where he develops AI powered systems for accelerated scientific discovery. His work includes agentic AI, digital twins, and automated image analysis for advanced material research, helping transform complex scientific data into actionable insights. He is an adjunct faculty at Case Western Reserve University and currently serves on the editorial boards of scientific reports and integrating materials and manufacturing innovation. We are privileged to have all the panelists present among us. And now it is my privilege to have Dr. Pratima, Assistant Professor at Department of Physics, JSS University, Noida, as the moderator for today's panel discussion. Dr. Pratima has been serving JSS institutions since 2010 and brings over 15 years of teaching and 11 years of research experience. Her research focuses on plasmonics, nanophotonics, and optical energy conversions. A Young Scientist awardee, she has published several papers in leading national and international journals and is a holder of published Indian patents. She is passionate about interdisciplinary research and mentoring young researchers. With her academic expertise, insights, and perspectives, I now invite Dr. Pratima to kindly moderate this panel discussion. Over to you, Dr. Pratima.
Thank you, Dr. Nupur. Am I audible?
Yes.
Good afternoon, everyone. It's my privilege to welcome and share this platform with my senior supervisor for today's panel discussion on the theme, Bridging Academia Industry Gap in Physics-led and AI-driven Innovation. We are living in an era where breakthroughs in physics are driving advances in semiconductors, quantum technologies, renewable energy, advanced materials, photonics, and healthcare. At the same time, the artificial intelligence is transforming the way we conduct research, design products, and solve complex industrial challenges. However, one important question remains. How do we ensure that discovery made in our laboratories become technologies that create real impact for society and industry? Today's discussion aims to explore exactly this question by bringing together distinguished experts from academia, research laboratories, and industry. So let's begin our discussion. I would like to begin with Professor Atul Khanna. Sir, many outstanding research papers are published every year, but only a small fraction eventually become technologies or commercial products. From your perspective, what are the major barriers in translating physics research into industrial innovation? I think most of us are facing the same problem in this. Sir, over to you.
Clearly. Couldn't hear the question clearly. Anyway, I will give some of my remarks. Can you hear me? Can you hear me?
Yes, yes.
Yes, sir. Yes, sir.
Okay. See, in India, chemical industry is very much developed, but the physics-related industry is much less developed, and that is why physics graduates also don't get many job opportunities compared to chemists or pharmaceuticals graduates. So, can you hear me? Can you hear me?
Yes. Yes, sir.
Yes, sir.
Okay. So the physics-related industry is mostly electronics industry, device fabrications, discrete devices, or the integrated circuits fabrication. So now we are coming up. Maybe in the next 5 years, we will see a big change in the employment of physicists. The physicists that we produce from our colleges or universities or other institutes. And presently, most of the graduates, they go for higher studies. And in physics research, or in particular, the focus is mostly to get a publication. And see, for example, in India, very large number of groups are working in the areas of batteries, supercapacitors, or such related energy storage devices. And the main aim, or in fact, the primary aim, is to get a good publication with a high impact factor. So people have not really gone to the extent of actually making a device. So if you want to commercialize a device like a battery or a supercapacitor, you must reach a certain threshold. Your battery or a supercapacitor must have a certain minimum energy storage capacity or current capacity. Only then it will be marketable. So first, our researchers working in physics labs, in material sciences, they have to focus or design their research in such a way that they achieve a certain critical threshold, which is acceptable by industry. Just by publishing papers or in high impact journals, that is not going to make a difference. So we have to reorient our research activities in material sciences, and we should aim to achieve a particular threshold in a material or a device that we are trying to fabricate. So with this, I would like to start the discussion.
Thank you, sir. Could you share an example for your own experience, sir? Any example, sir, from your own experience?
Yeah,
Can you hear me, sir?
Yes, I can hear you.
Yes.
So there are many examples. You see, open any journal, you will see very large number of papers in which they have reported very high energy capacities, very high current densities. But can we actually make a device which is comparable to, say, a lead acid battery or a dry cell or a lithium ion battery? So we have to reorient our materials research so that we achieve a particular threshold from the device point of view. It may be a battery, it may be a supercapacitor, it can be some other magnetic energy storage device, it can be anything. So researchers have to create a certain threshold, not just work from the point of view of publication.
Thank you, sir. That provides an excellent academic perspective. I would like now hear from other panelists also. Pawan sir, would you like to give your points?
Hi, everyone. Thank you for inviting me into this panel. It's 4 a.m. in the morning here. So, yeah, I think this is a very interesting conference and I think very relevant for today's days. So, bridging kind of AI and like physics for industrial applications. So I'm very pleased to be here. And in my opinion, so can you kind of get back to again, like what was the original point of discussion, like question? So sorry, I might have missed that. So I just want to kind of need a little more clarification on that. So
many outstanding research papers are published every year, but only a small fraction eventually become technology or commercial products. So what are the major barriers in?
Yeah, so I think as our previous panelist said, we see a lot of very good research papers nowadays. And so I think the problem is two-way. So there are definitely good research papers which are just talking about science. So they itself are like very informative and kind of very good in that sense. But then the research that is targeting to like a kind of a real or industrial applications, so which might not be like true for all the research that we are seeing coming along. But even after looking at the scale of these papers, we do see like I mean they are converting into an industrial product. because I think we need some more entrepreneurs coming up and taking those ideas and kind of scaling on that front. So that is one of the, I think, major thing that people want to pursue. So industries and I think academic institutions like GSS, so where I think we need to train people in these specific research areas which are kind of very relevant in modern days. So for example, nowadays we see a lot of applications where AI kind of combining with different types of science and tech areas. So we need to train our students, PhD students, masters, undergrads. So they all should have like at least a few projects where they have worked on some real data. And I mean, this should be like domain specific. So AI is like a general term, but they have to be combined with different areas, even like say in physics. So I mean, there is concept of these autonomous labs, and this combining with solid state research with quantum and everything. So we need to train our young generation into that, which is, I think, the path to go.
Yeah. Thank you, sir, for those insightful perspectives. So, building on this discussion, let's move on to our second question. I would like to invite Professor Manmohan Singh Sisodia, sir. Sir, India is rapidly investing in semiconductor technology, quantum technology, renewable energy, and AI. In your opinion, what should India's roadmap look like to become a global leader in physics-driven deep tech innovation?
Good afternoon, everybody.
Good afternoon, sir.
The roadmap chosen by the government, I think the roadmap is chosen by the government after due process. Now, where is the physics now? I believe any mission of the nation that will be governed by our original thinking and solving the problem of, let us say, our country, our region, or our state. So, as far as physics students are concerned or physics people are concerned, obviously, fundamental research, it is open in all sectors, and government, obviously, it is pouring a lot of money also. But we cannot keep aside the fundamental research. We can think about, let us say, a research topic based on what others have done, or let us say what others are already working. But definitely, probably we have been somewhat reluctant about choosing our research topic or choosing our research theme, that it should be driven by the need of our country, and also about the innovation, that there should be an innovation and it should not totally be based on what literature has been publishing and just picking some gaps. So the new ideas, obviously, being a physics student, being the fundamental science student, our aim should be like finding new ways of solving old and existing problems. And obviously then it could be material science, it could be semiconductor technology, it could be nuclear technology, and obviously it could be nanotechnology. But fundamental thinking is inherent, and obviously physics student, they should always think about optimum solution of word problems, and while choosing word problems, our problem of our country should be inherent in those problems. Thank you.
Yes, sir. What do you think, what policy changes would help in this?
Since last few years, I myself has observed so many policy changes. One change is, let us say, new national education policy, where a lot of flexibility in designing courses, more emphasis on industry, academia collaboration. Now, most of the institutions, they are approaching industries and they are inviting industries, they are welcoming industries, and I think same thing is also happening on the industry side also. And government as well as other sectors are basically giving the projects where it is compulsory that both academia and industry are involved. So probably it will reduce the gap that has been existing since so many years. So curriculum design, like having MOUs with industry, MOUs with academia, and choosing the research problem or the research theme in tune with the requirement of the industries, and in turn, obviously, the problems of the country. So that process probably has started and it is speeding up also. You can see that a lot of number of patents now continuously increasing, industry, academia, conferences, collaborations. In fact, center of excellence industries are funding center of excellence in academia at IITs, at different universities. Now industries are funding those center of excellence. Probably this is a good beginning, and maybe there's a need to accelerate that. Thank you.
Thank you, sir. That gives us a broader national perspective. Because, sir, what is your perspective as an industry point of view?
Deepak sir.
Sir, you are muted, sir. Yeah. Thanks.
Hi everyone.
Yes.
Good afternoon. So as per my personal experience, while doing research in the earlier years, what I observe is as we work in a laboratory, there are limited number of consumables available, and we can only try a certain number of sets, which may or may not give you the exact answer that we are seeking right now. So as an industry, what we can expect is that we need to finish that particular task in limited number of resources, where AI can help us in identifying the wrong use cases automatically before proceeding to that experimental part. So now what is happening is we formalize a particular phase where we formalize the problem, which is basically termed as market research in industry. So we do a market research as what is required in the market. Then we collect a lot of evidence to support our hypothesis, and then we give that particular hypothesis to AI to shortlist certain best 5 or 6 uh, outcomes which can be generated in laboratory itself. So in this way, what you can do is because what we have understood it that there are certain resources which are available on a shared basis in IIT or CSIR laboratories, which will get an appointment at very short duration of time for after waiting for a very long duration. So the only problem is you have to identify exactly the actual use case and eliminate all the irrelevant use cases much before utilizing your consumables or utilizing your efforts in doing that particular research. So as a material scientist, we have to figure out what is required in the market right now. So there are multiple sensors used nowadays, and the sensors are basically used in different purposes. So before starting any research in material science, because I am a chalcogenide glasses expert, so if I will be given an opportunity again to do the research in chalcogenide glasses, what I will do is I will go to different industries first, ask them what are their requirements, what kind of band gap they are looking for.
Deepak sir, you're not audible.
There is a net issue from the side.
Hello.
Unmute.
Yeah.
So please unmute yourself, Deepak sir.
Yeah. Can you hear me?
Yes.
Am I audible?
Yes, sir.
Hello.
So one thing I would like to say is that Indian researchers must learn to work in teams.
Yes, sir.
We are often not ready to share our results or collaborate with other persons because we think we want to get all the gains. So we should work in teams and not try to get all the equipment in our own lab. You need not have all the equipment in your own lab. You can use the other researchers' equipment because many equipment are now becoming very costly, costing 80 lakhs, 90 lakh rupees, and funding agencies can't sponsor individual projects. So you can share and form teams at IITs or other universities. And it is a duty of a researcher, the supervisor, to check the quality of data. The data quality also needs to be checked by the professor or the researcher because sometimes the data is not correct. Students bring something very extraordinary and it must be verified by repeating the experiments. So if you want to commercialize some device, if you want to have industrial collaboration, the data that you report must be reliable. So this is what I wanted to say. Okay.
Thank you, sir, for those insightful perspectives. So, before we move out to our next topic, let's make this discussion a little more interactive. Let's take a quick audience first. We have 3 fun yet thought-provoking poll questions. There are no right and wrong answers, just your perspective. Please vote through the quiz and we will display the live results shortly. The question is, Rohit, please share the screen. So our first question is, if Albert Einstein were alive likely today, which field do you think he would most likely choose to work in? Artificial intelligence, quantum computing, fusion energy, and space technology. Second question is, if an AI system plays a major role in Nobel Prize winning physics discovery, who should receive the Nobel Prize? Scientists who discover, the AI developer, both scientists and the AI developer, and or AI itself should be recognized in a separate category. And the third question is the biggest reason that many graduates are not industry ready? Limited practical exposure, outdated curriculum, lack of AI and digital skills, weak industry academia collaboration. So we will wait for about for the result.
Microsoft form link has been shared in your chat boxes. So you can, for all the 3 questions, you can use the link in the chat box to answer them. So you have some seconds. Please hurry up, participants.
So I think I like the question about the Nobel Prize, which I mean there is already an example. So you might have heard about Google's DeepMind, Demis. So I think I'm echoing somehow. So like recently we got this this field like AlphaFold, that's like a protein folding model. So they already got the Nobel Prize, which was like kind of an AI invention. So so you cannot like give a Nobel Prize to a AI. So it should always go to the scientist who made it possible.
So regarding the first question on Einstein, so Einstein was very intrigued by quantum mechanics. So I think if he is reborn, he may choose the field of quantum computing, which is based upon the phenomena of entanglement and superposition principle. And that was his favorite quantum entanglement. He couldn't accept the quantum mechanics. So I think Einstein will go for quantum computation.
I think the audience agrees with sir.
Yes, sir. 80% audience is with quantum computing. None of them is with fusion energy and space technology. So what are the polling for second question? Yeah. If an AI system play a major role in Nobel Prize winning physics discovery, who should receive the Nobel Prize? So
I think majority goes with scientist and the AI developer. So, but
scientist and AI developer.
yeah. But I think from my personal point of view also, I feel that it is a scientist that who made the discovery, because I'm not a core AI user or a developer. I don't know the backend, but I just know that we train our AI tools to work according to us, right? This is what I know. I think
Yes.
Deepak sir can reflect on it. So if I am using
Yes,
AI to make a discovery, then that means I am training it, right? So that
yes,
way,
yes.
that
AI,
way it is going to give me some results, right? So it has to
yes,
be scientific.
AI is only used as a tool for doing certain parts of the calculations as well as certain part of the literature research. So in the beginning, when calculators came, people start using calculations using calculators. So calculators are not awarded any Nobel Prize for doing the
Right.
calculation. Then we have moved to Excel. We are doing a lot of calculations using Excel. And Excel is only supporting us to do certain calculations. It has not been a part of our research itself. So same thing is going AI. AI is basically an assistant. Whatever you provide them as an input, they will only provide you an output. It will only help you in basically doing a lot of mental calculations as well as a lot of research. It is also assisting us in doing certain part of the research, but whenever we run a laboratory, the scientist alone cannot produce an outcome. It will be assisted by a lot of lab assistants, a lot of supporting staffs, and everything else. But the Nobel Prize still goes to that particular scientist who is basically the main key resource person for that particular research. So whether you use AI or whether you use quantum computing or whether you use some other technology later on in your future, it is the thought process which leads to that particular innovation is the most important thing. So in case of a Nobel Prize, it is always meant for the scientist, not for any other tools that is used to the calculations.
So we see the next question. What are the perspective of audience? What is the biggest reason many graduates are not industry ready? So major are with limited practical exposure.
Just the reason many graduates are not industry ready.
What is your perspective, Manmohan sir?
Outdated curriculum, lack of I believe this is the ecosystem that we have in our country. Actually, the learners, how they think, how they do, what they do, I think it always depends on the ecosystem that exists nearby. That means the ecosystem that exists in our country, probably that is responsible for, let us say, what learners are choosing, what industry choosing. And this is my say.
Deepak sir.
So,
So, not necessarily that maximum people are recommending an answer that will be correct.
Yeah. So, in my opinion, it is the fourth option which is most relevant right now because the industry is moving at a very fast rate. Even the industry persons are not capable to move with the pace in which the industry is leading right now. When they are saying limited practical exposure, it is basically the responsibility of both the learner as well as the university to provide adequate opportunities to learn. And there are a lot of things for physics which can be experienced by their own in the nearby surroundings. So physics doesn't stop anybody to observe or do any kind of experiment because it is not directly linked with most of the setups which are required, highly computational setups which are required for chemistry or biology itself. So if you want to figure out in practical setups where you can apply your scientific knowledge, then there are a lot of things available nearby. There are a lot of it. You can figure out their challenges and then do some theoretical calculations before going into the practical applications. Outdated curriculum, yes, this is always a problem for the last multiple number of years, and right now it is accelerated because AI is also going at a very fast pace. And lack of AI in digital skills, right now, the only problem challenge that I feel right now is in 2000 when the computers are introduced to the normal people, universities offer computer labs where the student doesn't have any computational facility at home. So they can come to university, they can use those computers, they can learn, and only thing that is required is only a compiler or an interpreter. Later on, learners purchase their own computational devices such as desktop or laptop, and they have started using those particular languages to learn on their own. But this is not actually possible with the help of an AI because AI requires a very huge infrastructure in terms of hardware devices as well as huge amount of investment in computational powers, which is not practically possible for every learner because not everybody is of the same economical background. So there will be a differentiation. There should be intervention by the university. There should be some budget for AI related computational power allocated to every student from the university side so that everybody is capable of using at least those AI tools. This is not something similar to one where people download certain softwares and keep on working on those softwares for free of cost. It is a paid technology and everybody has to pay for using it.
Yes, sir. Thank you everyone for participating. That's very interesting. So we'll return to our main discussion. So now I turn to Dr. Deepak Kumar. Sir, my question is this: from industry perspective, what do companies expect from today's physics graduates? Are university producing graduates with the skill that Industry 4.0 demands or not?
Is it for me?
What do industries expect from physics graduates as of now, at present?
This is for Dr. Deepak.
Okay. So right now what we are basically facing is basically the industry is moving into EV vehicles as well as battery energy storage, which is something related to solar power. So what the industry expects is that someone which is coming from a physics background should have a solid knowledge of how to make different kinds of material which can be utilized for developing these kind of applications. So it is basically more of a experimental perspective. They are willing to have certain candidates which are well versed with all the leading technologies. What are the science behind those particular technologies, as well as what kind of laboratory research can be done in those areas, which can easily be converted into an industry application. And it is very easy to convert any kind of battery energy storage technology or a solar energy technology into an industrial application right now, because you can easily convert and there are multiple channels available to market your product right now. So what they understand is you must have a good understanding of physics as well as certain tools to validate your data, do certain practical demonstration of what you have developed, and then they are ready to hire you. Right.
So I may add here, so basically industry wants people, students who can handle instruments. If we are in pharmacy industry, they should be able to handle UV visible spectrophotometers, Raman spectrometer, X-ray diffraction. Of course, they will give some basic training, initial training to the fresh graduates. They want people who are comfortable in handling instruments, machines, equipment. They need not know the theory fully. So they should be happy with the instruments or with the machine. That is what industry wants.
So I can also add few things. From our experience, actually, we at Gautam Buddha University organized few industrial meet. It was a meeting of industry representatives with our faculty members. So I could make out two things. Number one, they want a person, or let us say they want a student who is ready to work for their industry. That means so that they do not require to train the person. Number one. Number two, in addition to the core skill of, let us say, physics or other subject, equally important these days is becoming basically soft skill. Thank you.
And any industry also wants graduates who are mentally tough. They should be mentally tough, not get stressed very easily. So they should be able to face new situations or new challenges. अगर उनका बॉस थोड़ा डांट भी देता है तो उसको मतलब खुश रहना चाहिए. Mental state of health is also very important to be a new learner.
So that is also part of our soft skill.
Yes, definitely.
Thank you, everyone. It is always valuable to hear the expectations from directly industry as well as academia. So my next question is for Dr. Pawan Tripathi, sir. Sir, AI offers tremendous opportunities, but it is also raises ethical and social concerns. How can we strike the right balance between rapid innovation, sustainability, public trust, and responsible use of AI?
Yeah. I think this is a very valid question and concern as well. So the responsible AI itself has, I think, I mean, I should gently push back to this framing. So in all these four issues, so you mentioned about balance between innovation, sustainability, and public trust. So when we kind of stick to more kind of responsible AI aspect, so we always kind of have, for example, when you have high stakes experiments. So, for example, in my own research work, I work at a major synchrotron facility in US, and I develop agentic frameworks for them. So they have, I mean, you always need a human in the loop or something, and you also want your AI should always obey the laws of physics. So I mean, that's kind of validation to make sure the things are heading in the right direction. And on sustainability aspect, I mean, compute cost is really like a design choice, a constraint. It's not just an abstraction. So we need a kind of efficient task-specific models, which are or like massive general ones. So which could be like a default choice in terms of making it sustainable. And a public trust is always important, especially like in scientific field. You cannot compromise on that. So these are like I think core components of any AI developments.
Do you want to say anything on this point? Atul, sir?
Yeah, I'm I'm not such an expert in AI. So of course we have to be careful. I mean, AI has huge data, and ultimately humans are handling those AI machines or database. So we should be careful, ethical. So where AI will lead us to, I cannot say. Difficult to predict. What will AI do for us in the next 5 years or 7 years?
Yeah. So there is
But
a
it is good for us.
So there is a concept of human in the loop, so which is, I think, always essential to make sure we are heading in the right direction. So which kind of validates all the steps that AI is kind of taking, and then yeah, as mentioned, like we always need to know our data, we always need to know our AI framework, we always need to know our computational requirements, our design choices, which kind of shape the development. So that's always kind of coming in the arena of responsible AI.
So what do you think? Should AI literacy and ethics become a compulsory part of science and engineering education?
Yep. So if I look at the institutions in United States, so I think every major institute now provide some sort of AI capabilities to all of their students, or like anyone like a staff or faculty or whoever. So they get access to these at least these big models, like from these major companies, from the Google's Gemini models, Anthropic's Claude, and OpenAI's ChatGPT. So I think that's like a kind of bundle which always students or like university staff can access, and they can play with them. Of course, there is a limit on uses, but I mean there is always like a kind of basic level of access to those models, which kind of gives familiarity to young graduate students, or to kind of understand like how these models work, and then how they can be adapted to the different domains, and how they can kind of shape their learning process over their course time or something.
So one thing I may say here, so the open AI models, they should always be under some human control. I mean, they should not act independently. Then they can interfere with the other companies' internet services, or they can interfere. So some human control or checks must always be there.
Yeah.
Okay. Thank you, everyone. So my next question is for Manmohan sir. Sir, when a breakthrough technology has significant social implications, who should play the leading role in guiding commercialization? Scientists, industry, policymakers, or society at large?
Tima, can you repeat once?
When a breakthrough technology has significant social implications, who should play the leading role in guiding its commercialization? Scientists, industry, policymaker, or society at large? Sir, I have posted the question in chat box also.
So actually, breakthrough is done by a scientist or by a group of scientists. But once an industry is involved, then it will always be in control, because they have to see the financial or the economic aspects. So ultimately, let the industry decide, I mean, how that technology should be marketed or manufactured. Society will not be able to control it unless you make it some kind of a communist society. If it is a capitalist nation, then your company will decide once the technology is transferred to it.
Yes. Thank you, sir. Manmohan sir, what is your perspective? Manmohan sir?
Fatima,
Yes, sir.
can you, not very clear to me.
So the question is also in the chat box. When a breakthrough technology has significant
How there are
social
hindrances?
Yeah, when a breakthrough technology has significant societal implications, who should play the leading role in guiding its commercialization?
The
Scientists,
network somehow.
industry, policy makers, or society at large?
Network issues.
Okay, so till the time Manmohan sir joins us, let us have Dr.
He has
Deepak's
joined.
take on this
Yeah, please.
question. He's joined. Okay.
What is industry people say?
Hello.
Manmohan sir? No. No.
Because
Basically,
Network
there is
here
a
somehow.
breakthrough which is affecting a lot of social environment. So it must be governed by the industry, but there should be a policy which is governing the industry itself. So right now what we are seeing is basically there are a large number of large language models which are used for doing a lot of generation of content which is basically non-ethical, and the companies which are producing those particular tools are giving access to the users because they are earning money from them. But at last, the particular content is hurting certain socioeconomic section. So government is taking basically care of these policies. They will keep on checks on different industries so that they cannot get out of that particular loop. So in US, we've already seen that the Trump government has already applied certain policies on AI models that you cannot use those particular AI models without their usage. We have already seen those on Google Earth maps where you cannot have a Google Earth map of a particular region due to security concerns. So I think there should be first it should be done by the industry, and if the industry is not being able to do contain that particular effect, then there should be some government policies which is mandatory for keeping a tab on what is done with the help of that technology.
Yeah, I would like to add something on that.
Sir?
So recently there was a model called Fable released from Anthropic, and then I think it's just after first release, government just blocked its uses. So and that was not available to public or even to the industries. And then after I think making sure like that and making like some modifications in the existing model, they kind of get to a point where that could be released for public use. So it took almost, I think, a few weeks for them to decide on whether the use will be in kind of their nation's requirement or whatever, like the policies that or like ethical concerns which they might have.
Okay. Thank you, sir. So, sir, what do you think? How should the university redesign their curricula to prepare students for careers at the intersection of physics, AI, and Industry 4.0?
Yeah, as such, our curriculum are not bad at all. Our syllabi are good. So what I want as far as physics courses are concerned, I want students to have more training on equipment, instrumentation, practicals, projects, presentations. So focus should be more on equipment, use of XRD, material synthesis, whatever spectroscopy equipment. So students should be trained in that. And of course, some AI tools also need to be trained. They should have knowledge of that. Now they say programming is not required. Many people say that one need not learn programming because your AI tools can do the programming. You name any program, write a program to find the first 1000 prime numbers, you will have the program. So knowledge of AI tools is very essential. But as far as physics curriculum is concerned, I am for having more focus on practical courses, equipment, XRD equipment, spectroscopes, and so on.
Sir, would you like to add something else?
I do agree with Atulji. See, at one end, at 12th standard and 10th standard, we started, let us say, teaching our students computer science, artificial intelligence, and so many things. On the other hand, hardly any science labs are conducted at 10th or 12th level. And the same tradition then continued in the classes. So I think training of scientists or training of science should be very rigorous, I think, from the school itself. And that practice probably should continue in the university and colleges. Probably then, see, artificial intelligence, I don't think that artificial intelligence is the solution of everything. Artificial intelligence is just, let us say, one tool. And how long it will survive and other alternatives will emerge maybe in next decade. So ultimately, all the solutions, they should be again innovative, they should be again environment friendly, they should be again, let us say, specific for our need. And so artificial intelligence is only one thing that it is like hue and cry maybe for next few years. So the scientific temperament, if at one point of time the country lose the scientific temperament, then I think that will be basically a great debacle for a country. Need to keep that thing alive if we have to win competition at the world level. Thank you so much.
Thank you very much, sir. So, Pawan sir, what do you think? What new skills and responsibilities will define the physicist of the future?
What new skills and responsibility will define the physicist of the future? Yeah, I think the core knowledge in physics is very essential. And then, of course, AI and other skills, they are definitely useful. And students, especially like in core areas of physics, whether it's solid state physics or quantum or like semiconductors or advanced manufacturing, they need to know like their domain specific adaptation in like of these AI tools. So we might have kind of very much exposed to these general purpose models like ChatGPT or Claude, but we need to have our students thinking about domain specific problems, whether it's like in 2D materials, in nanomaterials, in high energy physics or wherever. And then people who kind of understand those problems very well, they get into the domain, they kind of knows all the pros and cons and what's happening in that area, what are the major challenges, and then see like how AI tools can generalize on those real problems, which might like accelerate the kind of problem solving skills in those areas. So I think again it goes to the basics. They need to learn like the basic and essential skills in their domain, and then kind of combine it with the AI tools, and that's the way to go, in my opinion.
So, Deepak sir, with AI becoming an integral part of scientific discovery, how do you see the role of physicists evolving over the next decade?
So physics is already part of every kind of science that we normally use, whether it is electrical, electronic, or it's mechanical. So physics, as a physicist, what I see is basically it is getting much easier for us to do research right now, because there are certain assisting tools which can help us do certain kind of tasks which are basically not possible earlier. Earlier, when we are in the laboratory, there are certain digital tools which can take readings and we can record those readings automatically. But there are certain analog meters where we have to sit down and then take readings on our own. But right now, with the help of vision models and other AI capabilities, what we can do is we can automate all these particular tasks so that our output or our efficiency of performing those particular experiments as well as collecting data will be increased multiple number of times. So what I feel right now is it is very easy right now for a student of physics to explore opportunities, identifying problems for research areas, doing literature survey, collecting data with the help of sensors integrated with AI, so that earlier record certain parts of it, but right now you can record any kind of data with the help of any existing setup by taking the vision models, as well as you can compute all also as and then prepare reports also. So what my feeling is that universities right now should provide this AI tool as a whole as a part of their curriculum. It can be used as a consumable budget from within that particular department, but every student should get an opportunity to do certain kind of analysis, certain kind of literature review, certain kind of report presentation for the department, for their own subjects with the help of AI, so that they are hands-on while going into the industry.
Thank you, sir. We want to hear from other panelists also on this point. How do you see the role of physicists evolving over the next decade? Salman, sir.
See, one thing I would add is artificial intelligence, fine. If natural intelligence and artificial intelligence, they are basically augmenting each other, fine. But when artificial intelligence starts basically weakening our natural intelligence, then obviously that need to be supervised. Literature survey, finding data, analyzing data, for that obviously AI is fine. But lot of situations now are arising when, let us say, a research paper is found written, let us say, almost 90% from, let us say, ChatGPT. So using AI for writing research paper and, let us say, utilizing AI for that purpose, then again, like, it can weaken our natural intelligence. So that is, I think, one precaution probably we all would need to take. Otherwise, fine, AI is again a tool, like so many tools. They emerged and they obviously they made some play. They are still used. So many tools are used. Help obviously understand things, understand data, understand, let us say, the old work, literature survey, whatever. But obviously, for innovation, natural intelligence will always be above artificial intelligence. But secondly, only that society will survive, will have basically the basis on natural intelligence. So for physics students, obviously, we cannot leave everything free, not everything only for AI. We need to have a strong basis to inculcate natural intelligence in our students and obviously in ourselves also.
Thank you, sir. Ashish, sir.
Yeah, Dr. Manmohan Singh has put very important points. So we should not be too much dependent on AI. It can decrease the intelligence of a person also. It will decrease his calculation power, his reading power, his writing power. So the supervisors have the responsibility to check that the students don't use AI tools to write papers or to write notes or other things. Paper writing at least should never be done with AI tools. After you have written the paper, then somewhere you may use AI tool to modify the title of paper and so on. Otherwise, don't use AI tools.
Sure, sir. Pawan, sir, your perspective in this point, on this point.
Yeah, I think these are very valid concerns. But I think we cannot stop the development in this area. So I think the models and everything, they will be keep evolving. And you might have seen certain benchmarks on like core skills, especially like say Olympiad exams in physics, chemistry, maths. So some of the these language models, they have surpassed in certain metrics, like they have surpassed human intelligence. So we are getting there. So I think I mean, for every technology that came in, we had always this valid question. So even like when calculators came up, like people started saying, okay, this might kind of limit human intelligence, and that's true in some sense. But I mean, this is how like the society is kind of shaping itself. So I think we cannot limit ourselves in using AI, but yeah, I mean, there is always this responsible and ethical use concepts are like that's always there. And as part of like I think developing the academic curriculum, I think or like training a research student, we should always be careful that we are kind of making sure that their skills are upgrading. They need to know like how to do proper research, how to write it, how to kind of look up at the ideas. So they should use AI as a, like a tool to augment their skills, not be relying on them. So that's definitely a valid concern. But like I mean, this is like a kind of two-way problem. So where we have to make sure like our new generation is kind of still able to like critically think, and they have the scientific rigor. And at the same time, we need to know like what's happening in this tech world, and we should not kind of limit ourselves in using those essential tools. Because if you have seen, so US was like I think kind of a big leader in this AI development and use. And now some of the Chinese model, they have even surpassed the US models, and they are kind of available at a very low cost or something. So, and there are not many native, I think, Indian models in that race. So I think government is putting a lot of effort on that. But I think we still need to make sure like whether kind of heading in the right direction.
Yeah.
US is contracting in all areas. Other countries are expanding. India is also rising.
India is in the region.
US is either contracting or stagnant.
Yeah, but I think here the major focus is about I think government puts like I mean they allocate a lot of budget to fundamental research and in all these core areas. So I think it's still there are a lot of I think good research that is happening here, and kind of the whole world is following that. So in each area, whether it's advanced manufacturing, quantum development, or AI or whatever. So and China is like really kind of competing, and they have a kind of almost neck to neck. So, but I think we are still not there. Honestly, that's what I have to say. Of course, we definitely have potential, and a lot of I think good brains coming from India. They are working in all these big tech companies that are kind of leading these developments. So yeah, so these aspects are always there.
Thank you. Thank you, everyone. Thank you to all our distinguished panelists for this valuable insight. I think the session was very much interactive and insightful. We now have some time for questions from the audience. Audience, do you have any questions?
I just have a question. So what is the major outcome of this event? Like, are you guys writing some meeting notes, or which you are kind of going to provide to some government agency or something?
No, we are not providing them to any government agency.
Okay. Yeah. Okay. That's okay.
Yeah. So one thing that I want to ask is that, I think Pavan, you mentioned, Dr. Pavan, you mentioned that we need to make sure that students don't forget to do critical thinking or use their minds, even though we are having using AI. Like, how do you think that can even be possible? Because earlier there was a AI detector, but students now know how to bypass an AI detector also. They can do that. So they don't usually
Yeah. So
do their own thinking on how things work. They just feed their doubts to AI and it gives a solution. Like, how can you like make students think?
Yeah, so I think faculties also need to learn AI. And these things will go hand in hand. So we have to kind of modify our curriculum to make sure, like I mean, the learning is not just by only like a project outcome or like an exam or something. It should be like more interactive and like students, they should be able to just not understand the research. They should also be able to demonstrate it, discuss with among their peers. So those, I think, uh, aspects like are very important in today's scenario. And of course, we should not judge them only based on like how they have performed in exams or in a particular assignment or something. So I mean that aspect is now kind of a little bit loose nowadays.
Okay, great. I agree.
Okay, everyone. So as we come to the end of today's session, let me briefly summarize some of the key takeaways. So today's conversation highlighted that the future of innovation lies in strong partnership between academia and research. Physics research forms the foundation of many transformative technologies, but translating research into real-world impact requires collaboration, interdisciplinary thinking, entrepreneurship, and a workforce equipped with both technical expertise and AI-driven skills. Our panelists emphasize the importance of industry-oriented curriculum, internship, technology transfer, startup ecosystem, and continuous learning to prepare students for the opportunity of Industry 4.0. On the behalf of organizing committee, I extend my sincere gratitude to our distinguished panelists for sharing their valuable experiences and insights. I also thank our audience for their active participation and thought-provoking questions. Thank you all. It has been a pleasure moderating this session. I hope today's session inspires stronger collaboration that will shape the future of physics-led and AI-driven innovation. Thank you, everyone. With that, let's move on to our next session. I invite Dr. Nupur to take the stage. Nupur.
Thank you, Dr. Pratima. It has been a wonderful session. On behalf of everyone present, I express my sincere gratitude to all the distinguished panelists. Thank you for sharing your knowledge and challenging our perspectives and making this session so dynamic and engaging. I'm sure everyone in the audience is taking back not only new knowledge, but also a fresh perspective and inspiration for future. As we come to the final segment of this remarkable summit, we now begin the valedictory session. And it is my privilege to invite Dr. Richa Verma, Head Department of Physics, JSS University, Noida, to summarize the event and vote of thanks. Ma'am, may I respectfully request you to kindly deliver the vote of thanks?
Thank you, Nupur. Am I audible?
Yes, ma'am.
So as we conclude this summit, I once again invoke the blessings of His Holiness, Jagat Guru Shri Shivratri Deshikendra Mahaswamiji. As I propose this formal vote of thanks for the Physics Sparring Industry 4.0 Global Summit 2026, organized by the Department of Physics, JSS University, Noida. On behalf of the Department of Physics and JSS University, I express my heartfelt gratitude to esteemed Vice Chancellor, Professor H.R. Mahadev Swami Sir, for his visionary leadership and constant encouragement. This was his dream, by the way. I also extend my sincere thanks to our respected Registrar Ma'am, Dr. T.G. Mamta, our Dr. B. Manoj Kumar Sir, Principal JSS-ATA Noida and Dean Academics of JSS University, Dr. Jagdish Sir, Academic Coordinator, and also Accounts Officer of JSS University, Manoj Sir, for always standing behind us. I thank all the deans, heads of departments, officers, faculty members, and staff for the invaluable support and gracious presence. To our students especially, a very big thank you for patiently listening on to the so many wonderful sessions. We are deeply indebted to our distinguished speakers for sharing their knowledge, insights, and experiences with us. I extend our sincere gratitude to Professor Ram Manohar Yadav, our chief guest and keynote speaker, Dr. Bindya Arora, Professor Manmohan Singh Sishodia, Dr. Alok Singh, Professor Atul Khanna, Dr. Deepak Kumar, and Dr. Pavan Tripathi, for whom the timelines are also a challenge. It's, I think, 4 a.m. At that place where he is. The enlightening talks on nanoscience, quantum technologies, photonics, renewable energy, artificial intelligence, and emerging industrial applications have greatly enriched the time. Today's discussions reaffirmed the crucial role of physics in driving innovation and shaping the technologies of Industry 4.0. We are confident that the ideas exchanged during this summit will inspire future research collaborations and encourage our students to contribute meaningfully to scientific and technological advancement. I would also like to thank all our participants, faculty members, researchers, and students whose enthusiastic involvement made this event a great success. Special thanks are due to the organizing team, the department, the whole department, technical team, all those who have worked tirelessly behind the scenes to ensure the smooth conduct of this summit. As we conclude this enriching gathering, let us carry forward the spirit of inquiry, innovation, and collaboration that has defined today's event. Thank you all for your presence and participation. Wishing everyone continued success in their academic and professional endeavors. Thank you, everyone. Thank you all present here.
Thank you, ma'am, for your gracious vote of thanks. With this, we come to conclusion of Physics Powering Industry 4.0 Global Summit 2026. And we also conclude a remarkable series of summits organized at JSS University, which was started as a vision of our VC sir, Dr. H.R. Mahadev Swami, for his constant encouragement. And I thank him and on behalf of my whole department for his constant encouragement and visionary leadership, which made this entire series of summit possible. With renewed inspiration and the shared commitment to innovation, collaboration, and non-building, nation building, let us carry forward the ideas, knowledge we have gained through these enriching discussions. With this, we formally conclude our Physics Powering Industry 4.0 Global Summit 2026. We wish you all a continued success, good health, and look forward to welcoming you at JSS institutions in future for many more academic events. Thank you. Jai Hind.
Thank you, ma'am.
Thank you. Thank you.
Thank you, sir. Thank you, everyone.
Thank you so much.
Kindly fill the feedback form. All present.
The feedback form has been shared in the chat box and also in your groups. So all the participants are requested that they fill up the feedback form so that we can provide them with the certificates in a week. Thank you. Thank you to all the participants. Thank you for joining.